wait for the numbers to suddenly jump up.
I'm gonna let everybody in now. There's a bunch of people in the waiting room.
So we're a minute past. Should we start the morning session?
Yeah.
Okay.
Sounds good.
Okay. Thank you all for coming this morning to the second day of this really excellent workshop. So I'm chairing this morning session. I'm Kieran Flanagan from the University of Manchester. Our first speaker today is Michael Ramsey Musold, who will be speaking on fundamental physics with atoms and molecules. You have 25 minutes, so over to you, Michael.
All right, well, thanks very much, and good morning, everyone from Shanghai. Just to let you know, in case the internet stability issue happens here, I'll do my best to reconnect, but this sometimes happens. So I was asked to give kind of a big picture talk, and in putting this together, I realized that most of the people here know the big picture, so I suspect that there will be a lot of repetition of what you already know, but nonetheless, maybe some new perspective. I just want to start with some sort of generic comments about the importance of these low energy tests. I think I'm probably preaching to the choir, but I think we'd all agree that low energy tests of fundamental symmetries and precision measurements do give a powerful window on possible physics beyond the standard model, as well as some standard model physics. And there is a really rich complementarity, I think, between these low energy studies and what's going on at our collider frontier and what we're learning from astrophysics and cosmology. And what's really impressive is the increase in experimental sensitivity at the low energy frontier is really pushing the reach into new territory and also challenging theory, I would have to say. And I think there really are exciting prospects for significant advances using atomic and molecular systems. So this workshop is really apropos. So what I'd like to do in this talk is just give a little bit more context, and then, if I had, as much time as I'd like, I would talk about both electric dipole moments and precision tests, but I suspect I'll only be able to get through the material on electric dipole moments, which really, to me, are the perhaps the most sort of rich area experimentally and theoretically. And I know you've already heard something about EDMs, but I'm going to give you some perspective on that, and then just a recap. So let's start with the context about low energy probes. And I think of them in sort of these categories. There are tests of fundamental symmetries, total lepton number, CP, charged lepton flavor, and baryon number in particular have been receiving a lot of interest in the community. Then there are the precision tests, with muon G-2 clearly being at the forefront of everyone's attention these days. But precision studies of weak decays and parity violation in atomic systems, and I should say not just electron scattering, but in atomic physics as well, is clearly advancing rapidly. And then there are these interesting searches for very light degrees of freedom, like sterile neutrinos, axions, dark photons, and so forth. So with regard to theory, where do you have to worry about standard model physics? Well, in the sense, the symmetry tests and the ultralight particles are sort of standard model background free, meaning that if you see something you see something new. Now, how you interpret it in terms of underlying dynamics still requires theory, but in terms of the ambiguity of whether or not there's an effect, if you achieve the experimental sensitivity, it's pretty clear that we don't worry about the standard model too much. On the other hand, for precision tests, the name of the game is to understand the standard model in order to pull out the new physics signals. So with regard to those boxes, there's another sort of diagonalization of that matrix that I put into 4 boxes, particular topics, searches for EDMs, and we'll discuss the interest there. Neutrinoless double beta decay is, as you probably know, receiving an enormous amount of attention these days, and resources potentially. Weak decays and other precision tests, and then studies of electron and muon properties and interactions. So in this talk, I'm really going to focus heavily on the EDMs, and these other precision tests I think are very interesting for AMO physics, but I, as I said, probably have too little time to say anything substantive in this talk. So let's go right to EDMs and review some of the reasons why electric dipole moments are very interesting. First of all, within the context of this, we still don't know whether there's strong CP violation via theta QCD. And so that would be fantastic to observe a non-zero theta term from the QCD Lagrangian. And then in the back of, I think, everyone's mind is we know that there has to be CP violation beyond the standard model to explain the baryon asymmetry. So where is that CP violation, and could it be seen in EDM searches or other low energy P&T violating physics searches? What is the mass scale associated with that CP violation? Does it live at the TeV scale? Is it very high scale CP violation? What are its force carriers? And then again, how, for this workshop, how can it be probed with the maximal sensitivity with atoms and molecules? And for theory, once we have a result, hopefully an observation, but no results even are interesting, how robustly and how can we robustly interpret the experiments with these various systems? So that makes EDMs, I think, all those questions very, very rich area for focus. Let me just review a little bit of formally what an EDM is. When we think of a spin a half particle like the electron or the neutron, there are 4 different interactions with an external photon that one can write down. And the electric dipole moment, of course, is this 3rd term here, the sigma mu nu gamma 5 q nu term, with the corresponding form factor F3. That's for a relativistic system. For nuclei at the heart of these atoms and molecules, there's a different way to organize these effects, and particularly interesting for non-relativistic diamagnetic systems. And these are the nuclear moments. So in this table, I have a list of various nuclear moments along the vertical axis and assumptions about the symmetries of the wave function across the horizontal axis. And let me just remind you what these are. So C means the Coulomb multiples. Tm means the magnetic multiples, J being, of course, the angular momentum. E are what are called transverse electric multiples. So if we look in the first column where P and T are good symmetries of the wave function, then a ground state matrix element of the Coulomb operators can exist for even J, for magnetic operators odd J, and they can't exist for the transverse electrics. Okay, so we have the charge, the quadrupole moment for the Coulombs, and we have the magnetic moment for the magnetic multiples and so forth. If we go over to the next column where P and T are violated, then what can be occurring in the ground state is a transverse electric moment with odd J. If T is violated but not P, it can be an even J transverse electric. And then the last column is when P and T are both violated, then the odd J Coulomb and the even J magnetic are allowed. So that would be the electric dipole moment or the magnetic quadrupole moment. So, most of the attention for diamagnetic systems is focused on the electric dipole moment or the corresponding quantity that's really of interest, the shift moment, which we'll come to. And then, it's very intriguing that this magnetic quadrupole moment exists. You have to have enough angular momentum in the system to see it. And then experimentally, how can you actually make a sensitive test? I think that's a very interesting question. And just, again, I'll have time to say anything about this or not, but the J=1 transverse electric moment, that's this so-called antipole moment, which is very interesting was interesting for cesium atomic parity violation. Is interesting for future work, for example, with francium. So these quantities in the green box are the sources of atomic EDMs for diamagnetic systems like mercury. And in particular, there's been a lot of interest in nuclei where there are nuclear enhancements to make the sensitivity to the underlying CP violation greater. So let me just recap what everyone knows, which are the current limits. And I won't go over the numbers here because I think everybody knows them, but let's focus on the bottom of the slide, which is a sort of a naive dimensional analysis mass scale sensitivity conclusion one would take from these limits. So with the limits in the table, if the CP violating phase is order 1, then the mass scale that's being probed is several TeVs. And if the mass scale is below the TeV scale, then the CP violating phases have to be very small, which is quite powerfully constraining for a lot of reasons, either way you look at it. And again, as you know, there's a lot of activity around the world trying to push the sensitivity of these EDMs by 2 orders of magnitude or more, which means the mass scale sensitivity goes up by a factor of 10. Now, with the Standard Model, how big would you expect the EDM to be? And let's do an example of the neutron. The neutron has QCD contribution and the CKM contribution. I'm just going to move my clock over here so I see how I'm doing on time. And the scale for the theta term contribution is 10 to the minus 16 e centimeters. So a limit on the neutron EDM of 1.8 times 10 to the minus 26 tells us theta QCD is smaller than 10 to the minus 10. And the corresponding number is very close to what one infers from mercury. And then there's the CKM contribution. And to my mind, the state-of-the-art sort of estimate of the size of the Standard Model contribution is in 2014, and it's of order 10 to the minus 32 centimeters. So well below where anyone is going to go experimentally for a while. So if you see an EDM in a diamagnetic system, or if you're in a system where there is no theta term, and you're looking for beyond the Standard Model physics, how big would you expect the beyond the Standard Model contribution to be? And here is, I think, a nice formula to sort of get orders of magnitude and to identify the various inputs for EDMs. So again, the scale is roughly 10 to the minus 16 e centimeters, which is really sort of e times 1 over the weak scale. Then there are 3 factors. The one that most people think about is the CP violating phase. And here the question is if the phase is large enough to be responsible for the baryon asymmetry. This first factor is a ratio of the weak scale script V over the BSM scale lambda. And the question is, what is lambda? So we don't know what the phase is, and we don't know what lambda is. And then the third factor, I write as y sub f times a function f. Y sub f is a fermion-Yukawa coupling. So for example, in the electron case, it would just be the electron's Yukawa coupling. And f is some function of the underlying particle physics dynamics. It could be perturbative, it could be non-perturbative, it could be strong dynamics. But because dipoles are, electric dipole moments are chirality flipping operators, they always come with a factor of y sub f. So there's really 3 unknowns in our estimation of how big an EDM should be, and you would like to unpack this. So a measurement of an EDM by itself doesn't conclusively tell us what these 3 inputs are. So we need information from at least 3 places, what I call 3 frontiers. And one way you might think about it is maybe you'll learn in a baryogenesis setup how big phi has to be. Then if you have a particular model, you might learn from direct observation of new particles in collider experiments how big lambda is. And then what you would then infer from the EDM result is something about the last factor, maybe something about the dynamics. Now, it's actually much more complicated than that because, as you've probably already heard from Vincenzo and Jordi yesterday, there's a lot that goes into connecting the high scale beyond standard model into the low energy world in which EDMs are measured. So this is my kind of flow chart where you can think of the vertical axis as energy scale running from experiment at the bottom to the experimental scale at the bottom up to the high energy scale above. And that's where there are these interesting connections with the baryon asymmetry or with collider physics. And then going down from the high scale, one comes to the weak scale where you, in a sense, integrate out the beyond the standard model physics into a series of effective operators, what we sometimes call the CP violating sources. And through a normalization group running, you can then run those down to the hadronic scale and start to match onto QCD objects like pions, pion nucleon interactions, or the neutron EDM itself, to light nuclei, go down even further in scale to the atomic and molecular scale and the nuclear scales. And we have all this interesting mini body physics that is being discussed at this workshop. So I know there are people who are speaking at this workshop who at least work on many of these aspects. I'm just going to flash some names out of my great respect for these colleagues of mine, and also my apologies to anyone whose name I didn't mention because I didn't really know who was going to talk about what. So I'm just throwing a few names up there. And my own interest has been a lot on the connection with the baryon asymmetry, but not exclusively. So very rich in terms of making connections. And so now let's talk about what we might learn if we can, go through this flow chart in a robust way. And again, it's important to distinguish the kinds of systems at low energy we care about. They're the paramagnetic and the diamagnetic systems. And in each case, one of the first things we have to contend with is the shift theorem, the shift screening effect. And let me just remind you what the theorem says. It says that the EDM of a neutral system will vanish if the constituents are non-relativistic, if they are point-like, and the interactions are electrostatic. So you might have a big EDM in some object, but you can't see it if all these conditions hold. And there's a very nice sort of semi-classical picture about the fact that a neutral object cannot accelerate in the presence of an external electric field. And so that means that the electric field at the center of all the charges has to vanish. And so if they're point-like, they just can't see, you can't get an E field into where the EDM is. There's, of course, a more sophisticated quantum mechanical proof of this theorem that we won't go into. So what's interesting then for us is not so much the theorem, but the corrections. And the corrections correspond to these different bullets. So if the constituents are relativistic, as they are in paramagnetic systems with large charge at the center, then you can get an enhancement. If the constituents are not point-like, as in nuclei, diamagnetic atoms with a large nucleus, then there's this shift moment that is the correction to the shift screening. And so that's interesting. And then in all cases, there are possible non-electrostatic interactions inside the atom that can induce an electric dipole moment and be sizable, as we'll see shortly, that are a way to get around the shift screening. So let's just review for the paramagnetic systems. You can ignore the cartoon on the right and just look at the table on the left and the formula. So the atomic EDM is proportional to some approximation. If we just consider the EDM effect, it's proportional to the electron's EDM, and the size of the proportionality constant rho is given in this table. And you can see that for various atoms, paramagnetic systems, that can be a big number. Look at francium, for example, whereas in the diamagnetic system, it's very small. So there's a big win due to this relativistic enhancement, which has been known for a long time. And then with polar molecules, again, which everyone here I think knows and loves, there's this effect of the internal electric field in the polar molecule being very large. So the name of the game is to get the electrons to line up with that internal field. And here's a nice graph from a publication by Ed Hines and collaborators that shows the relationship between the effective internal electric field and the applied internal electric field in the polar molecule ytterbium fluoride. And you can see you go from the kilovolts per centimeter scale in the external field to the gigavolts per centimeter in the internal field. And so there's this huge win in these polar molecules. So it's great opportunities. For diamagnetic atoms, again, we have this shift moment that we have to contend with. And the shift moment really gives rise to a P and T violating electron nucleus interaction that then is probed by the external electric field. And the shift moment is really an R cubed weighted moment of the CP violating component of the nuclear charge density. So you pay a price relative to an EDM of Rn over Ra when you go for a shift moment. And so something like mercury, you have to do a much more precise measurement or probe in order to get the same kind of sensitivity, say for theta QCD, that you would do with a less sensitive probe on the neutron, where there is no shift screening that you have to worry about. And within that context, then it's great to find nuclei where the shift moment can be enhanced. This shift moment comes about due to P and T violating nucleon-nucleon interactions that mix the states of opposite parity in the nucleus. And so because of, in perturbation theory, the 1 over delta E effect, if you can find systems where there's a small energy splitting between the opposite parity states, you get a big win. And one kind of system has been the so-called octopole deformed nuclei, like radium, where the parity states of opposite parity having to do with the orientations of the octopole in some reference frame leads to very small energy splitting and big enhancements. And I got these cartoons from John Engel, and I meant John to give you appropriate attribution here. I'm sorry about that. So those are some of the systems of interest. Let's talk about beyond the standard model implications, maybe in my last 10 minutes or so. And one sort of way to organize thinking is in so-called portals. And there are lots of portals I would love to talk about. I'm only going to talk about what's the Higgs portal, and others. I have some backup slides, but we probably don't have time. And so here's an example in a extended Higgs sector model, the 2 Higgs doublet model, whose details you don't really need to know, other than the relevant parameters besides the mass scale are a parameter called tangent beta, and it's on the horizontal axis in these plots, and a CP violating phase called alpha B, which is on the vertical axis. And in the panels, let's go on the far left, are the current constraints in what's called the type 2 Higgs doublet model, the current meaning as of 2014 when we wrote this paper. The present constraints, the blue is the thorium oxide, and I'll show you what the next one looks like. The red is the mercury, and the green is the neutron. And you can see that thorium oxide generally has the most sensitivity, except there are these blind spots in tangent beta that in principle can get probed by the diamagnetic systems in green and red. You can see they can fill in these little narrow places where there's no sensitivity in thorium oxide. Now in the future, which now is the present for thorium oxide, that's the middle panel where the dotted line is thorium oxide. There's still the blind spot, but the green and the red show possible future improvements in diamagnetic systems. And there's a new player here, radium, the radium-225 possible sensitivity, which can also fill in these blind spots. And over on the far right shows what happens if the neutron EDM improves by a factor of 100. So you can see there's quite some complementarity between these systems. And so, depending on whether you would see a result in all of them or in one but not others, that might either teach you where in this particular setup the CP violation is, or that it doesn't work in the type 2 Higgs doublet model. So it's quite important to exploit this. It's also interesting to ask how this compares to the LHC sensitivity. That's what's shown in this plot here that I just overlaid in something called the alignment limit. And let's just focus on this sort of magenta region here in the middle, which is the end of life sensitivity of the LHC for a particular decay channel that becomes open in the presence of this CP violation. And you can see it can kind of go into this sort of region here, this funny funnel region here. So what would be interesting is if you saw a signal there and you saw EDMs consistent with that region, that would start to tell you something about the mass scale and the CP violating phase, giving us at least a couple of those inputs that I mentioned earlier. Now let's say a little bit more about EDM complementarity. I want to look at the paramagnetic systems. And in paramagnetic systems, for those of you who don't know, there are actually two important contributors. There's the electron EDM. I've got a little mosquito going on here, so I'm waving my hand. And then there's an electron quark interaction that becomes a scalar. It's really a scalar quark and a pseudoscalar electron interaction. And you know, in any system, you actually constrain a linear combination. So you get ellipses. And so that's what's shown in this plot here. On the horizontal axis is the electron-nucleon interaction with a coefficient that's sometimes called CS. And on the vertical axis is the electron EDM. These different constraints include, you know, again, this was 2014, thorium oxide, ytterbium fluoride, and thallium, and they sort of all go in the same direction. So unfortunately, there isn't a lot of orthogonality here. But even then, if you find the 95% confidence level constraints, what you find if you translate them into mass scale sensitivities is for the electron EDM, about 1.5 TeV. It gets a little better now with the new thorium oxide result. And for the electron quark interaction, there's a generic sort of scale of about a little over 1,000 TeV, which is a fantastically powerful statement. That doesn't get a lot of attention, but I think it should. So you can ask, is there any model that actually realizes that mass scale, which is clearly LHC inaccessible? And there's one nice example, which is leptoquarks, where leptoquarks could induce through loops the electron EDM, but through a tree-level exchange of the leptoquark, the electron-nucleon interaction. And you can plot in the scale of the leptoquark and the CP violating phase, so that's on the horizontal and the vertical axes. The allowed region, according to the CS interaction, is this blue region here where my arrow points. And again, you can see the mass scale is over at the 10 to the 3 to the 10 to the 4 range, whereas the sensitivity of EDMs by themselves, whether it's electron, proton, or otherwise, are given by these colored lines, which are clearly ruled out in this model. So if the leptoquark model is right, then you would never expect to see the EDM, but you would expect to see the electron-nucleon interaction. And so if you saw an EDM in different systems, then it probably wouldn't be this leptoquark model because the EDM effect would be too small, whereas in a paramagnetic system, the CS effect would be dominant. So make one more BSM sort of connection here, which is with baryogenesis. There are lots of baryogenesis scenarios that people have worked on over the years. And part of the reason there are lots of scenarios is we have one number. And so you can come up with lots of scenarios to explain one number and live to tell another story. So what I've sort of organized here are a few of the interesting ones. According to energy scale in the early universe, when they would be active, that's the vertical axis. What's very interesting for EDMs are weak scale scenarios, which correspond in time after the Big Bang to about 10 picoseconds. So I highlight that in the dotted blue here. And something I've worked a lot on is electroweak baryogenesis. So I'm going to take an example to the power of EDMs to probe that possibility. And I'm going to do that in the context of what I call the minimal supersymmetric standard model plus. And the plus I can explain to you later, so let's not worry about it now. The relevant diagrams are shown in the upper part of the slide. There's a one-loop contribution involving the supersymmetric gauge bosons and fermions. And because of the LHC limits, this effect is actually precluded to be large enough to be interesting. On the other hand, there are still two loop contributions from what's on the right that are so-called bar Z diagrams. And there's one CP violating phase that's particularly interesting that shows up there and shows up in electroweak baryogenesis. So to illustrate that connection, I have on the bottom of this slide plots that show the mass of one of the supersymmetric mass parameters on the horizontal axis and the CP violating phase on the vertical axis. On the left panel, the horizontal lines or nearly horizontal lines are lines of constant neutron electric dipole moment. And to explain the observed baryon asymmetry, one would have to lie right on top of this funnel, this green V. So right now, the neutron EDM is not probing this scenario. On the other hand, on the right is the electron plot, and the current constraint, which is given at the 10 to the minus 29 east centimeters point here, is basically ruling out everything above. And so there's this only little tip of this funnel that's left. So that's a very powerful, result from this new ACME result, that it's really constraining this kind of electroweak baryogenesis scenario. There are ways around it. We don't have time to talk about it, but it's a very powerful probe. So lots of opportunities, as you know, with molecular systems, lots of horizons. I'll refer you to this archive paper here, and that's, of course, what this workshop is about. I think I probably don't have time to talk about precision tests, so let me just jump to my conclusion slide, and if there's time and questions, I can say maybe a few things about precision tests, but I'm basically recapping what I said at the beginning, and thank you.
Okay, thank you very much. So like yesterday, if you have questions, please put them into the chat as an exclamation mark, and I'll start working through them. Let's see. So maybe I'll start the, here we go, Robert.
Yes, I have a question to your slide number 13, because there was one of the moments which you did not discuss, namely next to the underpole moment, there was a T violating transverse electric moment. How about the prospects of seeing this? And
yes, a very interesting question. I'm not sure what observable you would design to probe that. Pure parity conserving time reversal violation, as you know, has been studied in other contexts, in neutron transmission experiments and other things. But in the context of an atomic system with a nuclear moment at the center, I don't know of a direct probe. Now, there's work in progress that I'll just share with everyone, that if you have a system where you have two photons being exchanged between the atomic electrons and the nucleus, and one of them has a transverse electric 1, and the other has a transverse electric 2, and you combine them into angular momentum, you can form a P and T violating effect that has J equals 1. So it has the same angular momentum as the shift moment. So there is a correction actually to the shift moment that comes about from the product of these two transverse electrics. But we don't have the final paper out on this yet. There's a lot of atomic physics that's being checked. But I don't know of something that would directly probe the transverse electric 2 in atomic physics, but maybe, in electron scattering, it would, again, people could think about that. I'm not sure. It's an interesting point.
Since you highlighted atomic physics, would it be different in molecular physics?
Not that I'm aware of.
Okay.
Yeah.
Yeah, thank you. Anastasia?
Yes, thank you for the nice talk. I was curious, one of the last slides you discussed were the two funnels.
Yes. Let's go down there. Da-da-da. Sorry, just jumping around my slides here. Here we are. Yes.
So what happens if you get the next generation thorium oxide experiment and your funnel is gone? What does it
then you have a lot of theorists going to the bar. to hang their head in sorrow over the death of this scenario, because this particular electroweak baryogenesis in supersymmetric models then becomes very, very tough. There are other weak scale baryogenesis scenarios that could survive, you know, a very tight electron EDM constraint, you know, a thorium oxide constraint, for example. What I call sort of stealthy or secluded CP violation. I think that's the word I use for it. And we have an example that we wrote about a couple of years ago where you could get around this. But that kind of result would say you have to put the CP violation in a way where it's not nearly as accessible to EDMs in order to explain the baryon asymmetry. Whereas in these sort of generic weak scale setups, you know, the CP violation is going to be right out there. And so that's what I think you would be taking away from these, you know, improved limits, assuming nothing is seen. But let's be optimistic. Maybe something will be seen, in which case, you know, there would be a lot of excitement, of course.
Then everyone will be happy indeed. That's, okay, thank you.
Thank you, Michael. Thank you again for an excellent talk. We move on to our next speaker now, Jacek Dobuczewski. You got your presentation.
Let me share my screen with you. All right, do you see my screen and hear my voice? All right.
So Jacek will speak on electromagnetic moments in nuclei within nuclear DFT. Over to you, Jacek.
Thank you. All right, so let me begin with the introductory slide. 4 years ago, we have established what we call a nuclear magnetic moment collaboration. Apart from establishing it, not much things have been done. Recently, we managed to do substantial work, mainly because we had a contribution from my student Paolo Cesarini and from Jeremy Bonnat at York, and also we had a great help from the chairman of our workshop. In the literature, very little has been done in describing magnetic moments in DFT. This is really strange that this observable was not exploited, almost nothing has been done. So there are some studies, there are some books written in the shell model, interpretation of magnetic moments. There are very nice, there is a very nice review article by Gerda already a few years back. And apart from tables of experimental data, the only purely DFT calculation which exists up to my knowledge are the two papers, one with the Goni interaction, another one with Skirm, and there are few analyses based on the spherical nuclei with RPA corrections. That's about it. It's really amazing. If you know about anything else in this domain, please let me know. I couldn't find things which would be of that type up to now. So let me now go to the outline of my talk. Sorry, here I have to remove these things. All right, so I will mostly talk about two items. I will give you a very brief recap on the electromagnetic moments in nuclei, and then the main subject will be the analysis of magnetic and quadrupole moments in the simplest cases, the nuclei which are adjacent to doubly magic nuclei by removing or adding one particle. And then I have several other topics in open shell nuclei. Indium isotopes have been submitted recently. I have a calculation in inequality 3 isotones. There is a paper in the archive about the magnetic octupole moment in scandium-45. There is an old paper of with a collaboration with John on the shift moment of actinides, including radium-225. We have a project on thorium-229 and its magnetic and electric depopulation of the isomer. I won't be able to cover all that. I will probably go to the conclusions after I cover the main subject of the talk. So let me now go to the recap. To remove these things again. All right. So the quadrupole and magnetic moments in nuclei are result of the single particle operator with some caveats which I cover later. So if you reduce the analysis to single particle operator, everything is based on the quadrupole density and the magnetic density, which are and integrals of those give quadrupole and magnetic moments of different orders, which are here denoted by lambda. And these quadrupole and magnetic densities are very simple. The quadrupole one is just a product of the density with the quadrupole form factor, and the magnetic one is composed of the spin density and the object, which is more or less a density of the orbital angular momentum, because it's a vector product of the distance times the current. And these objects here, Q form factors, are solid harmonics. So these are definitions. Now, if you look at specifically magnetic moments, very simple estimate of what magnetic moments might be is given by the Schmidt limits. Simply, you take a spherical nucleus, you occupy one single particle state, and then you can very simply analytically derive what would be the magnetic moments of the odd nucleus. These are called Schmidt limits. They are written here. They depend more or less on the total angular momentum of the single particle and two parameters, which are just single particle values of the spin magnetic moments of a neutron and a proton. So this is the simplest way to describe magnetic moments. If you look at data, here I have an example of data collected very, very long time ago in 1955. And you see that all known data at that time, but also now, lie between two limits which correspond to the Schmidt lines. So you can say there is nothing interesting happening here. On the other hand, things which are interesting happen on a very, very extended scale, because you have to look in very detailed values of magnetic moments if you want to learn something beyond a pure single particle model. The same conclusion holds for neutron odd systems where the Schmidt limits are almost constant. So the focus of today's talk is on the odd nuclei next to doubly magic ones. And here is the illustration of what I will be talking about. I will consider 8 doubly magic nuclei from oxygen through calcium, nickel, tin up to lead-208. Each of these doubly magic system has 4 neighbors where you either add proton or a neutron or subtract proton or a neutron. So you have a hole is a neutron in a neutron or proton system. So altogether, we have a playground of 32 simple nuclei, and many of them are not known experimentally. However, in theory, we can have a review of all these 32 calculations and try to find some regularities in the results which we obtain. So first of all, this slide contains a lot of text, but let me tell you the story of the quadrupole and magnetic moments in these simple systems. Of course, you can speak about these systems in terms of the shell model, but the DFT picture is quite different. For instance, suppose you want to analyze the quadrupole moment of such a single particle added to the spherical core. If you do that in DFT, you have to put the odd particle in one of the suborbitals split by deformation. So, for instance, you have a G9.5 state. It has 5 different magnetic components. They become split in the deformed field. So when you do DFT, you have to make a decision which suborbital you occupy. But no matter which one you occupy, every one of them will carry a quadrupole moment. And then the polarization story begins, because this single particle quadrupole moment will polarize the core. The core will acquire some quadrupole moment, and by the self-consistent mechanism, this induced quadrupole moment of the core will influence the hot particle, and this self-consistent influence will be summed up to infinity. That is a self-consistent solution of mutual polarization between particle and the core, and at the end of the day, we'll obtain a total quadrupole moment of the system, which will be which will have contribution both from the core and from the hot particle. And the same mechanism holds for the magnetic moments. However, here it's not the charge which is polarized, it is the spin distribution which is polarized. The interaction which is now in action is the spin-spin interaction, again up to infinity summation of the mutual polarizations between particle and the core will happen, and at the end of the calculation you'll obtain a total magnetic moment of the system with spin and orbital contributions both from protons and neutrons. Even if your hot particle is a proton, you will have a contribution from the neutron coming from the core and the single particle states. So this is the mechanism, by which you obtain non-zero quadrupole and magnetic moments in the DFT. So let us look at electric quadrupole moments first. Here is the world data set of 13 measured values among these 32 nuclei of quadrupole moments. So you see the plot shows the experimental quadrupole moment versus theoretical quadrupole moment. So in the perfect life, that would be aligned with a blue line or solid line. Those results which are outside the narrow region of the main plot are shown in the inset. You see that the values are very, very small. Even in the heavy nucleus like bismuth, these quadrupole moments do not exceed half of Barn, which compared to the collective quadrupole moments in the open shell nuclei is a tiny number. The results which we obtain are fairly decent. Here, not a single parameter was adjusted. The results are shown as an average of 5 different functionals. There is a set of functionals here of different type. There are 3 functionals of the Scherm type, namely they are local or quasi-local functionals, or zero range if you prefer, speaking about the range of the interaction. There are 2 functionals which are non-local, namely based on the finite range interactions, and all of them give almost the same results. The relative root mean square deviations between these 5 functionals are illustrated here by the horizontal error bar, and only in one case you can see a visible error bar. So apparently DFT is stubbornly predicting these particular values, which are slightly away from experiment. We have to look for a common reason for this deviation, which probably is not within the realm of different functionals. That must be something different here. Now, one very important remark here, what I compare here are really spectroscopic moments in the symmetry. Excuse me. The symmetry is exactly conserved. So the measured moment and the calculated moment are simply spectroscopic moments directly comparable one to another. Now let's look at magnetic moments. So again, the same type of comparison of a global set of measured values. There are 21 values measured. There are some measurements which are known but not published yet. But among these 21 values, we can compare the results, this time for one of the functionals, SCERM functional UNIDEF1. So this is this functional among the 5 which I've been looking previously. And here I have made an adjustment of one parameter, Landau parameter. I will come back to that in a second. So again, you can see that the agreement is decent. I would say that here at the precision which we are looking at, there are 3 outliers: bismuth 209, gallium 207, and nickel 57, which differ, calculation differs from experiment by about 1 magneton, and this is a lot. And this scale, this is a big difference, and we have to find reasons why these particular outliers are visible. So let me now go into details of this approach and tell you how we adjusted the parameter and what is the methodology which we use. Again, a busy plot, but I would like to, I must tell you how this adjustment is done. The main thing, as I said, is not an interaction in DFT, but the functional. The functional is the energy density. So the energy density is the function of densities. We have different densities in the system. The most important for the magnetic moments are spin density and the current density. And the terms of the functional, which depend on these spin and current densities, is a simple spin-spin term, which more or less corresponds to the spin-spin interaction. And there are more complicated terms which involve currents in combination with other time-odd densities. So in principle, we are free to change this term because it doesn't influence the time-even properties. However, the gauge invariance connects time-even and time-odd densities here in these 2 combinations. And without changing time-even properties, I would not venture into changing this term alone. So for the moment, we'll concentrate only on the spin-spin densities. And I will illustrate the changes involved by changing the coupling constant here by looking at the object which is called the Landau parameter, which is just another representation of the spin-spin term. So these Landau parameters are characterizations of the system in the time-odd channel. They can be estimated from all kinds of time-odd observables like spin alignments in rotational bands, for instance. However, they are not very well known, and a typical range which is allowed for exploration probably somewhere between 1 and 2, maybe going between 0 and 3 is a reasonable way to look at the results. So what is shown here is the dependence on the spin contributions to the magnetic moments in function of the Landau parameters. And as you see, there are very conspicuous differences between different orbitals. There are some nuclei where the dependency is 0, it's completely flat curves like those. There are curves which depend quite strongly on the Landau parameter, and there are intermediate cases where the dependency is weaker. And I think we can use this classification to understand what is the physical role of the Landau parameter in the spin-spin interaction. First of all, these flat curves always correspond to very light systems in which the Fermi surface is not separating spin-orbit partners. And the strong dependence relates to the nuclei in which the Fermi surface does separate spin-orbit partners. So visibly, the magnetic polarizations of these nuclei are related to the mixing between spin orbit partners. If you look at the comparison with data, here is a difference between theory and experiment, and so 0 would correspond to the perfect agreement. You see that in function of the lambda parameter, there is a region in which the results cross 0, and probably this value for this particular scalar force, the values of the lambda parameters in this region would be something reasonable. And what I showed you in the previous view graph was exactly the value at 2. There are some outliers, like indium-131 does not cross 0 at the same point, so there is plenty of analysis here to be done, looking for the reasons why this particular pattern happens. Now, if you look at the adjustment, if you look at the root mean square deviation between experiment and theory, the story is quite complicated because the minimum of the deviation happens at different lambda parameters for different scale forces, and also for the finite range forces in which you don't have this luxury of changing the spin interaction alone. You see that the values of the root mean square radius are not so nice as for the minimum related to the Scherm interaction. However, we have a clear sequence of the lambda parameters. The smallest one in this analysis is for the D1 with D1S Goni functional, then is coming the regularized one, and the Scherm functionals also have a specific sequence of the lambda parameters. So if I look now at the detailed comparison between experiment and theory in these 32 nuclei, so in some nuclei, of course, the experiment is not known, but you can clearly see that the dependence on the lambda parameter has this very typical structure, namely from Goni to regularized to UNIDEF, the dependence is really regular and quite often goes down to the experimental point if I pick this particular value of the lambda parameter. This is nice in many cases, like here. It is not that nice in some cases, namely for indium. This is a particular case in which the UNIDEF value for 2 overshoots experiments. In other cases, nothing happens between the Schmidt value calculations and experiment. This is exactly the same number. In some other cases, we don't go down to the experiment, and these are these outliers. For instance, here, the case of bismuth is not very nicely reproduced by this calculation. So let me not discuss the details of the other set of nuclei, light nuclei, and which are almost the same, the Schmidt values. Let me go now to the last point of the talk, namely the problem or a question of effective spin G factor. In the shell model, this is a workhorse of comparing results to data, namely when you obtain the result in the shell model for the magnetic moment, usually the obtained result is multiplied by effective G factor, which is of the order more or less 0.7, or it varies from the shell to shell. Here in DFT, we can do the following analysis, namely for every single measurement of the magnetic moment, I can assume that the experimental value would have been obtained by using a given value of the effective spin G factor, simply multiplying a single particle value by a number. And if I do this for the set of results which I obtained and illustrated before for UNIDEF with this particular value of the lambda parameter given here, this is the set of numbers I obtained. The average is close to 1, with a root mean square deviation which is compatible with 1, and it never exceeds 20%. There are these 3 outliers, which probably these results cannot be explained by these simple configurations anyhow, but the conclusion from this analysis is that DFT, in contrast to the shell model, does not include information about the possibility to use the effective spin G factor, namely single particle operators do quite a good job. This is very important because we are not certain at all what the real true magnetic operator looks like. There could be contributions from the delta resonance or from two-body currents. At the moment, when looking at this set of nuclei, we don't see any compelling reason that these contributions are important. And we would like to use here an Occam razor. If we don't see it in the simplest case, maybe it will be difficult to argue that the operator has to be changed because if you change the operator, you will have to keep these experimental values compatible with theory for the set of particularly simple nuclei. So as I thought, I would not be able to cover other subjects, so let me jump over to the conclusions after clearing this oval. So conclusions from this talk are the following. First of all, this is an extremely rich set of experimental data. Electric and magnetic moments have been measured in hundreds of nuclei to the very high precision, and we need a global analysis of this observable, and DFT does provide a global analysis. It is not done in the particular valence shell. It is the analysis which relies on overall properties of functionals, and the same functional in principle should cover all nuclei. Of course, the simplest configurations may not be enough. Maybe we need some configuration mixing and refining. However, this work is ahead of us. We need to consider the DFT calculations, especially for magnetic moments across the mass chart, not only in these simple nuclei, but also in complicated open shell systems. And the main goal here would be for nuclear theory, would be to look at the adjustments of coupling constants in this poorly known time-odd sector of the functional. And here a lot of work needs to be done. Thank you very much.
Thank you, Jacek. An excellent talk. Have questions from the audience? If you have any questions, please put them in. Yes, I see a couple immediately. Safranova, do you want to go first?
Hi, thank you for a great talk. You mentioned thorium-229 in your original outline. I would love to hear about it. You skipped the slide.
Yeah, thank you very much for the question. This gives me an opportunity to present you a project which we have. You don't have results yet. However, the project is to analyze this thorium system using a set of sperm interactions to have some spectrum of results. We have this is the open shell system, so it must be the paired system must be used. So we first of all have to adjust the pairing. We do it in the sequence of 3 thorium isotopes and in the sequence of 3 isotones around thorium-229, and then first of all we have to look at single particle structures, and we do see the orbitals which are probably responsible for the isomer. Certainly there is no chance we can get up to the degeneracy of the isomer of about 8 electronvolts, but these typical orbitals are there. So having these orbitals, we are going to calculate the magnetic moment of these orbitals, and in particular the transition matrix element between the isomer and the ground state. And here we are able to calculate not only the M1 transition, but also E2 transition and the mixing factor between these 2 transitions. So all this is in the making. Jeremy Bonnard is working full time on this project, and we hope that it will be possible to give you more details in not too distant time.
Thank you.
Robert Berger?
I have a question to the slide where you showed the 13 measured values for the quadrupole moments, and there you had one case where you had on the theory side a relatively large deviation, but you didn't mention which nucleus that is. And is this also a case which is troublesome for the magnetic moments, or is this all fine?
Excellent question. The troublesome case is again Bismuth 209.
Mm-hmm. Okay.
This is this quadrupole moment here, which is a clear outlier. Well, of course, if you look at the scale of this figure, you can say that there are also deviations here, but these particular quadrupole moments are really tiny. I mean, the precision here is I mean, probably well beyond what we can do. But this deviation is probably the biggest one here. Well, of course, there are some other cases which also deviate, but in the percentage rate, probably this one would be the most important.
And then the Triton case was outside your Schmidt model estimate, right? On the one slide, or a few slides earlier. When you had the Schmidt model, then I think you had one case which was outside the range of the Schmidt model. If you go to one of the slides earlier.
Oh, you mean these ones?
No, just in the very beginning, you had the case where you said, oh, the Schmidt model is covering a range from 2, and
yes.
all nuclei are essentially in this range.
Oh,
but if
okay,
you look to
here.
the very left,
yes.
One slide earlier, I think, then the Triton is, no, or was it helium-3? So that I didn't remember, which
yes.
was outside
well,
the range. Is there a specific reason why this is outside the range?
I don't know, but there is no theorem here that must be within the range, because you might have an antipolarization of the spin, which will go outside the typical spin average, which results simply from the spin-orbit coupling. The Schmidt value is a spin polarization corresponding to the spin-orbit coupling of a pure spherical orbital. And of course, this value can be outside. The real value can be outside.
Okay, good, thanks.
Good.
Yes, thanks, Jacek, for a very interesting talk. So nice to hear that finally, indeed, you can make these calculations of lots of nuclear moments. My question was a bit along the line of Robert's. So the outliers, is there something fundamentally in the theory you think that's missing? Would you recommend remeasurements? Because, for example, bismuth I know has been remeasured recently, very precisely the magnetic moment. So I don't think there it's related to the experiment. So, do you have an idea what's the problem?
Yeah, only once in my lifetime I was able to tell experimentalists that their experiment is wrong. It's not today. I don't believe any experiments here are really to be questioned. Certainly, there is a problem on the theory side, and the first culprit is the configuration mixing. I was using here the purest possible configurations when you put one particle or one hole into a specific orbital, and then you may have all kinds of configurations mixing, namely the mixing with rotational bands, for instance. You can have another configuration and a rotational member having exactly the same angular momentum. You may have a collective configuration mixing where not only one point on the deformation plane, but the wide region of deformations contribute. All this is work to be done. I don't think I can comment.
So this is
more
all
about that.
blocking one nucleon in a particular orbital when you do the calculation.
This is the case which I'm showing you now. Yes.
Yeah. So this, of course, can explain already a little bit. Yeah.
Yes.
Okay. One final question from Thomas Koukoulias.
Yeah, thank you, Kieran. It's actually a reaction to Gerda. I believe 57 nickel has been measured on a single point beta NMR resonance in the same way as copper 57 was done in the past, and that there was a big discrepancy there, which got corrected once the laser spectroscopy was done. So this is one where we could, as experimentalists, look back in the literature just to confirm how it was done and how confident we are, and evaluate there whether we could verify the measurement. I had looked at it at the time because it was very much linked to the physics case. So I was a bit concerned. It looked more reliable than copper, but the A=57 isobars is indeed a very crucial case that experimentally is very challenging.
Thank you, Thomas.
Thank you, Thomas. Okay, thank you again, Jacek, for an excellent talk. We go to our next speaker in this session, Jonathan Engel.
Okay, is that visible? And whoops.
You can see it.
You can see it, okay. So I hope this talk is going to be accessible, somewhat accessible to people who aren't nuclear structure physicists. I thank the organizers for inviting me to this meeting. I really wish it were at MIT, so I'm going to pretend I'm there for the purposes of this talk. Okay, so I want to talk about what the future of shift moment calculations hold, and perhaps talk a little bit about the uncertainty that plagues these calculations and what we can do about them. So just a little background to begin with. So this is stuff you all know, but here's a cartoon of how diamagnetic atoms get electric dipole moments. They come from presumably from some undiscovered source of CP violation that can eventually work its way into a pi-n vertex in chiral EFT. So here's some quarks and they exchange something maybe, and this is a CP violating pi-n coupling. And that can lead to a neutron EDM through a diagram like this, as we saw yesterday. And it can also lead to a nuclear EDM when this, as we also saw yesterday in talks by Victor and Yordi and Vincenzo, when this CP violating pi-n vertex couples to a pion, which then goes to an ordinary pi-n vertex inside a nucleus, that gives you a CP violating nucleon-nucleon interaction. And then the nucleus eventually emits a photon. A virtual photon that is going to can generate an EDM. And this interaction, this CP violating interaction, which I call VPT, parity and time reversal violating, has some factors here. There's 3 of these things corresponding to a different isospin structure. These are constants that you can try to calculate from QCD and from models of CP violation, but that a priori we don't know. And then there's this structure for pion exchange with CP violation at one vertex. And there's, as we heard yesterday, there's also contact terms, zero range, short range stuff. Now, this is CP violation in the nucleus, and then atoms get their EDMs from the nuclei when nucleons exchange photons with the atoms. But as we also heard many times now, the electronic screening replaces the nuclear dipole operator with a Schiff operator. So instead of being sensitive to nuclear EDM, it's another moment called the Schiff moment that matters for the nucleus. And that is like a charge weighted EDM. So this is the Z coordinate of the proton, and it's weighted by R squared. So it depends on R cubed rather than just R. And there's another term here, which comes in when you derive this carefully. And this makes the relevant nuclear quantity, not the nuclear EDM, but the nuclear Schiff moment, which in terms of this Schiff operator, I can write the expectation value of this operator. Because this VPT is so weak and is required to generate this, I can write this in first order perturbation theory as VPT acting on the unperturbed ground state of the nucleus. It excites all possible intermediate states, and then the Schiff operator de-excites them again, and there's an energy denominator. So that's just standard first order perturbation theory. And the job of nuclear structure theory, the one that I've been involved in, is to compute the dependence of this Schiff moment on these G bars, these pi-n couplings. and also on the contact term coefficients and on the nucleon EDM, on anything that causes CP violation inside the nucleus. And then it's up to effective field theory and quantum chromodynamics to compute the dependence of these G bars themselves on the fundamental sources of CP violation. So that depends not only on the source, but also on quark-gluon dynamics inside the pion and in nucleons. And Vincenzo, Jordi, and Michael all talked about these aspects to some degree. Okay, so now I want to talk a little bit about the kinds of nuclear models that have been used to compute the shift moments. So here is nuclear structure physics as it was a little while ago in one slide. So the starting point, no matter what your method is always a mean field. So what that means is that you approximate the nucleus as being, you approximate the nuclear wave function as coming from a potential, just a one body potential that comes from the average of all the nucleons. So this is like Hartree-Fock or something like that, where you pretend that the nucleus is just seeing a potential generated by all the rest of them. And you don't worry about correlations between the nucleons. That's your starting point, and I'm denoting that by this little picture of nucleons orbiting around the center of the nucleus as if there was some potential there that was being generated there. And this gives rise to a wave function, which is independent particle orbitals, and they are filled up to some Fermi level. So here's a neutron Fermi C, and here's a proton Fermi C, and this is the wave function in mean field theory, in mean field approximation. And then the way different models expand on this mean field picture is different in different models. So RPA, or density functional theory, is slight corrections to this kind of picture. And it has the virtue of including all these many orbitals in the wave functions, but the corrections to this mean field picture are relatively simple. So there's simple one particle, one hole excitations like I have here for protons, or the same thing for neutrons. A neutron is excited out of this Fermi C into a high-line orbit. And this kind of treatment and similar things are at the basis of DFT. And what you really focus on is getting this mean field as good as possible, really, in a really sophisticated way. And that can involve the use of density functionals, as Jacek was describing, and other kinds of more sophisticated mean fields than just this Hartree-Fock thing. The shell model is sort of an opposite picture in which you neglect all these high-lying orbitals and these low-lying ones within the Fermi C. You assume that these nucleons here are frozen and these ones aren't occupied at all. And you just treat the dynamics within these levels around the Fermi surface. But within those levels, you consider all kinds of correlations. So many particle, many hole correlations. So these pictures have complementary virtues. And for the sake of something I'm going to talk about later, I will tell you about an extension of DFT, although it can be applied in other realms as well, called the generator coordinate method, in which you take these mean fields, but you allow them to have all kinds of different shapes, and then your wave function comes from mixing these various different mean field wave functions, lots of them. But you still don't have these kinds of detailed correlations here around the Fermi surface. So the problem with all models like this is that they require phenomenological Hamiltonians or functionals and operators with coefficients that are fit to energies or transitions in the heavy nuclei you're looking at. And this is a problem. It can be a problem if you're looking at operators like VPT, this time reversal violating potential, which you need to compute the shift moment of the nucleus, for which there are no data. We can't go ahead and say, oh, okay, let's look at the measured VPT between two levels in some heavy nucleus, and that'll tell us what to use as our operator for. Sorry about that. For our calculation in radium-225, for example. So before I talk about one way of trying to deal with that, let me just describe the calculations in radium-225 that I was involved in and with Jacek. And In this nucleus, as we've heard earlier, unlike other nuclei, where in this expression here you have to worry about all these intermediate excited states in first order perturbation theory. Here, the only one that's relevant is this first excited, not the first excited state, but the parity doublet partner of the ground state. So the ground state is 1/2 plus, and this state has the very same intrinsic structure, but it's negative parity. And this is the only one that matters. The other ones are connected much weaker by these operators in much weaker way. And when you go look at this more carefully, you find that if you do this kind of mean field theory, density functional theory for this nucleus, you find a deformed, octuple deformed shape. And to some approximation, these parity doublet states, you can think about them as the composition of the superposition of this deformed state and its parity transformed partner with plus or minus signs in between. And to a good approximation, this shift moment just comes out to be the intrinsic shift moment of this shape. So it's a collective quantity, like the intrinsic octupole moment. And the expectation value of this VPT, also in this deformed shape. And then there's this energy denominator here, which we benefit a lot by from the fact that it's so small. So as Victor said yesterday, there are several reasons why this is large. One of them is this small energy denominator. One is this large intrinsic shift moment. And this factor here is more delicate, I think. And that's also the thing we have the least control over, which I'll just talk about in a second, this expectation value of VPT. So Vitek Nazarevich is going to give a talk later on about some recent work on octopoles in DFT. And I think, I'm not sure, but I'm speculating he might present a figure like this, where they have examined nuclei all over the periodic table in density functional theory to look for ones which are particularly promising for candidates for shift moment experiments. Here's just plots of octopole deformation with different Skyrm functionals. And this is from a paper that I was on with Jacek. This was really Jacek's idea, which was to correlate the intrinsic shift moment, which is half the ingredients in this laboratory shift moment, this thing here, this intrinsic shift moment, with the intrinsic octopole moment. And since the intrinsic octopole moment has been measured in radium-224, we can look at these predictions for it in radium-225 from different Skyrm functionals, different density functionals, and choose the ones which match the experimental octopole moment prediction, intrinsic octopole moment prediction. These all lie on pretty close to a line here. And this allows us to narrow down the intrinsic shift moment in a pretty significant way. And here the correlation is plotted versus radium-224 intrinsic octopole moment. So this is an octopole moment, shift moment. You have this correlation here. But when you plot it versus radium-225, the correlation is even better. And this moment is supposed to be measured at argon, on the radium-225 octopole moment. And there's similar correlations that observed in other octopole deformed nuclei, which you might want to use for shift moment for EDM experiments. Now, the problem with this has to do with the other ingredient, this VPT. So we also tried to look at the correlation of the intrinsic octopole with the laboratory shift moment, which now has, in addition to the intrinsic shift moment, also this expectation value of the time reversal violating potential. And here again is the intrinsic octopole moment and the shift moment. And although this looks pretty good here, here's what we got. This is the correlation again with radium-224 intrinsic octopole moment, and now you have the laboratory intrinsic shift moment. And these are these three things which multiply the 3G bars. So here is the coefficient that multiplies A1 bar, A2 bar, A0 bar, and A2 bar. And you can see that they look pretty well determined. But the problem is when you include octopole moments in other nuclei besides radium-224, this picture gets considerably blurred out. And as a result, we concluded that the uncertainties on these coefficients, which these A's here, were pretty large. And in fact, in this isoscalar channel, we weren't even able to determine a sign. Although these order of magnitude estimates, I think, are good. The other thing that I ought to point out is that although this range has to do with what different Skyrm functionals, different density functionals produce for your answers, they don't tell you if something is wrong with the whole framework. So if all the Skyrm functionals suffer from some deficit, or if the whole DFT procedure suffers from some deficit we don't know about, then that's going to give you another error which is not included here. So in fact, the real, I mean, if you're really being careful about quantifying uncertainty, which is what we're trying to do better and better in nuclear structure theory, this would just be what we call statistical uncertainty, and any systematic uncertainty is not included here. So how can you reduce this? Well, the problem, as I mentioned, is that we don't have any information about this VPT. So one thing I've been asking people without getting much of a satisfactory answer so far is, can we find measurements that will help constrain its matrix element in the same way we found that that octopole moments help constrain the intrinsic shift moment? And in the one-body approximation, this VPT can be represented as an operator that looks like sigma dot gradient rho, something like that, or which is close to something like sigma dot r. So is there any way we could measure sigma dot r between that matrix element between these important states in radium-225, or some operator like it, even sigma dot p would be useful? Is that at all possible? Might it be possible to look at related transitions? So this operator here, sigma dot r, is related to the axial charge beta decay operator. Can you look at axial charge beta decays of states in nearby nuclei? Is that something which could be examined at all? The full two-body VPT is similar to the full two-body current operator in this axial charge channel. That gives you a correction to the axial charge one-body matrix element, but it's a significant one. And so this axial charge beta decay would be a very similar kind of operator. Is it possible to find anything where we could measure that? Those kinds of things would give us some information that we could try to examine in our nuclear structure calculations and see how we do, see if the operator needs to be modified in any way. Barring this kind of approach, the other option, and I've become more and more involved in this kind of thing through work on double beta decay. The other option is to try to do an ab initio calculation, a first principles calculation, where you can try to control the errors. And there'll be talks about this later on, I think, about other related approaches to what I'm going to talk about by Jason Holt and Peter Navratil later in this session. I assume that's what they're talking about. Okay, so how does an ab initio nuclear structure theory work, and how do I contrast it with the models I was talking about earlier? So here, you really start with a nucleon-nucleon interaction as determined by, at the 2-nucleon and 3-nucleon level, by experiment and by chiral EFT, which you heard about yesterday, which is a power counting scheme for determining which operators are important and which can be neglected. You go to any order in powers of momentum exchange divided by about a GeV. And a typical momentum exchange is like the mass of a pion, so this number is about a third typically, or half. And if you can work to any accuracy you want in expanding this quantity, and at each order you find more and more terms, but at any order you can stop and fit all the terms in these operators here, and that gives you a nucleon-nucleon interaction that should be good to any accuracy that you want. Now, this theory is not rigorously correct, this power counting. It's not a true effective field theory in this thing, but it works well. And so people have applied it to great use and great profit in nuclear structure theory in the past 20 years. As we heard yesterday, when you do the same thing for this VPT, you also get some operators like this at each order of chiral EFT. They depend, their content depends on the source of CP violation, which you already talked about, and also Vincenzo. But for any given source, you can write down at any order in chiral EFT the operator you want for VPT also. Now, on top of this, you need a method which allows you to approximately solve the full Schrodinger equation for, in our case, 225 particles or something like that. So that has been a challenge, but in recent years, people have made progress on that. So the ab initio means start with as rigorous as you can in 2-body interaction, 3-body nucleon-nucleon interaction, and then try to solve the full many-body Schrodinger equation as accurately as you can, and in a way that you can quantify the error. So you don't have to do any other fitting. You don't have to do any fitting in heavy nuclei, and you can see where all your error comes from. That's the goal. So how do these methods work, these ab initio methods? So there are several varieties of them, but they're all based on a similar idea, which is that you want to find a unitary transformation or some kind of transformation, which takes this Hamiltonian in a huge space, the Hilbert space for 225 particles, say, and reduces it to an effective Hamiltonian in a much smaller space. So you want to find a unitary transformation that turns this kind of Hamiltonian into one like this, which is block diagonal. Then you just throw away all this, and since we're concerned only about the low-lying states, which are in this much smaller space here, we can neglect all this stuff, and if this calculation is done well, we can use the effective Hamiltonian here to do a much simpler calculation in a small model space. And then you have to apply the transformation of the Hamiltonian to any other operator you want to use, like VPT and the Schiff operator. In principle, this is as difficult as solving the original problem. If you find this transformation exactly, you're effectively solving the problem you want exactly, which we know is very hard, but the approximations come in neglecting certain kinds of operators. So when you do this transformation, if you start with a two-body Hamiltonian, you generate a two-body effective Hamiltonian in this small space, say a shell model space. But you also generate three-body pieces and four-body pieces because the transformation is very complicated in general. But these things, these higher body pieces, 3 and 4 body pieces, are less and less important, and you can discard them at some level, making only manageable size errors, and you can quantify the size of the errors that you're making when you do that. So how do you do this transformation? There's a variety of ways, but the one I'm going to talk about here, and also we'll hear about later on from Jason Holt probably, is something called the in-medium similarity renormalization group. So the idea here is it's a set of flow equations which gradually, step by step, decouple these low-lying states that you're interested in from the rest. And I'm not going to describe these flow equations, but the virtue of the flow equations thing is that you make a very small unitary transformation, sort of see what it's done, correct it, make another very small one, and along each step of the way, the differential equations tell you how to optimize the next infinitesimal transformation, and you end up, if you've done it perfectly, with a decoupled small space here. And then you diagonalize the effective Hamiltonian in the small space, like I said. And this is just showing you how well this works for spectra. Here are some experimental spectra. Here are some of these ab initio methods. I'm not going to tell you what all these letters means. Here's a phenomenological Hamiltonian, which people have traditionally used in the shell model, where all the Hamiltonians fit to similar levels and nearby nuclei. And you can see that this ab initio stuff, where the only fitting comes from the original interaction in 2 and 3 nucleon systems, gives you results that are all effectively as good as this shell model interaction that fits in nearby isotopes. And this is true over a range of nuclei. Okay, I'm running a little short of time. So I'm just going to very briefly tell you about how we want to apply this idea to radium-225. Radium-225 has a property that it's very deformed, it's octuple deformed. And these correlations are complicated many-body correlations that if we truncate these IMSRG flow equations, we might throw away. So the idea is to build them into the low-lying reference state that we use as to represent our small space to begin with, for which we want to then use the flow equations to compute the effective interaction in. So we construct the octuple deformed state as the small space to begin with. And we do all this dynamics of intrinsic parity violation and symmetry restoration, octuple physics ahead of time, and then do the flow equations on top of that. And the method we use for doing the collective physics is called this generator coordinate method, where we mix a bunch of different mean fields. I'm going to skip showing you the details of that, which I did here. This is, okay, I will just skip this. And we construct a reference state. Our small space, which we want to do the calculation within, is going to be based on these octuple deformed states. And then the IMSRG flow equations will include the physics which that octuple deformation doesn't include, the physics from non-collective particle hole excitations, things which high-lying stuff, which the flow equations are good at including, and the octuple physics we include by hand in a way that we've already done in density functional theory. So this would work in for the shift moment, and I've already done this for double beta decay. We've already done this. For the shift moment, the procedure would be like this. We take the bare chiral interaction and we do a GCM calculation, which is like a mean field calculation with some mixing of mean fields. And then we can construct an ensemble of two states, the ground state and the parity doublet partner. These are the two we're interested in. And then when we do the flow equations, we construct them so that you create an optimal Hamiltonian for these two states. We construct the flow equation so it minimizes the value of this transformed Hamiltonian in the ensemble of these two states. And then we apply this, that gives us our unitary transformation, which gives us an effective Hamiltonian, which should include all the physics we've left out of these two states, so it should stick it in there, in this two-state ensemble. And then we apply the same transformation to VPT and the shift operator to get the transformed operators for them. And then we do our calculation within these small states. And because neither one of these states in itself is an eigenstate of H bar, because we were using an ensemble to represent our reference state space rather than one state, we have to do another GCM calculation with this H bar. So we calculate these states again, now with our transformed Hamiltonian. And then we compute the shift moment with these new effective operators, VPT and S. So this is probably a little more detailed than I had time to fully justify in this talk, but that's the idea. The idea is to do the octuple physics in the way we're familiar with a bare Hamiltonian, then evolve the Hamiltonian so that it gives good, so that it incorporates the rest of the physics that we've neglected into these octuple states. We've already done this for the double beta decay of calcium-48 to titanium-48. Now we're doing it for the decay of germanium-76. And I'm out of time, so I will not show you the results for the double beta decay, but they're good. This I will just show you. This is titanium-48, and you can see here that in the shell model, when you do titanium-48, you find that these collective E2 transitions are not well represented. But because here we've built our reference state before doing the IMSRG to have collective properties, we get these E2s pretty well. And then the IMSRG just corrects things. So radium-225 is a lot bigger than the nuclei we've done this with so far. So we're going to require some improvements in the method. It'll require larger spaces and more memory, basically more sophisticated computer use than we're doing now. And it will require that these chiral interactions need to be really verified in these kinds of heavy nuclei where they haven't been looked at extensively. But that's about it, I think. And the question is, the last question I have is, when we're all done with this, which hopefully won't take too long if I can get my collaborators to work on it, is how much smaller will the uncertainty be? And that I don't really know yet, because like I said, this chiral EFT is not perfect. People do make their own different kinds of chiral interactions by fitting in different ways, and results give slightly different result answers when you do the calculations of the different chiral interactions. So there will still be some uncertainty. I don't know how large it will be, but I can say that we should have much more reliable error bars, and there'll be much more physics included in here. So I think whatever the error bars end up being, they'll be a lot more believable. And that's all. Thanks for listening. I hope we can have results for you at some point in the next couple of years.
Okay, thank you very much, John, for an excellent talk. I immediately see a question from Makoto.
Hi. I just want to ask, in the beginning, you said that chiral effective field theory is not rigorously correct as effective field theory. Can you describe that a little bit more detail?
Well, I'm not an expert on this, but my understanding is that it's rigorously correct in perturbation theory. So if you start counting diagrams, you can say, oh, okay, here's a higher order diagram. If I add this perturbatively to a wave function, then I can see that it's going to, if the coefficients are of reasonable size, it's going to give a correction of such and such a size. But when you do a non-perturbative calculation, like we do in nuclear structure physics, where you you're not diagonalizing your Hamiltonian in perturbation theory order by order. You put in the whole Hamiltonian and then diagonalize it. Then that can confuse the power counting. And you really have to verify explicitly that it still holds. And there seem to be some channels where in certain partial waves where it doesn't rigorously hold in non-perturbative calculations. And if I'm misrepresenting this, anybody who's an expert should correct me, but that's how I think it works. However, in applications, it's worked remarkably well.
So how do you quantify this non-perturbative part of the non-rigorous uncertainty in this non-rigorousness?
So that is the whole in what I was saying. So what we can definitely quantify is the error in the many-body methods, where we can go to sort of the next order in approximating them and see what the correction is. But the non-perturbative the corrections to the fact that chiral EFT is not a rigorous, the power counting does not rigorously hold in non-perturbative calculations is not so obvious. And all we can do is, so that is, you sort of zeroed in on the weakness of this approach. That in the end, we'll just end up doing calculations with different chiral effective Hamiltonians like we're doing now, and hope that the range is going to be a lot smaller than it is for different functionals. I don't know of a way of quantifying that particular source of error, but that is the only source of error that you can't quantify. So I wish you hadn't asked that question, but thanks for asking.
Thank you.
JD.
Hi, John, it's JD. Thanks for a wonderful talk and all your great work. I just want to make sure I understood this implication of this last thing you talked about in terms of doing a new calculation for radium-225. Am I correct in understanding that you want that the result of the calculation will be a way to connect the shift moment to these G0 and G1 parameters? Is that correct?
Yeah, the same kind of calculation that you've done with the OTSEC.
Okay, got it. Very cool. Thank you. This is great.
Okay, thank you. Robert.
Yes, I'm an experimentalist, and so I would like to make a measurement on radium fluoride. Would it be better to, well, what would I see in the hyperfine structure of either the ground state of radium fluoride or the ground state of the radium fluoride singly charged ion? Is that something that could be done with modern experiments?
Okay, so I'm unable to answer that question. That's outside my range of knowledge, but I don't know. I mean, people have talked about doing experiments in ions in molecules with radium as one of the constituents. I don't know about radium fluoride. Has anybody else thought about that?
I think a few people have thought about it. Robert Berger, do you want to comment?
So what one would specifically see in the type of measurement, right? So there would be in principle a contribution to the electric dipole moment measurements of the radium fluoride molecule, which one then can disentangle and see what the different sources to this electric dipole moments are. So if you follow the branch which we have seen in Michael Ramsey-Musoev's talk, that one has to connect, so to speak, the measurement, which gives the dipole moment, to the different sources which we can have in our molecular system.
But measuring the hyperfine structure is a different sort of thing than measuring the electric dipole moment of the molecule.
Once again, please.
Well, in high resolution spectroscopy, one could conceivably measure the hyperfine structure. So each rotational level is split into a bunch of hyperfine levels. That's something which is a fairly standard thing in high resolution spectroscopy, but it's difficult to do this on a radioactive molecule. And so is it worth trying? Measuring the dipole moment is something that's much easier, but I don't think the precision one could measure the molecular dipole moment with would be of any relevance.
I think it might be easier just to leave that for a breakout room, just to move
But
on
I
to.
have a comment. Yes, definitely. Yeah. Okay.
Yeah. Okay. So Jordi, you had a question.
Yeah, thanks, John. I was wondering, do you think it's a problem that the double beta decay calculations involve somewhat smaller isotopes? I mean, they're still big, but you're talking about germanium-76, and going to radium or mercury is really a big stretch. Is there any effort on pushing these ab initio all the way up to those nuclei?
Yeah, I mean, I should say that germanium-76 is harder in some ways than this will be. Probably not harder all told, but germanium-76 has is what we call a triaxial nucleus. So it's not only, it's deformed along more than one way. And so that requires a more detailed reference wave function to build in the collective physics there than this one will, where this has a octopole deformation, but it's only axial deformation. If you rotate around the axis of symmetry, there is an axis of symmetry, in other words. And that will allow us to simplify this reference wave function. Yes, I mean, the 225 particles is something that no one's done yet, I don't think, although people have pushed this stuff up to lead 208 in some preliminary calculation. So it will require some developments in storage and basically storage will be the main issue. But I think that, unlike some of these ab initio methods like coupled clusters, which have really leveraged the best supercomputers, these methods so far, the similarity renormalization group methods haven't. So they can be pushed considerably further, I think. So although it will be work, it won't be impossible.
Okay, cool, thanks.
Finally, John Bear, you had a comment in the chat. Did you want to expand on that?
It's really more to try to get Wick to come to a breakout with John. So I think it's really neat that you'd like to try to benchmark or measure related observables to get something about VPT and that sigma that operator you showed, the one body version of the operator. Okay, so you're asking, I think, for first forbidden beta decay and separating the operators for that guy, but that's only loosely related, probably. And I was just wondering, I think I've asked you this before, if we did weak NN, if you did the gamma ray asymmetry of one of the gamma ray transition between the two, the doublet, which would be something, but not impossible in one of the cases. Is that any more helpful? That's a nightmare to calculate as well, but.
Well, I think when I talked to you before, I talked to you before, I said, no, that's the wrong operator. You concluded it was the wrong operator. But now I don't care. I mean, I think I'm getting more desperate, and any related operator I think would be useful. So yeah,
I saw that. That's good. Okay, can we talk at the breakout? Thank you. That could be fun. Thank you.
Thank you, John. And thank you, John, again for an excellent talk. So I think we can move on to our final speaker of this session, which is Peter Butler.
Okay, do you see anything?
I see you, but I don't see your slides. So you should.
Okay, what's happened here? I'm trying to share the screen. Oh, there we go. Okay, right, desktop. Click one more button. Is that fine? Are we getting there?
It's
nearly there. Hang on. How's that?
Yeah, I think you're in the middle of the talk.
Yeah, okay. A quick preview of the talk. Right, okay. Well, first of all, let me first thank Ronald and the local organizing committee for giving me the opportunity to present these data. I am actually an experimental nuclear physicist, and what I'll be talking about are the measurements we've made at Isolde on heavy nuclei with octobole deformation or octobole vibrations, as we shall see. And I'll start really with a brief history of the topic and try to put it in the context of EDM measurements, of which we've heard quite a lot so far. And so I will discuss rotations of radon nuclei to see whether we think they are octopole vibrational or whether they have permanent octopole deformation, and then move on to the study of E3 moments in radon and radium, and then look at future prospects. Okay, so so just to say a few words about EDMs from an experimental viewpoint, at least from my viewpoint. So I do apologize if I've missed any important references out here, but I think just to say, from at least historically, this whole thing probably kicked off in 1977 with a paper by Feinberg, who pointed out the enhancement in the EDMs arising from the energy difference between the ground state and other states in the denominator, which of course, if that becomes small, then the quantity becomes larger. And he, in fact, referred to the possibility of rare earths. This is actually published in the Transactions of the New York Academy of Sciences, which is a rather obscure journal, but you can still obtain the article. Okay, then in 1983, Haxton and Henley pointed out that there would be a large enhancement of the atomic electric dipole moment due to any CP violation in the nucleus, arising from, again, from parity doublets, but this time looking specifically in actinides, where there may well be expected to be a very small energy spacing of parity doublets. And in fact, their paper seems like it was inspired by protactinium 229, where at the time it was conjectured that there was a splitting of the parity doublet at the ground state of around 200 EV, as we've heard already, except of course that now that is cast into doubt. But never mind, that paper was published, and then well, a little bit more than 10 years later, Auerbach, Flaumbaum, and Spivak wrote their paper where they now included the effects of the collective octopole moment and showed that that is equally important, perhaps more, in providing an enhancement of the EDM. And there's a number of papers there published by that group or by Victor himself. Then in 2000, Engel, Fry, and Hayes pointed out that there would be a large enhancement also for octopole vibrational nuclei. And that, of course, is important because, as was pointed out, that the programs to look at EDMs are not just in the odd mass radium nuclei, but also in the odd mass radon nuclei. But I shall discuss a little later on, as I said, what we think is the experimental situation there. 2003, Jacek, John, and others now applied a good microscopic method using skerm, Hartree, Fock to radium-225, and that's now getting to the state of the art. I should also mention the 2011 paper by John Ellis and his collaborators. As you probably know, I mean, John is one of the leading theoreticians in SUSY, and so he's a particle physicist who is also interested in this particular topic. And this paper actually calculates what the maximum values of the radium EDM would be allowed by a minimal version of the SUSY theory. Okay, now, as we've seen, I mean, this is using formalism actually, which I think is in the 2000 paper by John Engel. The shift moment is related to these two terms in the numerator and the energy splitting in the denominator. And the term which gives rise to the enhancement in the numerator is that which is proportional to the, as he pointed out, to the octopole deformation body, and then to the electric octopole quadrupole moment. And what experimentally we've been trying to do for various reasons, to look for that information on this term, i.e. dielectric octopole moment, and also on this term to see what there is experimentally. Okay, so, well, where do we expect pair shapes, octopole deformation? Well, the usual statement is to say that this occurs when the nucleons, either protons or neutrons, are have interactions between single particle orbitals, which differ by orbital angular momentum and total angular momentum of 3 units of h-bar. And also this happens near the Fermi surface. And this will happen for various values of proton and neutron number given by these on the side here. And if you look on the periodic table, then you might expect that where this effect occurs, or where these correlations are largest for both protons and neutrons, then you would have strong octopole effects and the possibility of static pair shapes, such as this region here, which has been in the light rare earths, and this region here in the light actinides. And I will focus on these actinide regions here. Okay, so if a simple sort of experimentalist naive picture of what's going on is that, well, we could have two possible phenomena we might see. If there was just instability in the octopole deformation, then we would have vibrations. And this, in order to see a signature of that, then one might expect that if we look at the difference in angular momentum of the negative and positive parity states at the same rotational frequency, then this difference would be about 3 h-bar if it simply arises from an aligned octopole phonon. Whereas if we have a static octopole deformation, we have a true rotating pair shape, then this difference would be essentially 0. And so what we have to do then is actually have a look at what that happens in nuclei. Now, again, coming back to history of the experimental measurements in the actinides, parity doublets and E3 moments, I mean, in some ways, the whole thing started by the observation of Frank Stevens and his collaborators of low-lying 1- states in radium-222 and 224. And in fact, his paper of 1955 was the first one, I think, that mentions the possibility of pear-shaped nuclei based on a suggestion by Robert Christie. Now, as far as parity doublets are concerned, well, I mean, this is a quickly put together history, so it could be a little wrong. I could have missed out some important reference here. But one very early observation of the 3/2 minus 3/2 plus doublet in actinium-227 was made, in fact, by a Brazilian group working at Orsay. And in that paper, they mentioned the possibility of octopole vibrations, and that was done in 1970. But things really got more pronounced interest, I would say, to various experimental groups when Dick Chasman at Argonne made firm predictions about the parity doublets and also large connecting E3s between them, which was published in 1980. Then Ray Schielein and Georg Leander did a lot of interpretation of these odd mass nuclei, published in 1983 the interpretation of actinium-227 as a parity doublet. And then I should mention Ray Schielein's measurement of the, I suppose the interesting one for EDM's concern, the 55 keV parity doublet in radium-225. Now for E3 moments in the actinides, in fact, the first measurement made of a BE3 in what we now think are octopole nuclei was actually made by a Norwegian group from the University of Bergen, working at the Niels Bohr Institute using the spectrometer there, where they, from DD prime scattering measurements, they measured the large enhancement of the E3 moment in radium-226. And in fact, this group here was the same one who also worked on the radium-225, just a matter of interest. Then in 1996, I mean, I got Hans-Jürgen Wollersheim and his collaborators got involved in that also, measured E3 moments more, or up an additional E3 moments in radium-226. And I said the disparity of years there, it should be 93, I think. That in that particular set of measurements, that they also carried out determination of E3 matrix elements between many other states in the nucleus. And as I'll show later, it looks like from all those measurements, it seems like it is really a rigid octoball shape. And then came with Wollersheim, took advantage of the fact that one can obtain a target, radium-226, which is 1600 years half-life, and therefore it's not too radioactive and can be put in bombarded with an accelerated stable beam. But in order to progress on this, relied on the development of accelerated radioactive beams. And we carried out measurements of E3 moments in radon-220 and radium-224 20 years later. And I'll show what I want to do now in this particular, the rest of the talk, just show what we've done since then. So the data I present is essentially from one experiment carried out 3 years ago now, not completely analyzed, I should say, fully analyzed, but some of it has been published. So this is the only experimental spectra I will show. And all it essentially indicates are gamma ray spectra using the Miniball gamma ray detector array with accelerated radioactive ion beams from the High Solder facility at CERN. And what one sees is that the progression of E2 transitions between the positive parity states, and then there are, in addition, transitions between the negative parity states. So this is actually for radon-226 beam, radium-224, radon-222, and then down here we've got radium-222 on 2 different targets and radium-228 on 2 different targets. And certainly one can see plenty of evidence for the excitation of the negative parity states. And from that, from the Coulomb excitation analysis, which I won't go into the details of, we can determine what the E3 matrix elements are. But the other thing we can do is, in fact, we can determine, because radon, there's nothing known up to these experiments about radon-224 and 226, we can measure the level schemes of these heavier radon isotopes. The radon-222 was actually measured 25 years ago using stable xenon beams on a thorium-232 target and a method of multinucleon transfer. Okay, so this is what we obtain for the level schemes of the radon-224 and 226, which is published in Nature Communications. And what's, I think, interesting is that if we carry out this plot of this delta IX, that is the difference in angular momentum, as I said, between the negative and positive parity states as a function of rotational frequency, what you can see is that from the behavior of this quantity for the radon isotopes in particular, that they all pretty well lie about 3H bar. And we interpret the radon isotopes as being octopole vibrational. Whereas if one does the same sort of analysis for the isotopes of radium, thorium, and uranium, some of these show good indication to be have a rigid pear shape. And I think probably, I mean, if I get rid of these blocks again, I mean, one can just see, for example, at n equals 134, that there's quite a big difference between the behavior of radon and the isotone radium, thorium, and uranium. Well, the interpretation then is that we, as I said, we think that radons are octopole vibrational, but there are isotopes of radium which are permanent octopole deformation. The other piece of information we can look at now is the matrix elements. This is a bit of a complicated picture, but what it is I've taken the matrix elements for the E3 matrix elements between states, different spin, parity, and then calculated what the effective intrinsic octopole moment is using the rotational model. And if these nuclei were, for example, we believe them to be a rotation of a rigid octopole shape, then one would expect that this Q3 value to be the same independent of what sort of transition we have. I mean, whether it's I to I plus 1 minus, or I minus to I plus 3 plus, and so on and so forth. The one, of course, one has the best data on is the ones like spin 0 plus to 3 minus, which is these guys here. But this now is 2 plus to 5 minus, and then these are 4 plus to 7 minus. So we've got quite a lot of data on these different matrix elements. And what it seems to indicate, if we take, say, radium 222, the blue squares, then these are all roughly rotational like. Whereas, for example, if we take radium 228, there's some matrix elements which are not rotational like. So we think that, for example, radium 228 is octopole vibrational, whereas radium 222 and radium 226, in fact, are pear-shaped, rigid pear-shaped. Okay, so if we just take the lowest matrix, the 0 plus to 3 minus matrix element, and compute the electric octopole moment, and look at that in a systematic way for all the heavy mass nuclei from lead-208 up to uranium-234. This is plotted here. So on the right-hand side is the electric octopole moment, and on the left-hand side in blue are the quadrupole moments. Well, of course, the quadrupole moments, as you might expect, slowly increase with mass as you go towards the mid-shells. The system gets more and more deformed. But for the octopole moment, there does seem to be an enhancement around here, around radium-224, which we, as I say, which we interpret as the onset of a rigid octopole shape. It's always amusing for experimentalists to compare with theory. I don't have a plot of the comparison with the quadrupole moments, but it's rather dull because theories are very good at reproducing the behavior of the electric quadrupole moment. It's not quite the same for the electric octopole moment. There's actually many calculations for radium isotopes. There's not so many for both radium and radon. So this picture confines the theoretical calculations to those where they have calculated the radon isotopes. So the calculations for the radons are the red dotted lines. The calculations for the radiums are the blue dotted lines. And you can see there's quite a bit of difference actually between the different theories. And it's not such very good agreement in particular for the experimental values either. I mean, for example, some theoretical calculations predict a maximum, which, well, in fact, is at n equals 140, whereas others predict one maximum around n equals 134, 136. So there is some way to go there, I think, before we properly understand this behavior. Okay, now, okay, in John Engel's talk, actually referred briefly to measurements that will be done on radium-225 at Argonne. I actually carried out a simulation as to what you might expect in the gamma ray spectrum if you try to Coulomb excite radium-225. So this is the lowest part of the level scheme. So you can simply put all these levels into your electromagnetic calculations, which is, in fact, in this case, is a code called Gaussian, which we use to analyze the radium-222 and 228 and 224 nuclei. What one can see is that indeed, I mean, you do have sensitivity to or some transitions in the spectrum. The simulated gamma ray spectrum do have sensitivity to the E3 excitations, and if you're able to measure these at rather low energy, you'll be able to determine some information about these matrix elements. The only problem is here we are. The only problem is that the level scheme is actually a lot more complicated than this. And what you'll see in your Coulomb excitation is excitation to all these states up here and many more besides. I mean, all the low-lying collective band, other types of collective bands, quasi-beta bands and gamma bands will also be excited with feed down. And it would be very complicated to carry out this sort of analysis. So I think that still is going to be an experimental challenge. What about heavier Z nuclei in this region? Because, I mean, for example, there's a lot of interest in protactinium-229, so it would be nice to have information about the E3s in uranium-228. And in fact, this is a plot of the calculated values of the BE3 from the ground state to the 3- state in single particle units as a function of mass for various isotopes. So the ones we were measuring were down here, radon and radium. And this particular theory produced this plot by Lewis Robledo and George Birch, is calculating these values which aren't so far from experiment, but they also calculate values for thorium and uranium, and one can see that the expected BE3s are much, much larger. And that would be very nice, in fact, to determine what these quantities are. It would be a much better signature, I think, of the fact that we would have the onset of stable octoball deformation if one was to see a massive increase in the BE3. This is not so far in the future, as we know that the FRIB is expected to come online not too distant future. According to their website, the reaccelerated intensity of uranium-228 from FRIB for the first period of operation is expected to be about 3 × 10⁵ per second, although I think actually there was a talk on actinide beams expected from FRIB later on, today or tomorrow perhaps. And we have submitted a letter of intent to the FRIB PAC. We did that in February. The PAC meets in August, so we'll see what happens. But our plan is, in fact, to accelerate isotopes of thorium-224, 226, 228, and 226, 228, 230 uranium to measure BE3s. Okay, my talk is nearly finished, so let me just come to the summary. Okay, so I'll write down the expression for the shift moment again. And just to summarize what we've done, we've measured this quantity in radon 220, 220, and 222. At least we've measured the electric octopole moment related to this, the shift moment term, and also in radium 222, 226, and 228. But there's no measurement so far in odd mass nuclei. We've also measured, or not we, but has been measured, the energy splitting in radium 223, 225, which is around 50 keV as known. We think because the radons are octopole vibrational like, in contrast to the radiums, that this delta E splitting would be significantly larger in radon than what it is in radium. So it may not be such a good case to look at, but nevertheless, there's other considerations, of course, in carrying out these measurements. It will be challenging to measure the E3 moments in odd A nuclei, but anyway, we can try. But there may well be better cases in nuclei heavier than, said, 88. And then finally, just say that the results I presented here come from a fairly large collaboration, which is given by these 20 institutions here. Okay, thank you very much.
Thank you, Peter. Thank you for an excellent talk. Do you have questions from the audience, Peter? Maybe I can start. So which of the radium isotopes would you feel would be then the most sensitive based on this?
Uranium isotopes?
No, radium.
Radium isotopes. Well, from what we can see, I mean, there's the two factors, of course, the large E3 moment, which we see in the even radium isotopes 222 to 226, and the the known parity splitting is known in those odd mass cases. So I think radium-225, at least, which happens to be the one which, of course, is the EDM specialists are concentrating on, is almost certainly the best choice to look at as far as that radium isotopes are concerned. Now, whether there's better ones to look at, that remains to be seen, I think, because we just don't have sufficient information. We don't know what the parity splitting is really in the odd mass radon isotopes, and has been an experiment carried out at GSI fairly recently, where there may be some information on that to be seen. And also, as I mentioned right at the end, it's possible that we can look at the heavier systems. And if, I mean, there will be, I think, a talk on protactinium-229 later on. If it turns out, and we've heard about it being discussed as a focus of possible measurements yesterday, if it turns out there is a parity doublet with a very low small energy spacing in that nucleus and that isotope, then almost certainly that would be an excellent possibility to study, I would say, particularly if you can obtain large quantities of it from EFRIB.
Okay, thank you, Peter. John Bear?
Does that, I think Victor also mentioned the octopole vibration enhancement of something like an order of magnitude. Does that happen for all the ground states in this region, or does anything have to be special at all about the ground state? Do you know?
Can you? Yeah, I didn't quite understand the question. You said you were asking about the octopole vibration and
enhancement that you mentioned. Engel and Hayes and Fryer had come up with in 2000 or so. Does that work for all the ground states in this region?
Well, John can probably answer that better than that because he's the first author of the paper. Do you want to comment?
Well, it only depends on how strong that vibration is. So what it depends on is the E3 matrix element from the ground state to the vibrational state. And the larger that is, the more the enhancement will be. So you know, in general, when a vibration gets higher in energy and it gets weaker, and there'll be less enhancement, but as it comes down in energy, the matrix element goes up, the E3 operator goes up, and it's even larger in general when it comes down so low that deformation sets in. But so that it really depends on the details.
Yeah, well, it's the details we don't know, of course, but all we do know is that at least the E3 moment is almost, I mean, it's not so dissimilar, I mean, at least for EDM measurements to that in radium. But the energy splitting could be quite different. I mean, that could be maybe a factor of 10 or different between radons and radiums. And I don't know what effect that would have on the enhancement. Whether it's just a factor of 10, I'm not sure. You could probably answer that, John.
Yeah, I don't know exactly what it is, but right, that's the other factor is the energy denominator. So, you know, that the shift moment is linearly proportional to that, or inversely proportional.
Yeah.
JD?
Hi, Peter. Shady, thank you for a very nice talk. And I was particularly interested in the history as well. Can you comment? You mentioned it a little bit, but I was wondering if you could comment more about the implications of the experiment that you have a letter of intent for at EFRIB, the implications of that for the octopole deformed nature of protactinium-229.
Okay, well, oops, just go to this picture actually. Yeah, well, the calculations, as I said, strongly suggest that the octopole deformation is the beta 3, for example, is larger in this region of the periodic table for around uranium-228 or so. That is borne out by the very large BE3, which is calculated. And I should say it's not just Robledo and Birch's calculations, but also there's some quadrupole octopole collective Hamiltonian calculations carried out recently, which also predict very large electric octopole moments in this particular mass region here. And I think what this is saying is that if you at uranium-228, you would have a large collective octopole contribution to the shift moment, and there's no reason to believe that protactinium-229 is going to be any different. It's going to be very difficult to measure protactinium-229, but what the next step, of course, is what is the energy splitting of the parity doublet in protactinium-229, and that we have to find out. I mean, as you know, I mean, Ershad Ahmed's carried out a recent, or 6 years ago, I think it was, measurements of this system, and came to the conclusion that the first conjecture that there was a low-lying parity doublet is not so secure, but nevertheless it could still be there, and that's something that we have to find out. But I think, yeah, I mean, if there really is if it really is of the order of a few hundred EV or something like that, then it would be an excellent case to study.
Okay, thank you.
Thank you. Jacek?
Yes, Peter, thank you very much. Excellent talk. I would like to raise a question about this parity doublet, because somehow we all assume that the lowest negative parity state is a partner of the ground state, which doesn't have to be the case. Because, for instance, the octopole deformation is certainly different from the positive, for the positive parity and negative parity partner. I mean, at least from the calculations, it's obvious it must be the case. So do we have any experimental way to decide the exactness of the parity doublets in experiment? In theory, we can evaluate this mismatch between the positive parity and negative parity state, but would it be possible to have an experimental probe which would tell us how exactly these are really doublets?
Okay, well, as far as I know, there's only two probes. One is the E1 transition strength, and the other, the better one would be the E3, to see a high collective E3 transition probability between the two different parity states. And in fact, that was suggested by Chasman in his 1980 paper, that we should see that effect. And that's the only surefire proof, I think. And the E1's a little bit unreliable, of course, but nevertheless, I think you would expect probably to see this sort of enhanced E1s, well, which have been measured for these systems anyway, which, I mean, that the enhancement of the E1s is part of the basis of the sort of Scheelein Leander systematics, and also, of course, things like the behavior of the magnetic moments, and so on and so forth. Decoupling parameter being of opposite sign and so on. That they've laid down all the characteristics experimental characteristics you would expect for a pure parity doublet. But I think the long-term goal would be to measure the E3 transition strength between the opposite parities directly. And well, I don't know. We could try it. I mean, it's one of these things where it's easy enough to do the experiment and obtain spectra and yields, but then come back a few years later for the results of the analysis. But it's something I think we have to look at.
Thank you. Mariana, last question.
Hi, I just wanted to make sure I understand how the E3 moments are measured. So is the only way is to measure the E3 transitions?
You measure, no,
yeah,
no, sorry. Well, the simple idea is here that you, that in Coulomb excitation, the E3 excitation up is quite strong, actually. It's probably of the order of, it can be up to 10%, a few percent anyway, of the E2 probability of operating the state. And of course, as you know, when you look at the decay, they're going to be dominated by E1s. So that's the basic idea. It's a little bit more complicated than that because the method using this computer code Gosha, which was developed initially at the University of Rochester by Doug Klein and Tom Etchersnicker and collaborators, is to simply treat all the matrix elements in your electromagnetic calculation of the population of the states as free parameters, and hope that you have enough experimental data that exceeds the number of free parameters. And well, in these blocks I've written down, as you can see, there's, for example, radium-222, we had nearly twice as many data as variables, and similarly for radium-228, and then you do the fit. And you have to apply some constraints. Sometimes you put in a little bit of model dependence, but in the end, you do get out mostly model independent matrix element determinations. Yeah.
And then, is it possible to do that in thorium-229? And there's also I have a general question about the E3 moment. There is now a project to try to extract sensitivity to the alpha variation, which essentially will be the difference in Coulomb energy between ground state and isomer for thorium-229. Yeah. And the question is, would actually E3 contribute to that or not?
Well, if you, of course, when you populate an isomer, the matrix elements by definition must be very different. So the states, the compositions of states are going to be quite different unless it's just due to the energy difference. If the composition of states is very similar, then you would expect to see, and the energy is very, very small, the transition energy is very small, then you would see a massive population of the isomeric state, which I guess is the case, isn't it, in thorium-229. So yeah, I mean, there is a general problem, as I mentioned, for odd mass nuclei, that there's this picture here is complicated enough already for an even nucleus, but when you've got an odd mass system, you may have 2 or 3 times as many states, or maybe more, which are populated, and then you do run into the problem of having number of variables being greater than the number of data. But yeah, no, I mean, for the case of thorium-229, I think those 2 states are, probably do have a similar structure, although they wouldn't be so close to each other. And if they are, then the Culex, if they're opposite parity, if they're not, then you'll have a large E2 excitation. But you will have to look at the details of the structure.
And there is no way to get E3 information from any atomic properties because it will not affect the hyperfines, right?
Yeah, I don't think so. No, I can't see how you can do it from atomic hyperfine splitting.
Thank you.
Okay. Thank you. I think I'd like to thank all of the speakers from this session, and just say thank you for excellent talks and keeping to time. We're slightly over, but it was a good question session at the end there. We have a 15-minute break for coffee, and then we'll reconvene in 15 minutes.
I think we'll make it 10 minutes. Yeah, to go back on time. Yeah.
Are we supposed to go into breakout rooms, these speakers?
That we want to move into, Robert?
Yeah. So yeah, Eric,
please.
Can you please open some breakout rooms, and then we can, if the speakers can join the different breakout rooms, so we can ask more questions during the coffee break.
Should be all
Good.
set.
Yeah. Thank you, Nick.
Thank you very much.
Okay, I'll go into 3.
Hi, Nick.
Yes.
Nick, can we bring all back? I think we are already 3 minutes late.
Okay, sure.
Yeah, interesting discussions. Yeah, thank you, Nick. Okay, we'll give a few, less than a minute, that all participants come back.
Okay, I guess I can start, Ronald?
Yes, please, Gerda. Yeah, I
Yes,
think we are
okay.
all back.
Okay, hello, good afternoon, everybody. So let's continue with another very interesting afternoon session. So now we have a talk by Vitek Nazarevich, who's going to talk about nuclear charge densities and in spherical and deformed nuclei.
Hello, good afternoon and good morning. So let me. Okay, can you see my screen?
Yes, yeah.
Everything is okay. So thank you very much for inviting me to this very interesting program. Thanks to several talks this morning, I think that some background to the material which I'm going to show has been laid. I'm going to discuss the nuclear charge densities and how from those charge densities we can extract important data which are of interest to the community attending this workshop. So I will give a very brief introduction to the nuclear DFT, and Jacek and John already defined some keywords here. Then we'll talk about reflection asymmetric nuclei. So what do modern DFT calculations tell us about like systems? And then we'll have a comment on nuclear charge densities and charge radii. And I will finish with a very interesting recent topic pertaining to this parity violating asymmetry measured in lead 208 by PRX2 experiment. Okay, so this will be interesting coupling between nuclear physics, nuclear theory, and electroweak physics. Okay, so this is one slide on the DFT. Jacek Dobaszewski and John Engel were talking a lot about it. Okay, so there are various strategies of how to arrive at quantified energy density functional, which is a basic input to calculations. One can start from ab initio nucleon three-body interactions, and through the technique known as density matrix expansion, one can derive the form of the functional. One can start from density-dependent interactions, or one can just postulate energy density functional, as in Jacek's talk. Then the form of the functional, this functional contains a number of low energy coupling constants, and those have to be determined by confrontation with experiment. So here we have fit observable, we have experimental data like binding energies, the charge radii, and other important quantities. We can also use some pseudo data which were obtained by ab initio calculations, more fundamental calculations. So at this point, we have to calibrate the functional, optimize it using usually heterogeneous data sets. And this will give us a quantified EDF. If we do calibration properly, for instance, using Bayesian approaches, through this calibration, we get covariances, which will later be used to estimate error bars of calculated quantities. So error bar estimation is very important here. So then we use variational principle, which gives us Hartree-Fock, Bogoliubov-Dejean equations. Okay, we are dealing with self-consistent problem. Symmetries, laboratory symmetries are often spontaneously broken in those solutions. And then we can either use this approach with broken symmetries and compute observables, or we can also restore symmetries by going to multi-reference density functional theory through GCM, which was explained by John. We can also do time-dependent density functional theory, time-dependent HFB, and we can compute observables. And then we have next confrontation with experiment, and we can go back to this point and iterate, okay, in the cycle of the scientific method. Okay, so a few more general points about DFT. So there is a big difference between nuclear DFT and electronic DFT. First of all, in nuclear physics, we deal with two Fermi liquids. We have protons and neutrons. The nuclear system is self-bound. There is no external potential, which keeps everything together. And we also have superfluidity. That is, pairing correlations are important at low energies. So we are dealing with superfluid systems, okay? So in the simplest version of nuclear DFT, one deals with one body local densities, finite range effects are simulated by gradient terms, okay? And we deal with particle hole and pairing channels because of superconductivity. So the energy density functional, as I stated in the previous slide, does not have to be related to a force, can be just postulated. And we know that if we have the if we have a good functional, there exists a functional in principle which should give us true answers. But by making calculations, confronting with the data, improving the functional continuously, we can arrive at something which is realistic and provide spectroscopic, make spectroscopic predictions. Okay, so a few technical details. Okay, so the functional has kinetic part, has a particle hole part, and it has pairing part. So this is the part which is responsible for pairing. Usually we deal with isoscalar densities, which are symmetric proton and neutron, which are symmetric in proton and neutron, and isovector densities, which reflect the motion of neutrons with respect to protons. Those energy density functionals which are used in modern calculations, they are usually parameterized in terms of 10 to 12 coupling constants. And those terms are usually adjusted by confronting predictions with experiment. Pairing functional is poorly determined. There are not that many data which can illuminate pairing functional. Usually 1-2 parameters are used to model pairing functional. The most popular density functionals are Scherm functionals, Goni finite range functionals, or covariant or relativistic functionals, which are used in the context of relativistic mean field theory. Okay, so these functionals can be used in the multi-reference DFT variant. Okay, so let me start from pair-like systems. We already got several presentations today about nuclei which have octupole deformations in the ground state. Okay, so this is an example of our recent calculations in which we use 9 energy density functionals. We carried out large-scale DFT calculations in the whole nuclear landscape, looking for the candidates for octupole shapes. Okay, so this is a standard nuclear landscape, neutron number, proton number here, and the limits of known nuclei are shown by this green line. So this is where we actually went experimentally. So the predicted drip lines are very far away. So here, as you see on the proton side, we are close to the so experiment is at the proton drip line. So stable nuclei are shown by black squares, okay? And the regions of octupole deformations are marked by these circles. So we use 9 EDF models. So if all 9 models predict octupole deformation in a nucleus, this is marked by a star. And as you can see, there are several stars here. This in the actinide region, which was discussed by Peter a moment ago. There are some candidates for octupole deformations in the heavy lanthanides around barium 146. Okay, so from the point of view of this discussion here, the nuclei which are hit, which in several models are octupole deformed are of most interest, and you see there are quite a few potential candidates here. There are also some nuclei in this region of heavy lanthanides, like some neodymium or some arum isotopes, which are stable. So in those nuclei, the theory expects strong octupole correlations. And the fact that the nucleus is stable, of course, is very useful because it's possible to do experiments much better. Okay, so this is the general picture. So those calculations were carried out for even nuclei. So one now needs to look into those regions and look for potential candidates for parity doublets for the EDM calculations. And this is what we are now trying to do. Okay, how does it work? How does it compare with experiment? So Peter, in his previous talk a moment ago, said that those models compare pretty well. And this is an example from our global calculations. This is the quadrupole moment, which was measured. This was taken from Peter's recent review, okay? And those are results of calculations. So you can see that for the quadrupole moments, there is a very, very good agreement with the experiment. So quadrupole deformations, elongations are very well predicted or reproduced by the models. But octupole moments, Q3 values, are not poorly described either. So there is pretty good consistency between the regions of octupole deformations and the current data. I would like to draw your attention to this recent paper by Mengzi Chen, which is on microscopic origin of reflection as asymmetric nuclear shape. In this paper, we try to understand how those pear-shaped deformations come around, okay, in the context of DFT, density functional theory. And we concluded that pear-shaped deformations are primarily driven by odd multipolarity isoscalar deformation. So like proton-neutron interactions, proton-neutron interactions in octupole channel, for instance, will be very important for the presence of octupole shapes. We also showed that isoscalar octupole polarizability is very large in atomic nuclei, okay? And also that exotic odd multipolarity couplings like dot-3 contapole, lambda=5 couplings are of great interest, okay? So one day, advanced Culex measurements perhaps will be able to get some information about those modes. Okay, so let me now talk a little bit about nuclear charge densities. So how to model nuclear charge densities, which are so important for many quantities which are measured in experiment, like charge radii, like quadrupole moments, hexadecapole moments, etc. So the charge density is expressed through nuclear charge form factor. And charge form factor is given by proton and neutron form factors. This index T stands for protons or for neutrons, okay? So this is the proton or neutron charge form factor, okay? But we know that nucleons also have some charge distribution, so those are multiplied by nucleon charge form factors, here marked by this symbol G, okay? So those have been determined by electron scattering, for instance, and very well parameterized. This D is defined in this way. This is a standard relativistic expansion, so there is a term proportional to Q square momentum transfer. And the second term here carries information on magnetic properties. This is the magnetic form factor. Magnetic moment appears here, and this F form factor FLS corresponds to spin orbit form factor defined through spin orbit current. So all those quantities like rho T, JT are calculated within the nuclear density functional theory. What is of interest that this JT here appears through its divergence, which is a general expression which is valid for spherical and deformed nuclei. So whether the nucleus of interest is spherical or deformed, this expression will be valid. Okay? So this plot shows the comparison between the root mean square radii of various nuclei. Some of those nuclei are magic, like calcium, tin, and lead. Some of those nuclei are deformed, like ytterbium or strontium. Okay, so blue color shows the proton charge, proton radius. So this is the radius of point proton distribution. One has to add all those corrections due to form factors to get the charge radius. So we see the charge radii are slightly larger than proton radii because of form factor, nucleonic form factors, relativistic effects. Okay. It's interesting to look at the balance of budget of various contributions to the charge radius. So the upper plot here shows the difference between the calculated charge radius and just proton radius. So all those corrections due to nucleonic effects and relativistic effects are entering this quantity. Okay, so you see here is contributions from the charge proton radius, charge neutron radius here. This is the contribution coming from neutron spin orbit. This is neutron magnetization, proton magnetization, and center of mass correction. It all sums up to this quantity, which you can see has definite dependence on the neutron number. So if we are interested in small differences, for instance, of charge radii between nuclei, so if you want to look into King's plot, for instance, okay, those small corrections will become important. And I'm showing ytterbium chain because there is definite interest in ytterbium nuclei because of beyond standard model physics. Okay, we are trying to get information about BSM effects from, say, King nonlinearities in King plots, some nice recent work. Okay, and but ytterbium isotopes are complex, deformed systems, so such calculations are important. Okay, this is interesting plot. This shows the difference again between the charge radius and proton radius in slightly different scale for the sequence of various isotopes. I just showed you ytterbium chain. Okay, and you see that there is a very significant difference between just proton radii and charge radii, and this difference indicated by this full radius, indicated by this red line here, shows very strong dependence on the neutron number and also on the proton number, of course. Okay. But if you are interested in small variations of charge radii, all those effects have to be accounted for. So of particular interest is this dramatic change here in the calcium chain when going from calcium 20, to calcium 40 to calcium 48, and this is due to the fact that one system is spin saturated, one is not, and spin orbit correction becomes large. So even larger corrections are to higher order moments, like R4 moment, okay, which is also of interest. So those upcoming measurements of charge radii might bring us some information about fourth radial moment. And as you can see in this plot, it is important how we calculate charge densities. So all corrections should be properly accounted for. Okay, so difference between red and green become large, and there is a strong neutron number dependence. So you can also see that those relativistic nucleonic corrections impact sigma, which is the surface thickness of the nucleus, and diffraction radius, which is extracted in the electron scattering. Okay? So the bottom line here is that if we are aiming at precise predictions, many small effects should be properly accounted for. Okay, so I would like to mention one interesting aspect of charge radii. So now I'm showing a direct comparison between charge radii, experimental charge radii for calcium chain. So those are given by the squares, and we see that charge radii in calcium show this characteristic pattern here. So the charge radius of calcium 40 and charge radius of calcium 48 are very similar. They're almost identical. And there is this rapid rise of charge radii, which was demonstrated by Isolde. And so Ronald, the chairman of this conference, actually is responsible for the is the first author of the paper, which showed actually this very large charge radius here. Okay, what about theory? So shown are several theoretical predictions here. So very standard Skyrm interactions, Skyrm functional, SV mean, does pretty decent job actually on this quantity, which is the differential radius, the difference between charge radius of a given nucleus and charge radius of calcium-48, but it does not reproduce this steep rise above calcium-48. There are ab initio coupled cluster calculations, which were mentioned by John. Okay, this is a very recent interaction, N2LO with this interaction knows about delta resonance. Okay, and again, not too bad. The best agreement here is obtained by the novel Fayance energy density functional, which has specific specific form of surface and pairing energy. Here, this functional actually makes a very good prediction for this charge radius. So the data like charge radii or quadrupole moments or magnetic octupole moments are extremely important for calibrating those nuclear models. And this is very nicely demonstrated here. So after so many measurements, for instance, from Isolde, showed us this amazing pattern of charge radii above neutron number 28. So this is a systematics of charge radii for a number of isotopes, calcium, titanium, up to zinc. And you have to admire how constant this radii are. If you subtract the values for neutron number 28, you get more or less universal curve. This was recently discussed in the paper by Agi Kosaros. And you see, this is almost perfect parabolic dependence. A is the slope and B is the curvature. Okay? So the question which we're trying to address in this recent paper, in which we attack this problem with both density functional theory and with coupled cluster method, was it whether in nuclear theory you also get this universal lines, whether the results will be almost isotope independent. And one is not as perfect as in experiment, but you can see that, for instance, in this ab initio coupled cluster method, one obtains a band of predictions which are with rather large slope. Using the Fayance functional, one can get, again, pretty good consistent result, not as consistent, not as universal as in experiment. Okay, so we see that this kind of data, or for instance, those two parameters, NAB, can carry very important information about the properties of nuclear models. And in principle, one should use this data to calibrate interactions or functionals. Okay, so the last part of my talk, how much time do I still have?
Yeah, so I'm sorry, you have no time. So
no time?
Maybe a few minutes, but in principle, your time is up if you want to get a few questions.
I start a little bit later. Okay.
Yes.
I just would like to mention the applications of those charge densities to recent PIREX2 measurement. So PIREX2 collaboration measured this parity violating asymmetry at Jefferson Lab. So this asymmetry comes basically from the Z boson exchange. So this is the weak part of the interaction. One obtains this by looking at this asymmetry between left and right helicity, actually electrons. So in this measurement, PREX2 collaboration got this parity violating asymmetry, which is of the order of 550 with large statistical and systematic error here. And this measurement was interpreted in accompanied theoretical paper. Okay, so this was a measurement as simple as a single kinematic condition at 1Q value. Okay, so one can extend this DFT formalism to this case. This parity violating asymmetry can be expressed as a ratio of weak to Coulomb form factors, which again depend on those nucleonic form factors and DFT densities. Okay, and this I will just show you two plots. The one shows the error budget for this parity violating asymmetry. I forgot to mention that this is in parts per billion. This is an extremely small quantity, and this experiment took long time. Okay, so this shows the error bars associated with different input when one calculates this APV. So this whole group of quantities pertain to this nucleonic relativistic effects, and as you can see, those things are calculated pretty accurately. So this is the total error due to this nucleonic relativistic part. Nuclear DFT models, of course, contain uncertainties. Those neutron and proton densities are not given precisely, and this is the error bar. Okay, and if one considers two typical DFT models, non-relativistic, relativistic, this is what one gets. Okay, one gets the value which is significantly above the PREX2 1 sigma limit. Okay, and this will be then my last slide. So what one can do in the next step, one can use the information which is, one can use this PREX2 value of APV, and one can calibrate new models based on this information. And you have those error ellipsoids here. So those are the models like SV mean star. So this model knows a little bit about the PREX2 result. And this is relativistic mean field model, which also has been calibrated to this. And you can see that those two models are closer to PREX2 data, but they are really away from the data on electric dipole polarizability. So there has been an experiment at Osaka at RCNP laboratory, which provided fairly precise data on electric dipole polarizability in LED 208. And as you can see, there is a significant tension between the PREX2 data on parity violating asymmetry and electric dipole polarizability from Osaka. So our conclusion is that there is a tension, okay, between existing data. If one takes well-calibrated models, they are somewhere here between Osaka result and JLab result. You could say that they are fairly close to 1 sigma limits of measurements. So the situation is not totally unreasonable. This interesting puzzle. Where is the problem with measurements, with theory? Okay. So I will offer simple conclusions, precise measurements of electroweak effects, offer sensitivity to explore basic properties of the atomic nucleus and study fundamental symmetries. And in order to establish constraints on beyond standard model physics, one is precise calculations of nuclear charge densities and other nuclear effects as discussed by Jacek and John, and theory is making a nice progress in this area.
Thank you, Vitek, for a very interesting presentation. I'm afraid you used a little bit of your discussion time, but still I would ask for a few questions. So put a question mark in the chat if you want to ask a question. There's a question by Pablo. Can you raise your question, Pablo?
Yes, you mean ask it?
Yes.
Okay, thank you. Thank you, Vitek. My question, I think I asked Menzi this a long time ago, but I don't remember if I had the answer. Do we have an intuitive explanation for the parabolic rise on the charge radius after n equals 28 as n increases?
Yeah, so those, if you look at nuclear shell model, between neutron number 28 and neutron number 40, there are 3 shell model shells, is F5 half, P1 half, P3 half, and P1 half. So they are close lying, okay, and there exists an effective symmetry of nuclear shell model, which is called pseudo SU3 or pseudo spin symmetry, okay. So in the language of this symmetry, those 3 levels form one pseudo SD shell, and in this, within this symmetry limit, radial wave functions are very similar, and radial matrix elements are very similar. And if you add pairing interactions to this, you will see that things should really change very smoothly as a function of a neutron number beyond number 28. So this result you can also get by looking into seniority scheme, generalized seniority scheme. So what is interesting is that those microscopic calculations have been issued, calculations, DFT calculations, they contain some elements of this seniority model and pseudo SU3 scheme.
Thanks.
There's another question by Ben Ohio. Ben?
Okay,
Ben,
I wrote
your question, yeah.
a short question. In the beginning, you mentioned that the pairing correlation in the effective potentials is not very well constrained by experiments. So could you comment on which experiments could be useful in that regard?
Well, I mean, we usually fit pairing coupling constants to odd even mass differences, and we have plenty of data on even mass differences, but this data do not discriminate between, say, volume pairing or surface pairing. This data do not tell us too much about the density dependence of the pairing Hamiltonian. So from this point of view, those isotopic shift data, radii data are very important. For instance, this data on isotopic shifts in the calcium region tell us that perhaps pairing interaction have gradient, density gradient term. So this is a very strong hint. So for instance, charge radii provide good information on pairing forces, which needs to be utilized in the global calibrations.
Thanks.
Okay, I see no more questions. There's time for one last if you want. No. Okay, thank you, Vitek, for a nice talk. And before moving to the next speaker, I just realized I forgot to introduce myself. So I'm Gerda Neyens, and I'm from the University of Leuven in Belgium. And I'm currently at CERN as the physics group leader of ISOLDE. And so now we move to the last speaker of this session, and this is Dimitri Budkor, who's going to talk about new approaches to molecular parity violation and the gamma factory. Dimitri, the floor is yours.
Thank you very much for giving me an opportunity to speak at this amazing meeting. Today, I'm going to tell you about 3 things that are not directly about radioactive molecules, but nevertheless, I hope you find them interesting. So my first short story for you is about measuring parity violation in chiral molecules. So people have been trying to measure molecular parity violation for the last 50 years, and maybe it's about time to succeed in this. And we're trying to see if there are some interesting roads towards this goal. And one of them uses this interesting effect called diastereomerism. And but let me first say that a chiral molecule is a system that doesn't have a certain parity, and so whereas normally parity violation doesn't cause first order energy shift, it does cause first order energy shifts in chiral systems. You can, for instance, try to measure that in, let's say, infrared or optical transitions in chiral molecules, but you can also try to do this in nuclear magnetic resonance, and in this case, you would be sensitive to nuclear spin-dependent parity violation. Now, if you estimate the size of the effect, and the effect would be, if you like, parity violating chemical shift. If you go to a high field magnet, today these magnets are about 20 Tesla in strength. For most favorable systems, the size of the parity shift is about 1 millihertz. And in principle, this is not a very scary number, but you ask yourself, how would you do this? And you immediately realize that this is actually quite impossible to do, for instance, if you have a racemic mixture of chiral molecules, because, okay, so you have some kind of a line, and clearly this would be broader than 1 millihertz, and then you have some small parity violating shift within that, and as a result, you will measure some kind of broadening, but it's really very impractical to try to detect this effect, because you wouldn't be really able to distinguish it from broadening. Then the next idea is, okay, we just take one NMR tube, we take one enantiomer, we measure the NMR lines, then we put another enantiomer measure again, and then we compare them. But then you realize that this is subject to terrible systematics, because if your container has a slightly different shape, you would be in a slightly different field, and there will be large shifts. It's practically impossible. So the idea that we're trying to push here is based on the effect that is called diastereomerism. And the idea is that if you take, let's say, a racemic mixture of chiral molecules, and now you put them in a solution where the solvent is also chiral, then clearly the interaction between left and left and left and right is slightly different. And this would lead to small splitting of NMR lines. And now I'm going to show you some data that was obtained a few years ago by James Eales, then an undergraduate student who is now a postdoc at Mainz and will soon go to work in Barcelona. And he used some kind of chiral molecules whose names I wouldn't even risk to reproduce here. And indeed, so putting a racemic mixture of your signal molecule, if you like, into a solution and changing the chirality of the solution, you
you see pretty nice shifts given here in hertz. So as you change the chirality, you see these blue peaks, let's say corresponding to the right enantiomer, they're split from the left ones, and as you change the excess chirality, you move, so the blue line is on the other side. And fantastic, so now you can measure parity violation because all you need to do is prepare a solution that with a chiral solvent and just basically extrapolate this to the point where, well, actually, you don't even need to prepare that. You just change the chirality of the solvent and then take the point where the chirality is 0 and extrapolate to see if there is any shift there. Of course, this is completely crazy because you cannot know when the chirality of the solvent is exactly 0. And here comes the central idea of this work is, and the idea is that in this molecule you have different types of spins. There are proton spins and C13 spins. And the idea is that the parity violation that scales as a large power of the atomic number is completely negligible for protons, but it would be non-negligible in principle for a heavy nucleus. And so now you look at different lines and you basically use your proton to measure the chirality of the solvent, and then the signal molecule measures the diastereomeric shift, and then the parity violation would show up as sort of non-zero intercept here. If you want, this idea is very similar to this very powerful idea used in all precision measurements, the idea of comagnetometry. And here, the nice thing about this is that you have your comagnetometer built in the same molecule. So this trick is I would say, a relative of the idea that is used, for instance, by the ACME experiment that we all know, measuring electron EDM. I think it's a pretty powerful idea. So the experiment I just showed showed the resolution of about a millihertz or so on that order. But unfortunately, the calculations of the effect that have been done by Mikhail Kozlov, who is the main theoretical brain in our molecular parity violation operations, are such that unfortunately the effect for C13 being a relatively light nucleus are very small, many orders of magnitude smaller than our resolution. So we really need to go to heavy chiral molecules. And as a first step, with a bunch of collaborators whom I'm going to show pretty soon, we decided to move to phosphorus containing molecules. Here the effect is larger, and this is in fact an intermediate step before we go to something much heavier, perhaps platinum or thallium or something like that, where for most favorable cases we actually expect millihertz type of effect already achieved, millihertz already achieved here. And where we are now, we're studying the phosphorus, and there are some preliminary results that have been obtained by Eric van Dijk in our lab, showing nice diastereomeric effect. Of course, there are many interesting things that are being discovered as we go. And here, in this type of experiment, you want to minimize interesting things, or at least you want to understand them very well. And that's where we are at the moment. So that concludes perhaps my first short story for you. And for the second short story, we move now to something different, and this is a proposal to measure parity violations, again, spin-dependent parity violation in spin-spin couplings, also through NMR, but in this case in non-chiral molecules. And originally we formulated this proposal in this paper over here in the context of liquid state NMR, but as we were trying, and in principle it works, but as we were trying to think of the best molecule to use in these experiments, we realized that actually liquid state NMR is not the best place to do this experiment. And so I'm actually going to show you where this evolved. And this is a paper that's about to be submitted with these authors over here. And the gist of the realization that, in fact, the best system that we know for this is, in fact, thallium fluoride, and not in liquid phase, but in fact in a molecular beam. And moreover, there is this program called Centrex that's being pursued under the direction of David DeMille and Tanya Zelevinsky to measure a nuclear time reversal violation. It looks like this parity violation experiment could be sort of a little parasitic addition to this in principle. And the effect is much bigger than what these guys ambitiously aim at. So maybe it could be an easy experiment for them. So just to remind you, these two nuclei, they both have non-zero nuclear spin, so they, in principle, you can write their spin-spin interaction, electron shell mediated spin-spin interaction as a second rank reducible tensor, where the zero rank tensor is the J coupling, scalar J coupling, but we are going to be interested in the first order, first rank component of this tensor. And this can be written as sort of this I cross S, where this is the spin of thallium and this is the spin of fluorine. This is like, for those of you who work with condensed matter, is like Ziloshinsky-Moria interaction. Okay, but in order to have a scalar here, you need to multiply this effectively by a vector, and the only vector that's available is the molecular axis. But then what you have here is nicely time reversal conserving and parity violating. So now we want to measure this effect. Maybe I should say a few more words. So the two spins, in this case, both of them are spin 1/2. They can form a triplet and a singlet. And it turns out that all we need to consider is the m equal to 0 state of the triplet and the singlet state, and then look at the transitions between these levels. One more thing to mention is that so this vector here needs to be directed along the molecular axis. And so normally if there is no electric field applied, this term will average to 0. So you need to polarize your molecules in the electric field. And so then the idea of the experiment is that you have your beam of thallium fluoride. You do laser preparation, for instance, into the singlet state, as you would do for the Centrex experiment, and then send it through a region where you have an electric field to polarize the molecule, and then the molecular, the magnetic field to drive the singlet to triplet transitions, and And in this transition, you would have an interference between the parity violation-induced term and so this electric and magnetic field induced term. So you can have many different versions of how you do this. The P or T even rotational invariant can be written like this. So you can modulate either electric field or magnetic field, and being the greedy people, we modulate both, as you can see here, and then there appears an asymmetry that you can detect here again with laser interrogation after the beam. And so you might want to know how big the effect is. And of course, we turn to our theorists for this. This is Mikhail Kozlov and Leonid Skripnikov. Actually, that's a beautiful story because Mikhail has estimated the effect here on the back of the envelope very nicely. And then Leonid has done a full-blown molecular calculation. So we really believe the results now. And the guys are saying that the effect should be about 1.5 millihertz. What does this mean? Well, if you take the parameters planned for the Centrex experiment, it means that you get a signal to noise about 100 in half an hour of statistics, if you are really statistics limited. And the question then is, what about systematics? Yeah, and I'm not going to go in any detail here, but to say that we feel that, well, maybe there is some systematics we haven't thought about, but it looks like the systematics are under control because there are multiple reversals here, because you can, for instance, reverse the relative phase of electric and magnetic field. You can use actually different rotational states, which is again this idea of built-in comagnetometer at work. There is also non-trivial dependence of electric field, so perhaps we're going to have a DC component of electric field and then an NIC component, and you can see that by changing the DC offset here, you can have actually this is the polarization of the states that you can change the sign. So there are many different things you can change to verify that this is indeed the effect that you're looking for. So we're quite optimistic about this and are hoping that the Centrex experiment actually adopts this as a side project, so to say. All right, so we are doing the work. So there is a Minds group that you see these guys over here. John Blanchard recently moved to industry, but maintains a close connection with us. And we have very, very nice collaborators.
Dimitri, we lost you. Dimitri.
Yeah, we can wait 1 minute to see if
maybe he will come back.
Yeah.
So it was not only me, I hope. Huh?
No, I think it was
everybody, I guess.
Because we had a thunderstorm here, so I was already worried. hope he comes back.
In the meantime, David can tell us how is it going with the Centric experiment. When do you expect to take these measurements? Is David the mill?
No, I think he left.
Okay,
Probably.
nice.
Maybe a minute. Yes.
While Dave's not here, I can maybe answer that question.
Yeah, please.
We're expecting sometime in 2023 or 2024. So a couple of years still to go.
I see. Yeah, thank you, Scott.
He's still not back. I hope he comes back. Would be
Email. Perhaps we will do something.
Sorry, Timur?
Yeah, hi, Arnold.
Maybe you send a quick email to just know if it's a Zoom problem or an internet connection issue.
Maybe, yes. Do you have his email, Ronald?
Yeah, I can write to him.
Yeah, I sent one email already, so.
Okay, super. Yeah, thank you. So I think we can start the discussion. So we have the Mikhail, the theories behind, and Robert. So in chiral molecules, so you will be sensitive to both the nuclear spin dependent and the nuclear spin independent parity violation.
If I may answer this one for the nuclear magnetic resonance experiment, one would mostly be sensitive to the nuclear spin dependent parity violation. There is a small contribution by hyperfine coupling and then the parity violating interaction, which is spin independent, but one expects typically for the heavy nuclei to be just dominated by the nuclear spin dependent term of the parity violation. But in principle, the chiral molecules offer the advantage that you can just choose by the type of spectroscopy if you want to go for the nuclear spin independent or for the nuclear spin dependent parity violation.
Robert, what would happen with the anapole moment then, if we're looking at the nuclear spin dependent?
That would be the major contribution, actually, right? At least for the heavy ones, that the major contribution comes from the nuclear anapole moment, and then there's this Z-naught exchange, which should be smaller, typically.
But then we cannot really tell from outside, right? From the measurement, we just have this p-violating effect, and that's it.
You have the p-violating effect, and then you have to disentangle, but you have the typical scaling laws that you say, okay, you are mostly sensitive to this part, right?
And Robert, which was the final molecule, you know, which was chosen for this experiment with?
So the phosphorus compound which was shown.
Yeah, but phosphorus compound looks not good.
No, well, it's a start, right? And then, I mean, as Dima mentioned, so then a lead or a thallium compound, which is chiral, would be then the one due to the additional Z scaling, which would certainly help, right?
So, and you don't need something with a special large deformation or an octupole. That's not important in this case.
For the nuclear spin dependent parity violation, I don't think that one benefits from the octupole deformation, but that's where I'm not entirely sure. A nuclear theorist should answer, I guess.
We don't see him coming back.
And there's a related question to John Angel. John, are you online?
Yes, but I haven't been listening very closely the last few minutes.
Okay. Yeah, I think the question will be, so you were trying to find observables that will be sensitive to this kind of sigma dot p terms, right? To constrain it. And I was wondering if the anapole moment, for example, will help in constraining that.
Maybe the anapole, yeah. Probably that would be useful. Yeah, that's a related quantity. Is it possible to measure the anapole moment of these unstable?
Well, nobody has measured that, but I think it will be more realistic to have these measurements. I mean, they will contribute, they will come experimentally far earlier than the violating properties. Yeah. So yeah, we have plans, and plans like this are to measure those anapodes. Yeah.
Is there any interest in barium, in higher neutron content baryons up to the 144, 146?
You mean for anapoles?
Yeah, for anapole or for shift moments?
Yeah, for us, definitely as a nuclear physicist, yeah, we would love to see systematic measurements for neutron-rich nuclei. Yeah.
All right.
Yeah, definitely. And yeah, and John, if you can show us how you can correlate those observables, that would be a strong motivation for us as an experimentalist. If by measuring the anapole, then we can constrain.
All right, let me think about that, but I will get back to you.
Yeah.
But I think you mentioned in your talk, right, that you have sigma dot R and maybe sigma dot P would help. So is there some correlation, or is it, I mean, that you don't learn from the P comma T odd property something for the P odd?
Well, so no, I think so what you really want is some matrix element involving those two states in the parity doublet. So sigma dot anything would be of some use, especially, yeah. Now the anapole moment, I have to check to see whether that state is going to be more strong, the only one which contributes essentially. Maybe, yeah. So I don't know about the other 1/2 minuses in that case would contribute. But let me think about it. Any matrix element that isolates those two states would be really helpful.
Yeah, that would be great, because definitely I think we are optimistic that we will see these measurements in the near future. Yeah, anapole moments. By the group work of David Emil and what the speaker was showing.
Any response to the email, by the way?
So then may I suggest we go for the lunch break?
Yeah.
And then we just come back and hopefully we'll have a DIMA after lunch and we can ask.
Okay, so I would like to thank the two speakers. Unfortunately, the last one isn't around, but I hope he can come back and enjoy the lunch. And so we'll be back in about an hour, right?
Yeah. Yeah, at 2 p.m. Boston. Yeah.
Yes. Okay. Okay.
See you.
See you. So Dima, connection is working again.
Yes.
Yes.
I don't know what it was. I don't know. There was actually a storm here. So I wonder
Okay.
if it has anything to do with it. I have no idea.
Yeah, could be
I'm really
because
sorry.
yeah, because we had one shortly before, right? So here in Geneva, so maybe
There was another outage.
No, I mean we were just worried that this is related to some storms which we had here, right? Also.
Oh, yeah.
Oh, yeah. Too bad.
To your question, I don't really know if deformation can help with this kind of parity violating interaction because it's good to violate the Schiff's theorem, right?
Yes.
But here we don't have that. So, but I'm not sure. I have never heard actually deformations discussed in the context
of anapole moments, right? Yeah.
Yeah. But actually, maybe it's a question too weak.
Yeah, so.
Hi, Dima.
Hi, Week. How are you?
Yeah, I had a question about your talk too. The interaction you showed with this asymmetry J discussion, is that also T violating? It looked like
No.
Momenta.
No. It can if the J that it multiplies I cross S is not angular momentum. It's an unfortunate notation due to probably Erwin Hahn, where this spin-spin interaction is labeled as J. You could put there rotational moment of the molecule, and then you have T violating component as well.
Yeah, I thought it looked like the triple correlations we know and love.
That's right. It's very unfortunate. It confuses a lot of people that this is called J coupling, but you know, history.
Do you have also a direct contribution, because the J is reserved for the indirect spin coupling, right? Otherwise, you could go for D or T, right? If you have also a direct contribution. So then there's not the mistake with this J, right?
Yeah.
So should I try to display my slides?
Well, that would be wonderful. Yes. So then we know that everything is working. Yes.
I was being reviewed when the practice time came up, so I missed that. So I'll see if I can share my screen. How does that look?
Yeah, perfect. Now we are in.
And can you see my cursor?
Mode. The cursor is working, but it's a bit on the light side, so it's a bit smallish. So if you have a larger one, that would be fantastic.
Yeah. How do I find that now? Oh, I'll make do with this. I won't use it very often.
Oh, okay, good. So then it's working. So I mean, it's visible, but one has to focus a bit, right?
Okay, got it.
Splendid view, by the way.
Yeah, hope Dima misses this view. Yes, the view from LBL over toward through the Campanile over to San Francisco.
Yeah.
During the holiday time. So one can see all the lights of the city.
Oh, wonderful.
So hi, Wick. Hi, everybody. This is Vincenzo. I'm supposed to chair the session.
Vincenzo.
Hi, and for the speakers, I'd like to set up some protocol. Is it okay if I give you when you reach the 25-minute mark, I'll make some noise, I'll let you know, and then you decide how to use the remaining 10 minutes. Technically, there's we should leave some time for discussion at the end. So, but I'll let you know when you reach the 25-minute mark. So.
Great. Sounds good.
All right, I would say we start. Welcome back, everybody, to this exciting session, which is in the afternoon for East Coast US time. I guess it's after dinner in Europe and maybe brunch time for our first speaker Wick. And so we'll start with Wick Haxton. He'll tell us about the strange case of Protactinium-229. Wick, please go ahead.
Yeah, I'm going to tell you a little bit about Protactinium-229, this strange behavior that's brought about because the energy scale for excitations is actually comparable to the typical atomic scale. And I also wanted to take this opportunity to bring Ernest Henley up because Ernest had a fantastic love for atomic physics and nuclear physics as many-body systems that could test symmetries generally. And I actually first got interested in this general problem of parity and time reversal violation from early interactions I had with Ernest. He was a frequent visitor to Los Alamos, where I was a postdoc. And we first got involved in parity and then moved on to time reversal. And I've kept this love of symmetries ever since due to Ernest's mentoring. And I also think this example of parity violation is a really good one for the issues that we're talking about, the enhancement of EDMs in nuclear systems. And there were really three reasons that these degeneracies became so important in parity violation. One was the ability to use quantum labels of nuclear states to filter, to isolate parts of particular interest to us. And the second were the two mechanisms of enhancement, nuclear degeneracy, which we discussed quite a bit today, but also further magnifying interesting interactions by competing symmetry-allowed suppressed transitions against symmetry-forbidden strong ones. So that's an additional source of enhancement that can occur in many body systems. The application to parity violation in the nucleon-nucleon interaction is fairly straightforward. Daniloff a long time ago wrote down the effective theory basically for parity violation at very low energies. There are 5 independent SP amplitudes, and they can be considered in various languages. The original language was in terms of Mason exchange, but more recently we've been thinking about the same physics in the context of effective theories. And so basically, if you build an effective theory for this interaction, you have 5 contact interactions supplemented by one channel where the pi and the long-range pion plays a role. And this is really equivalent to potentials like the Donahue, DuPont, Holstein potential that was developed, they have these 6 degrees of freedom buried into that potential. And it remains a very active, interesting field. The previous decade, there was the development of EFTs for this process. In the past few years, there's been a really interesting development involving the application of large NC to parity violation. And this, for the first time, has given us a sort of a hierarchy among the 5 low energy coefficients that one could write down to describe the short range physics. But the main issue, the reason that we turned to nuclei was the scale, the same problem that exists in time reversal violation. The natural scale for interactions is given here in the right-hand corner. It's on the order of 10 to the minus 7. So the experiments are very difficult. Early on, we found out that there was really only one experiment that could be done very, very well. And that was the polarized protons on protons. That's the only measurement involving an elementary system. That's what we'd ideally like to do 5 independent measurements in the nucleon-nucleon system to completely characterize the Danilov amplitudes. This was the one measurement that was actually done to 10% precision. There was also a very nice measurement of polarized protons, the symmetry measurements of polarized protons on the alpha particle. And so then something else had to be done. In particular, the great motivation for studying this field was the desire to isolate the neutral current in the nucleon-nucleon interaction. Turns out that that if you look at the charge current contribution in the isovector channel, it's suppressed by sine squared of the Cabibbo angle. So it's recognized very early on that if you wanted to see the neutral current, isolate that particular aspect, which had not been seen, could not be seen in hyperon decays or other changes, changing decays, that you had to find an isovector filter. And fluorine 18, this marvelous system, gave us exactly what we wanted. First of all, there was a great degeneracy between a 0 minus and 0 plus state, separated just by 39 kilovolts. And then these states have opposite isospin, so they interact by the isovector part of the NN interaction. And then the 0 minus state decays to the ground state. And there's a similar case, the neighboring case, fluorine 19, that also was tremendously important. It's interesting because actually for us here, because it's ground state doublet, it's actually a ground state doublet. And so not only can you see the asymmetry associated with the gamma decay of the excited state, but you could also probe very similar physics by measuring the Anapel moment of fluorine 19. And what happened to us was when we found these 4 cases, and these were the 4 cases that could be not only measured but interpreted. It turns out these 2 nuclear cases, the nuclear physics can be essentially measured by looking at axial charge beta decay. We had to wait 25 years for new results, and those new results have just come in the past couple of years with the SNS cold neutron beamline beginning to produce results, first for NP to D gamma, and then for polarized neutrons on helium-3. So we finally are back in the game of being able to measure parity violation at this requisite scale of elementary systems of 10 to the minus 7 to 10 to the minus 8. Now, the enhancement in fluorine 18 is interesting because it has 2 sources, and both are important. One is the doublet, the fact that there's a very low energy denominator. So the 1 over E is typically, that appears here, is typically 100 times the typical nuclear scale for parity violation, which is H bar omega. So there's about a factor of 100 that comes from the fact that we found a doublet that we can exploit. But the other factor of 100 that comes in fluorine 18 comes because there's an isoscalar E1, which is the normal way the 0 minus state decays, that competes with the symmetry forbidden M1. And the E1 in a self-conjugate nucleus is forbidden in first order, so it's quite weak. But the M1 in this case is extremely strong. It's over 10 single particle units. So this gave another factor of 100 of enhancement. And combined, you expect to see not an experimental observable at 10 to the minus 7, but instead one at 10 to the minus 3. And what puzzled us a great deal until very recent years was that heroic experiments were done to try to measure this effect. It was not seen at the 10 to the minus 3 level. In fact, it's not really seen yet. And that seemed to contradict what we were expecting about the size of the neutral current hadronic parity violation. And it's the impact of the recent work on large NC that told us that, in effect, we initially expected the pion coupling, the size of vector coupling, to be leading order. But looked at in the context of large NC, we now recognize it is the next leading order. And that gives us this additional factor of 10 that explains this suppression. So we've made a lot of progress in this field. I could talk about this for the whole half hour. I want to go on to the main theme. But the lesson is that we have these two sources of enhancement that we're able to exploit, and we learned some good physics from this. So the theme is to find, it's rare to find both conditions satisfied in EDM measurements. And I think possibly protoactinium-229 may be an exception for those. They're both very strong admixed multiple, as well as an exceptional, interesting degeneracy. So in EDMs, we'd like to understand what happens if you're trying to measure an EDM, not in an elementary particle, but in a complex nucleus within a neutral atom. What are the moments that contribute to the response? And how do you decompose this response into its various contributions? And Michael already showed this table this morning, how you classify the electromagnetic moments of any particle or any composite system into their various components that are P even, T even, P odd, T odd, P odd, T even, or P even, T odd. And the interesting case is if you're, it's interesting case for P odd, T odd interactions, if you're measuring in the neutron, of course, is the EDM. That's the only thing you can construct. But if you go beyond that to a nucleus where the ground state spin is variable, it can be a half, greater than half, greater than 1, greater than 3 halves, then only the C1, but the C3 and the M2 can contribute. And protoactinium turns out to be a case with the spin 5 halves ground state, where all three of these interactions contribute and can be interesting. What about a generic case? How big is a nuclear EDM, given that if you've measured, for example, a neutron EDM, what would you expect if you go into a nuclear system? Well, that requires you to build a little bit of a model for how the nucleus generates its EDM. So this is before you put the atomic electrons around it to screen. And basically, an external field can couple directly to the nucleon, which is the first diagram shown here. And that's the EDM coupling. But the ordinary C1, the ordinary dipole charge operator, can couple to the nucleus and see the parity violation, that mixture that appears because of the nucleon-nucleon interaction that will violate parity and time reversal. And also, there are in general exchange currents that shown down here at the bottom, where the interaction is in fact with more complicated constituents of the nucleon. So basically, the nuclear EDM breaks into a one-body part that you would think of as equivalent to the free nucleon EDM, this polarization contribution and this exchange current contribution. And this is the dominant term. It's the term that allows you to build the biggest charge separation over the longest distance, and that's why it dominates the EDM in the nucleus. And you can kind of see that dimensionally. If I take a nuclear EDM, what do I expect? Well, I envision this as my a valence nucleon interacting with the next rest of the nucleon through a T-violating and P-violating interaction. So this is some sort of coherent field that's generated by all the other nucleons on the valence nucleon. And that valence nucleon can be distorted now over a size scale that's comparable to the size of this of a heavy atom, which is a large number. What is that number? Well, the size of the nucleon is basically, which determines the EDM of the nucleon, is basically proportional to m pi. The size of the valence orbital in a nucleus is basically h bar omega, the separation between positive and negative parity nearest neighbor shells. So when you compute this, you'd expect that the nuclear EDM, kind of generically, an average nucleus with no special degeneracy, would be 10 times the EDM of the valence nucleon. And in fact, that works out for a wide variety of real calculations. That's more or less what you find. The polarization effects dominate and typically enhance the EDM by a factor of 10. And if you're then lucky and find in addition a case where there's a very, very a favorable energy denominator, then it could be that there's an additional enhancement proportional to h bar omega divided by that new energy scale that comes from the parity doublet. So we're able to maximize the charge separation by deforming the valence nucleon over the orbit of the valence nucleon over the entire nuclear size. And that's why nuclei are great. And why they're bad is just shift screening, which we've talked about quite a few times, but it's the reduction in the response because the electric field, when it applies, is applied to a neutral atom, the electrons essentially screen the nucleus except for finite side effects. And so you can make a little approximate formula for what the loss of sensitivity to do that, to get to it because of the shielding. And it's on the order for a heavy nucleus of 10 to the -3. So if you do this with the back of the envelope sensitivity estimates, how good is the mercury 199 measurement, for example? Then if you turn on the generic shift screening and consider only the nucleon EDM, you would expect a interaction strength, affected nuclear atomic dipole moment of something on the order of 5 times 10 to the -4 of the valence nucleon EDM. But if you now include the polarization terms, you gain this order of magnitude. And so in fact, the real strength with the polarization added because of this large size effect is about an order of magnitude larger. And then you compare experiments because the experiments are not equivalent. The mercury experiment has a greater absolute sensitivity than the neutron right now, and that ratio is 4 times 10 to the -4. So when all the dust clears, what you expect is if you interpret mercury 199 properly in terms of depending on some underlying source of CP violation, the limits you should get should be about a factor of 10 more stringent from those derived from the neutron. In actual practice, it doesn't quite work out quite this well, but that appears to be because the shift moment for mercury is somewhat anomalously small. So you lose this order of magnitude that you expect to gain. But it makes things very, very exciting because now if you in addition can find a really great doublet that can further enhance this, like we did in parity violation, get a similar factor of 10 to the 4, then you might expect to be probing EDMs on the order of 10 to the -30 in such a special system, if you could do an experiment as exquisitely precise as the mercury experiment. And so we jumped into this, Ernie and I, at a particular range. This is the standard formula that tells you how you go from a UV theory all the way down to the bottom, which is the experimental measurement. And we were able to jump in because there was a nice available interaction at the time at the nucleon-nucleon level. And so we could take a nucleon-nucleon level or an EDM and then propagate it back down to an observable. And that particular theory we used was the QCD theta parameter because of some nice work that had been done where they reduced this interaction to an effective low energy CP-odd coupling of the pion to the nucleon. So in addition to the usual axial coupling, there now was a scalar coupling that was CP violating with the right phase associated with it. And that could be related to the parameters of the theta parameter in the QCD Lagrangian. It happens that this case is isoscalar. The isovector coupling also rises, but is suppressed by m pi over mn. And you can take this interaction and generate the CP-odd nuclear interaction that you also need in a nuclear calculation. And that has a rather simple form, sigma.r with the associated Yukawa. And this interaction is the interaction that can mix opposite parity orbitals of the valence nucleon and produce the charge distortion that you need over the nuclear size. You can also, of course, generate the nucleon EDM in this way, and roughly it can be estimated to sort of a factor of 2 by just calculating this pion loop. It's the same idea. The pion is the lightest meson. It can produce the largest charge separation, so this should dominate the nucleon EDM. So that can be calculated as well. So you basically have the ingredients with this simple pion nucleon coupling to actually go ahead and calculate a nuclear EDM. So the fact that you know the strength of this DN fixes the single nucleon coupling, and that can be used to calculate the C1, M2, and C3 moments in a nuclear system that are associated with the valence nucleon. But it also gives you the interaction that you need to calculate the polarization, which you expect to dominate the nuclear EDM. So in addition to the valence nucleon contribution, there's a contribution that involves a polarization of the nucleus, basically. This interaction that takes you from the ground state to some state of opposite parity, and then it couples it back down through the C1 operator. So that's the polarization term. that you expect to be generically dominant in these nuclear cases. And much more has been done. In fact, there's a bunch of nice papers that you can access. We understand more details about how the theta term should work. In particular, it generates, in addition to what's been discussed here, in principle, a 3-pi interaction and therefore a 3-body interaction. This arises in order m pi over mn squared. And you can do similar reductions for other sources of CP violation. There's a series of papers that a couple of our chairmen and others that are participating in this meeting that are archived at the KITP website from the Frontiers in Nuclear Physics program, which dealt with this problem in some detail. So this kind of motivated us to take this simple model, simple example of a CP violation that we could implement for both the polarization and the EDM terms, and then to search for dipole for doublets where we might be able to see enhancements similar to those that we found in parity violation. And of course, it struck us we were lucky to do this search just after Ahmed had done his work and found the doublet in protoactinium-229. And so that was the one case where we saw a really large enhancement. So factors of several thousand for the EDM, and actually for on the order of 10,000 for the M2 moment. But surprisingly, we only found this one case because there were a number of other cases where if you look at the size of the energy denominators, they're very similar to the ones that we found in parity violation, but you don't see the corresponding 4 orders of magnitude enhancement associated with that. And that's because of this feature. And unfortunately, I quoted the C1 as sort of odd units, but if I translate these odd units into Weisskopf units, you'll find that all of these cases, except for samarium and protoactinium, correspond to E1 strengths that are less than 1/100th of a Weisskopf unit. So what's missing in these systems, what's missing is the strong parity odd multiple that allows you to really see the parity and mixture that's generated by the parity mixing of the nuclear states. And that's why you don't find more spectacular cases in EDM studies than we do. And in fact, even as written down here, the samarium and protoactinium cases involve interaction strengths with the C1 that are on the order of 0.03, 0.04 Weisskopf units. So relatively modest. And what that reflects, of course, is the fact that E1s are incredibly collective in heavy nuclei. All the strength gets sucked up to high interaction energies. Very little is left over for mixing these parity states. So we were somewhat actually disappointed by these results that only one case came up that looked really interesting. Now the PA229 case turns out though to be a little non-trivial. So we've seen about these enhancements. The relevant experimental information is actually given here. We have the doublet at the ground state. Various measurements have disagreed about exactly how degenerate this doublet is. One group even disagrees whether there is a doublet or not. But at least in the tabulations, this claim that this doublet does exist and is somewhere between 160 and 220 electron volts. The internal conversion coefficient is measured, and that's how we got that C1 matrix element. I'll come back to that. That's the big issue here, is interpreting this internal conversion rate. And then this nucleus decays by electron capture with a lifetime of about 1.5 days. So not as long-lived as radium, but long enough that you could probably do a good experiment. And it is definitely a 2-level system, because if you look at the next identified state with the right spin to mix with either of the doublet states, it's at 99 keV. So the ratio is a factor of 500, very similar to the same ratios that we found in parity violation. So we know the mixing of this state is suppressed by almost 3 orders of magnitude. So all that's very good. So we did our calculations with a simple Nielsen model. We were intrigued by this case, but we really were not motivated to do very much more work after it was originally found for 3 reasons. One, there were no examples at the time of EDM experiments done with unstable isotopes. There was no source of protoactinium-229 that you could imagine using for a long-term experiments. And none of the correlations that had been studied in recent years between octavole deformation and enhanced EDMs were explored at that time. But all that's changed. The radium experiment has been done. It's a big success, and it's going to get even better. The isotope harvesting at EFRI is ideal for protoactinium. Turns out it's right in the sweet spot of what they produce. And in fact, if you actually calculate the number of available atoms of proto-actinium-229 and don't mind replenishing your trap or device as frequently as required, you can get something on the order of 50 times the amount of proto-actinium-29 as you can of radium-225. So that's great. And then Jacek and John and collaborators have looked carefully at the octopole moments in this region, and they found that proto-actinium-229 is consistent with other isotopes and really kind of favorable. So things look very different today than they did a long time ago when we first considered this doublet. This moment for proto-actinium-229 is kind of interesting, though, and I'll try to explain why in a second. So this is kind of the standard way we think about the shift moment. There's some external field that comes into the nucleus, and it can also come in and polarize the electron cloud and then de-excite the nucleus. So we have these three diagrams. The shift theorem is not usually done this way, but it's instructive to think about the shift theorem as a little toy model of vector theory, where you're expanding in the ratio of the atomic nuclear size to the atomic size. That's the small parameter. And if I do that counting, what I find, of course, is this is couples directly to the nucleus. It's an EDM, so it's got to go like the nuclear size. This is likewise, it couples to the atom, the C1, so it's got to go like the atomic size. This has got a bubble, but a bubble is an atomic energy. An atomic energy is 1 over an atomic size, so in counting that goes like RA. And this is the Coulomb interaction, but it's not the entire Coulomb interaction. It's just the Coulomb interaction associated with the dipole, because we need that parity. And if we expand the Coulomb interaction in multiples, we can see that there's a suppression here. First of all, the Coulomb interaction goes like 1 over RA, but in the dipole, there's an additional factor of Rn over Ra. So when I attach all these guys and multiply them all together, I find out that each of these diagrams is proportional to Rn. So that's why they're canceling. It's possible for them to cancel. It depends on the details. The details is given by the physics, and they do. So the point Coulomb interaction used above, it gives you a total of 0 for the sum of those three top diagrams. So it tells you got to deal with the part of the Coulomb interaction you didn't use, because this is the point Coulomb interaction. The real Coulomb interaction, in addition, includes the penetration term. There's obviously no penetration terms in the direct diagram, so you have to reevaluate the last two diagrams, including only the penetration term, and that's what generates the shift moment. And when you do that, you find out that the residual interaction is proportional to the bare ADN interaction, but suppressed by 2 powers of Rn over Ra. So that's the shift shielding. Now, why that's interesting is something we didn't recognize way back when we first found the proto-actinium case, which is dynamic shielding. Even though dynamic...
You're at 25 minutes. You're at 25 minutes.
Dynamic shielding is something that's actually in the literature as way back in 1978. I think the very first paper was written by Mel Leon and Safety. And it says that the shift shielding doesn't necessarily apply only to moments. It can, in principle, apply to excitations if the excitations are extremely low energy. And the one existing case where you satisfy the condition in the case of a dipole, is that the energy denominator of the doublet has to be small compared to the energy of the average E1 strength in the atom is proto-actinium-229. So in fact, this cancellation is a little bit more complicated than we really assumed. Where it comes in is in fact in the interpretation of the internal conversion coefficient. Because what was done to estimate the strength of that parity allowed, parity forbidden transition that we used to get the C1, if we took the internal conversion coefficients from the standard extrapolation from the standard tables, applied them to the lifetime and estimated the E1 strength. But that's wrong, because now if I look at a transition from an initial state to a final state and write down exactly the same diagrams that we had for the EDM, the exact same cancellation occurs, except for the fact that there's small energy difference between the initial and final states. When you work this out, you find out that distinct cancellation is again exact, except for a correction that's proportional to the splitting of the doublet divided by the atomic E1, which is about a 10th. And in fact, you can confirm this by now doing a real calculation. So we use a Los Alamos RPA code, which puts in the bubbles to actually calculate the internal conversion coefficient. And then we compare it by turning off the bubbles and just calculating the mean field rate. And what you see are these huge differences between the internal conversion coefficients with and without the RPA bubbles. And so basically these calculations encompass what was previously used in this calculation, but they're all wrong. Their RPA corrections reduced the strength, the transition rate by a factor between 49 and 200, depending on how you do the atomic physics precisely. What that means is, since the experimental rate is the experimental rate, the only way you can match experiment is you've got to boost the size of the C1 matrix element in the nucleus by the square root of this number. And so that means that this nuclear E1 was really exceptional. But it was not only a good doublet, but in fact, the strength of that C1 transition is a fair fraction of a Weisskopf unit, somewhere between 0.2 and 0.4 Weisskopf units. So it's the only case I know where you get both the energy denominator and this very, possibly this very strong C1 E1 matrix element at low energies. There are other, protoactinium-229 is actually fairly complicated. I'll say a little bit right at the end about what this means, but it also has contributions from the C3 interaction. It has contributions from the M2, and at least the nuclear part of the M2 is quite strong for this case. That suppression is only Rn over Ra, but is also suppressed by relativity. So it's on the same order as the C3 and the C1. And finally, Satoru Inoue has even calculated a new contribution that explicitly depends on the fact that you've got this very small breaking the scale due to this nuclear intermediate state that may also be important in this case. So let me conclude now, because I'm out of time. I think the success with radium-225 is really that plus the extraordinary energy denominator, plus the effort production abilities, and the efforts to predict size of octahole productivity all seem to motivate today more thought for protoactinium-229. The internal conversion screening arguments presented here are intuitive, but they're also backed up by detailed calculation. So requires it gives you an unusual case where there's an enhanced E1 or C1 that can further boost the size of the nuclear EDM. PA229 theory is complicated because you've got the C1, M2, and C3 multiples all contributing, and because of the breakdown in the usual Rn over Ra counting, because you've got to deal in many ways with this very, very low energy nuclear excitation. All this has to be done in detail. And I think progress on this problem is going to take a fair amount of coordination between atomic and nuclear physics. I think that's been the rub why so little has been done. Each of these polarizabilities involves some pretty complicated polarization in the atomic cloud. And so a nuclear physicist can't actually carry through a calculation to completion. So I think what really good outcome for this meeting was to build some collaboration to try to make some progress on these three moments and to look at the terms that Satoru looked at to see if they are sizable as well. Thank you.
Thank you, Wick. We already have a question from Dima, and I would encourage everybody else, just type a question mark in the chat if you have a question, and that way I'll see it. So please, Dima, go ahead.
Wick, thanks so much. This is super interesting. I have a question. If you have, say, hydrogen-like protoactinium, or even bare protoactinium, the lifetime would be much longer, right?
That's right. Yeah.
So, and then the second question is, if you magically had a laser that can scan around 220 electron volt, would it be useful to do laser spectroscopy of this nuclear transition and find it that way?
Yeah, in idle times, I've thought a lot about this. First of all, if you can strip it, then what you should see is this screening should no longer be effective. So the decay rate will be adjusted, it will be faster actually. And in a laser experiment, if you could go to a light source and somehow pump the state, you see a very, really is like, you really have two dipoles that are mixing.
Yes, I think it's possible.
There's a plus and a minus state that exists there when you do the quantum mechanics. One of the state decays very rapidly, the other one very slowly. So you should see a pretty weird de-excitation spectrum if you could actually do this measurement. So yeah, it'd be fabulous if someone could actually do a light source experiment and manage to get enough photons in that they could excite the state despite the screening, then the decay of that system afterward would be really interesting to watch.
I think it might be possible.
Okay, thank you. I think John Engel has a question. Please, John.
Hi, Wick. That was really nice, and I appreciated the historical perspective. I have a question about the E1. So the fact that it's large might indicate that you have octopole deformation, but other than that, I'm not sure why it matters because that's not really the operator that's relevant. It's the Schiff operator, which can behave somewhat differently. So why are you putting so much emphasis on the E1?
It was mostly to try to get this intrinsic strength of the E1, because what we notice is, I don't know how it will track if you start now multiplying by powers of R squared, which basically happens when you do the correct shift theorem. But this was the only case where we found states that were strongly coupled that in the nucleus by an E1 that involved the parity doublet. So it seems to me it says something about the nuclear structure of this case, that something has to be going on that is defeating the normal rule that all the E1 strength gets sucked up to the giant resonance region. So that could be the octopole deformation, but I haven't seen, I don't know, maybe you know if someone has actually calculated the C1 or the E1 in this case, but I would be really interested in whether or not you get the requisite enhancement from calculating that interaction in the bare nucleus.
Yeah, I don't know if it's been canceled, but you do expect, I mean, if it's been calculated, but you do expect larger E1s in octopole deformed nuclei, although sometimes you can have, things which cancel them out, but in general, on average, you expect them to be larger.
And I should stress that when we did the atomic calculation, we effectively have the shift moment in there. I mean, that was a real calculation. It had the real nuclear distribution, and it also had the fact that the energy was not exactly zero, but instead is 220 electron volts. So that was a demonstration. I mean, in a sense, the internal conversion is like a measurement of the combination of the effects to the shift moment and to the intrinsic nuclear decay. So it's almost what you need for the parity violation, except for the fact that the energy is not exactly zero, but in fact 220 electron volts.
Okay, thanks everybody. I think so. We should move on. Let's thank Wick again. But I want to remind everybody that after the session, we can go into the breakout rooms and ask more questions to the speakers. So let's move to the next talk. Jason, Jason Holt, tell us about ab initio theory for fundamental symmetry studies. Please go ahead.
Sure. So is the screen looking good? I assume that's yes.
Yes.
Okay, excellent. Great. So yes, greetings from a very balmy Vancouver. Hope everybody's staying hydrated out there. Yeah, so today I'm going to be discussing some very nice work that we've been pursuing here at TRIUMPH, really pushing the frontiers of ab initio nuclear theory, and as you'll see, also atomic theory, not just for the usual questions in nuclear structure physics, but kind of into I think the very exciting area of really being able to attack big questions in beyond standard model physics where nuclei are relevant. And of course, for this workshop, the question of fundamental symmetries is the key one. And it's actually interesting, this work was triggered by a visit that David DeMille took to TRIUMPH a couple of years ago, where we realized that there's a huge need for these types of calculations, and we've been working hard ever since. So to see these results, please stick around for the talk of my postdoc, Takayuki Miyagi, who will tell you all about that. But what I would like to do is really sort of frame sort of the progress in the field, just since this is a very broad audience, just to kind of give everybody an update for where we are really as a field, and then frame this, how we would attempt to attack the question of these searches for fundamental symmetry violations in terms of other big questions in beyond standard model physics that we're currently working on. Just again, a few brief really overview here. One of the key ones, of course, is neutrinoless double beta decay. And you're going to see a kind of a similar pattern here. Again, if the neutrino is its own antiparticle, then again, this process could exist, where again, only the two electrons would be given off. There are, of course, a large number of large-scale searches taking place around the world looking for this process, which, of course, as of yet has not been observed. But were it to be observed, there would be a laundry list of new physics, not the least of which would be if some rate for this process were observed, then we're able to get at, well, sort of in the absence of exotic new physics, this object, which would set the absolute mass scale of the neutrino, but only if this object, which is the nuclear matrix element sort of governing this decay, can be calculated accurately within nuclear structure theory. And this object isn't just relevant for if this process would be observed, but also in sort of these types of exclusion plots that are produced from these searches as they sort of push the lower limit of the lifetimes as kind of ruling out regions of neutrino masses. You sort of get these bands and kind of move down. But the widths of these bands, of course, are not some experimental uncertainty, but our uncertainty in this object. And so kind of you get the sense here that were we to come along and do a better calculation than what's previously out there, that could not only change the size of this band, but shift it up or down depending on what we find. And so there's a very similar question, of course, in searches for dark matter, where in direct detection experiments, again, there's a large number of these taking place around the world. We hope to learn something about the nature of dark matter by seeing, for instance, a galactic WIMP scatter off a proton or a neutron inside of a nucleus, and we're there to see it. But of course, again, similarly, to put the results of all of these different experiments, which use different target nuclei, onto these sort of exclusion plots, again, that you see. We need this object, the differential cross section, but within here, there's this object called the structure function, structure factor, which again can really only be calculated from nuclear structure theory. And so again, if we're to come along and this object changes from what's previously out there, that can really change the picture of what these experiments are seeing or not seeing. And again, this is quite similar to, at least in spirit, to searches for fundamental symmetries violations, where there's a number of high precision searches underway worldwide involving a number of target nuclei, typically in the medium to heavy mass region of the nuclear chart, which is a challenge for us. Because not only do we need a good description for the nucleus, we need a consistent description for the electroweak physics that's relevant, and we really need to be able to move into the heavy regions of the chart. So that's why we're only now just beginning to attack these types of a question. But to really give the idea of how we approach ab initio theory, just would like to give a quick little a verbal description of it, which Marie Goeppert-Mayer kind of laid out quite nicely. And so this is really our approach here. Is the first, or the basic approach, is to really study the elementary particles or properties of mutual interactions. And here's the first key point. One hopes to obtain knowledge of the nuclear forces. So that's really our first ingredient in this ab initio approach. And then if these forces are known, one should, in principle, with no further adjustments, no further touching, just calculating, be able to deductively calculate the properties of individual nuclei. And it's only after this has been accomplished can one say that one completely understands structure. And so that's really our ab initio approach. And really in here are the two ingredients that go into that. And this is, then you can contrast with the more model or phenomenological approach, where you gather data and you use this to inform particular models, which again is not, this can give you a clue to the structure of the nucleus, but it's not this sort of ground up approach that we would really like. And so how we do this in practice, this boils down to something very simple to look at, but of course, virtually impossible to solve. What we're really after here is being able to attack just the nuclear, the many-body Schrödinger equation, where again, really the two ingredients are, first of all, what is the Hamiltonian in this picture? And already in nuclear theory, this is a challenge, because in principle, you'd like to get this from QCD in some way. But of course, there are many different energy scales sort of separating that type of physics from what's really relevant inside of a nucleus. And so what we use is this approach, which we'll hear more in the next couple talks, called chiral effective field theory. And what this essentially is just a low energy expansion of QCD, where we treat the nucleons as point particles and pions as the only other degrees of freedom. And so what this allows us is really then a systematic expansion of nuclear forces, where we have 2, 3, and higher body forces really rising in a natural hierarchy in the scheme, as well as a way to consistently treat electroweak physics. And so this really, in principle, gives us this approach to treat all of the physics that should be relevant for all of these nice beyond standard model physics questions that we're interested in. And beyond this, if this is pursued rigorously, this allows us to, in principle, quantify the uncertainties from the interaction side. And so that'll kind of be a main theme in the ab initio approach, is that we're really also aiming not just to provide calculations, but to provide really meaningful and rigorous uncertainties. And so in principle, this gives us that power. So even if we have these perfect interactions, which are, this is a whole field in and of itself, we then need to essentially solve the nuclear many-body problem. And that means in some way really kind of solving this tremendous dimensional eigenvalue problem. And really over the years, this has been quite slow progress, simply because of the methods that we have, which typically scale exponentially with mass, and with the sort of concurrent growth in computing power, there's been really kind of a slow linear trend up over until roughly a decade ago. But since then, there's really been a flourishing of new polynomially scaling many-body methods, where there's some quasi-sacrifice in accuracy, but nonetheless, these are all controlled and systematically improvable. But due to this polynomial scaling, you see there's really been an explosion in the reach of ab initio theory. And again, this plot's now a couple years old. And as we'll see in a few slides, we're really up here currently, and we might be way beyond mass 100. So we'll see about that. So it's really been a very exciting time to be in this field, especially over the past few years, and really the physics that we've been able to attack. And so this is roughly where we were a few years ago. Just simply because we can get to something like mass 100 doesn't mean we can calculate everything in there. And that's really been one of the big challenges of the field, because most of these methods work quite nicely near doubly magic, or doubly magic plus or minus 1, or in some cases spherical even type systems. So this is really sort of where we were as of a few years ago. So not a bad coverage of the nuclear chart. But what we really didn't have was some approach which could really hit everything. So really where we could look at systematic physics across isotopic, isotonic chains, or in entire regions. And that's sort of where our approach came in. Again, this is going to go quite quickly. I don't want to inundate with theory, just to give the basic idea. But the approach is what we call the in-medium similarity renormalization group. Really don't worry about that. All it is a clever way to construct a approximately unitary transformation, which decouples away whatever physics is making your life difficult. So if we're interested in just a doubly magic system, like say oxygen 16, what this allows us to do is essentially come up with a transformation where we go to a picture where all particle hole excitations out of this sort of reference state are decoupled. And when this is done, again, this is not an easy task, this essentially would give you then the exact energy for this ground state. And that's sort of what we call the single reference. And so this is why a lot of these methods worked well at doubly magic systems. But where the power here comes in is we proceed through another step, another approximate unitary transformation, which decouples a valence space Hamiltonian from the full A-body Hamiltonian. And so once we do this, this looks similar to something like a standard shell model, except when we diagonalize this simpler problem, this would, in principle, if there's no truncations made along the way, this would give us the exact a subset of eigenvalues of the full A-body problem. So it's really an ab initio method, which looks a lot like the shell model as a last step. So this not only allows us to get at the energies, but the beauty here is once we have this unitary transformation in hand, we can apply it to any operator and to get a consistent valence space operator consistent with the Hamiltonian. So whatever you have, we can then calculate. If we can write down an operator, in principle, we can then start calculating. So whether we're talking about simple things like electromagnetic operators, E1, E2s, M1s, things like this, or more complicated things like neutrino double beta decay or Wnt nucleus scattering, or the operators that are relevant for these fundamental symmetry searches. So that's our method. And now in principle, what this allows us to do is really then attack the entire regions of the nuclear chart, where really the only limitations are weirdly on the storage limitations for 3-body matrix elements, and in doing this last sort of shell model step. So once you get to sort of the heavier regions, your valence spaces, you kind of need bigger ones, and the dimension of these can just kind of grow beyond what's currently doable. But just not to show you that we're just sort of cheekily coloring this whole thing pink and saying, yeah, there we go. Over the past couple of years, we really did undertake a very large scale study of the nuclear chart up through, well, roughly the nickel isotopes or so. There's some good stuff going on out there, where we really calculated all nuclei here. And just by looking at, I think there's roughly 700 or so, sort of by looking at the separation energies and comparing with known data where it existed, we were then able to make predictions for the limits of nuclei, not just on the proton-rich, but on the neutron-rich side. And really across where data was available, we found quite nice agreement. But just this is another talk in itself, just to give you an idea that we really can do this. And so this really opens a number of very exciting nuclear structure questions, but I'm going to skip that and go to what's of much more interest here, into the beyond standard model physics questions. And so this is really sort of the type of things that we're looking at here in my group here at TRIUMPH. And of course, the problem is if you sort of look at where the nuclei that are relevant for these types of studies, so neutrinos double beta, you have the xenons and things like this up here. Of course, for us, cesium is up here. These lie just sort of tantalizingly outside of our region. And so close, but not quite. But actually, Takayuki, who you'll hear from in a little bit, had a very nice breakthrough earlier, well, last year, where we really were able to overcome the storage limitation in the 3 nucleon matrix elements, where just very quickly, these open circles are where we were before, where roughly 100 gigabytes is the computational limit. And so this sort of marker in how we store 3-body matrix elements, not worry too much about it, but let's just say that previously we were here, the maximum would be in 18 in this E3 max truncation. And with his new scheme, which again is quite clever in storing only the matrix elements that we need in order to do the type, to capture what we need in our calculation, we're really able to get at least a couple orders of magnitude improvement. So that takes us from where we were here to somewhere out here, E3 max 28 in this truncation scheme. But again, don't need to worry too much about what that is. You can just sort of see the results. And so if we're now able to look at something like TIN 132, here's the ground state energy, and here we can look at it in terms of a particular h bar omega, in terms of increasing that E3 max truncation. So here's where we were before. So if you wanted to sort of guess what the ground state energy would be, there's really no signs of convergence here by 18. But if we're then able to carry this out to kind of the limit, we get a very nicely converged ground state energy for TIN 132, not just for the ground state energy, but for the charge radius. And we've also done things like dipole polarizability and so forth, which is important for neutron star properties. So not just ground state energies, but excited states. We see the same sort of a question here in cadmium 127. This is our previous limit, and there's nowhere near a convergence, but when we're able to carry it out here, we see a very nice convergence. So we've now at least been able to move to the sort of TIN 132 region, which is excellent because that's where there's a whole lot of exciting nuclei for all of these beyond standard model physics questions. So that really kind of takes us to something like this. And even in this sort of shell model diagonalization limitation, we've been working with the Tokyo group. They have these very nice Monte Carlo methods that are available. And we're even hoping to remove that limitation in some sense. But you saw that TIN 132 is even quite well converged. And so then really kind of the holy grail of ab initio theory is kind of up here, lead 208. And we kind of asked ourselves, well, let's see what we can do. And it turns out that if we want to attack lead even, this is quite doable. And this is even an old, we even have a way of speeding this up more at this point. But if you just sort of, this I think it gives a quite amazing view of how actually great this progress has been. This E3 max 18 is where we were previously for a lead calculation. But now if we really carry it out here to the maximum, we're really able to extrapolate and get again, a converged calculation for the lead ground state energy. And again, we've been doing things like neutron skins, a lot of exciting things. Oh yeah, we have a plot of this where we've been working with other groups who use machine learning emulators and things like this, where we can really take these calculations as a starting point and really perform many billions of calculations, really exploring the parameter space of these chiral interactions. So just to show you where we are on the nuclear theory side, structure side. So we're now quite, this very heavy region is within reach, and just actually did this last night, looked at nuclei in this region because I don't know what's up there. But again, see some very exciting targets here for fundamental symmetry studies, mercury, francium, radium, things like this. So again, potentially within reach. But now, how would we actually take this advance in the structure side and apply it to these beyond standard model physics questions? Well, first of all, if we want to talk about dipole moments, antipole moments, we have to make sure that we're able to do basic electromagnetic moments first. So let's sort of take a look at how we do there. But even before getting to that, sort of the next natural operator that you would look at would be the radius. And just to show sort of the types of studies that we can do here, we can really look at radii across any given isotopic chain. Here we have the copper isotopes, which was a nice experimental collaboration that was just published last year, where we're really able to look at the odd, even, staggering. Here's our calculations across the chains and compare quite nicely with density functional theory type calculations. There's a similar study in the nickel isotopes as well. And again, there's really, as long as we're in the tin region, we can really do all of this. So moving from the radii to kind of the E2 transitions, here, the things don't look quite so nice at first look, because if we really look at E2 transitions across, say, the SD shell and compare with experiment, as this was done in a nice collaborative study with the Tigris group here at Triumph, we find that the IMSRG calculations, our ab initio approach, is always below what's measured. And of course, phenomenology has this fudge factor of these effective charges, which they kind of use to fit to reproduce data. So we're definitely missing some overall strength. But if you look at sort of the trend, it actually looks to be pretty nice. And this is kind of a busy plot, but you can sort of see, here, let's just look at these bottom panels here. Just in looking at, if you sort of decompose different parts of the E2 transition and compare sort of the theory to experiment, here's the ab initio, and here is phenomenology. And so you see that we're actually doing a better job sort of on a relative scale. If you take away this overall collectivity that we're missing, we're actually doing a better job reproducing the trends than phenomenology. So yes, we can't get the full strength, but we can definitely still learn something by looking at the trends. This is a plot I just wanted to throw in case anybody's interested for why we're missing this collectivity. But of course, now we can move, again, like I said, to any isotopic chains. And I'm guessing maybe we heard about this this morning from Jacek. Looking at the magnetic moments in the indium chain. Again, this is a very nice collaboration with laser spectroscopy experiments, really measuring these moments across the entire indium chain. And again, we see that we reproduce these trends quite nicely. And of course, even with the magnetic moments, we would expect some strength or some physics to be missing because we haven't included meson exchange currents yet. But again, we see that the trends are quite nice. And yeah, this is when we compare with density functional theory, we see that it's quite comparable. So I'll just kind of go through this a little bit quickly to get to the kind of the main points. So now that we at least have some handle on energies, radii, moments, things like this, I really kind of wanted to kind of lay out the strategy for how we want to start attacking beyond standard model physics questions where there isn't typically experimental data to inform us. These are really, we're kind of moving out on our own here. And so one of the best ways to sort of see how this is done is with neutrinos double beta decay. So the first step is we not just, we don't want to just go and calculate. We want to make sure that we're doing a good job all the way up to our final results. And so the first question is, okay, is there a similar process which is easier to calculate, which is out there? And in the case of double beta decay, yeah, it turns out there's this thing called single beta decay. And it also turns out that there's a long-standing puzzle, which on the order of, I'd like to say here, at least from papers in the 70s called a long-standing problem. And that's this question of GA quenching, where you really can just see it from this plot here. You can always tell how old the problem is by the quality of these types of plots. And it's really that theory just doesn't match up with experiment, and it's off by a pretty clear factor on the order of 0.75, 0.8. And this is what was always referred to as GA quenching. So of course, if we want to go and have a reliable calculation for double beta decay, we better understand GA quenching first. And so that's what we sort of set out to do. And this was a nice collaborative ab initio approach here with many different methods, attacking the light region, sort of this medium mass region, which we did, and even the heavy region with the couple cluster methods. And just showing the basic point here in both kind of the SD shell and the lower PF shell, when we included everything we need in sort of the systematic approach, so good description of nuclear forces, consistent electroweak interactions, including meson exchange currents, we largely are able to account for this GA quenching. So we're basically able to get good agreement with experiment without touching GA. Again, it's not perfect, but again, we're not doing a perfect calculation just yet. So that's step one. If there's something else out there, let's do it. And so we did that with GA. Step two is benchmark where we can, if we can, in light systems where we have these quasi-exact methods available, such as no-core shell model or some variation. And so this is what we did with neutrino-less double beta decay. Again, just showing very, very quickly, just want to give you the idea here. Comparing with sort of these fictitious decays in light systems, which could be done with no-core shell model. And in all cases, we see quite a reasonable agreement up through sort of oxygen 22, which is really the limit of these types of things. So that's good. So benchmark where we can in light systems, so we know we at least have a handle on the many body physics. And then finally move to our principal final cap. Yep.
25. Yep.
5. Perfect. Really kind of moving to the sort of final calculations. And here the important part is with uncertainties, and this can often be as hard, if not more difficult than the actual calculation. But just to show that what we have for neutrinos double beta decay using a number of input 2 and 3 body Hamiltonians, we're really now able to get really have someone's handle on the uncertainty from the interaction side. And really then produce calculations, converge calculations for really the most important target nuclei for the search, germanium-76, tellurium-130, and xenon-136. And we're really able now to contribute really an ab initio band to this sort of typical matrix element plot that's ubiquitous in the field. And so the final step is to then make sure or compare, if available, with other ab initio methods. And so that's what we have here in calcium-48. There's 2 other methods, and we all agree well within uncertainties. So then again, we might expect that if when these other methods are able to calculate out here, that we would also agree within uncertainties. But again, this is something that has to be undertaken. And of course, go back and think about if you're missing any physics, which we are here because there's this contact term, which we're isn't included yet. So these aren't final, but just to show that we can really reach this, this region with converged calculations. Yeah, the point here is that our final results are actually quite different than sort of the accepted value, or sort of this accepted band that has been out there. So that's somewhat of a cautionary tale. It's difficult to know exactly where the final ab initio results will come up, because the spread here in these results is not an uncertainty at all. So we know that there's physics missing in all of these, so there's no reason that we should lie within that band. So, and here we typically don't. So now if we look at another type of question here, the WIMP nucleus scattering, again, I'm just going to show our final results. Again, we really have convergence in all. Here we're looking at spin dependent WIMP nucleus scattering, the structure functions for all the nuclei that are used in these searches worldwide, really up through Xenon 130. And again, these are all converged in the many-body, many-body approach. And here we see that there's not too much different than the existing phenomenology. In a couple cases, say sodium here, we see some differences at low Q, low momentum transfer. But again, I just want to use this to sort of illustrate what could happen either way. We can either, of course, see some big differences, or in the case of WIMP nucleus scattering, we have quite similar results to what's been out earlier. Yeah, and so now applying this approach to the symmetry violating moments, yeah, which is why we're all here. Please stick around for another hour or so and see the talk of Takayuki Miyagi, who's been working very hard on this, and also a lot of what you've seen here. Really do a tremendous job. And just to sort of wrap up here, would just like to say that we've also been kind of extending this our ab initio approach to atomic systems, because again, for these laser spectroscopy experiments, we need these isotope shifts, which so far are not terribly well determined theoretically for many systems, and typically can only be done again for kind of closed shell atoms. But with this valence space approach, we can really, in principle, attack all atoms, well, most atoms, I guess. Yeah, so not just for these isotope shifts, but also there's very exciting ways to get it beyond standard model physics by looking at things like these King plots and such. So there's, I think, a very nice opportunity. And just to show very quickly what we've been up to, just going to flash a couple results. We can now do ground state energies. Here we have the helium ground state and neon ground state, where our results will typically agree with kind of the best, in quotation marks, kind of couple cluster calculations that are out there, which can handle doubly magic systems. And so that's quite nice. But here we see a neon that we still diverge, or we still don't agree with experiment perfectly. And that is kind of a hint that we're kind of still missing relativistic effects, which is something that's in progress. We can look at binding energies of open shell atoms. So here we have 2 electron systems, magnesium and calcium, where again, there's some ab initio out there to compare with. And again, here we typically agree with the best that's out there, which is sort of this line up here. And yeah, this is sort of increasing that many-body basis size. But then there's no reason, so now we at least have some confidence there, and we can then go out and look at systems for which there is, to our knowledge, is no real ab initio calculations been done. So really looking at really now whole periods of atoms here. So period 3 ionization energies, period 2 ionization energies, where all we have is experiment to compare with. And again, when we get up here, we would expect relativity to become important. And finally, yeah, we do have some isotope shifts as well. But so far, these are only been kind of benchmarked in very light systems. So these are the isotope shifts for lithium. So just wanted to kind of throw that out there and have them in the slides in case somebody was interested and wanted to check that out. Of course, you're free to ask many more questions about it, but this is really all the nice stuff we've been up to. And this is just a preview. Takayuki will be, I think, talking about what we're really interested in. So thank you.
Thank you. Thanks, Jason. Again, please, if you have a question, type an exclamation mark in the chat. Okay, while people think of questions. I have a comment and a question. If you go back to the double beta decay chart. So I just wanted to point out that recently, Wirth, Yao, and Hergert have included in calcium 48. So using an estimate from myself and my collaborators on the contact term, they seem to find an increase in the matrix element for calcium 48 of about 42% plus or minus percent. So that I have no idea whether that will be across all nuclei, but that's, at least for calcium, it's good news. So that's the comment. And the question is, do you have a sense of why your ab initio result lie on the low end of those ranges? You know, never mind those ranges, but do you have some intuitive explanation for that?
Yeah. So to kind of on the first point there, we're actually one of my student here, Antoine Belly, he's actually, just started as a master's student, but he's really been pushing this. Yeah, we have been implementing the contact using the information from Heiko in his group. And yeah, we should have that implemented and really included throughout all of these calculations, I don't know, within a month at most. It should already pretty much be done. There's just one question on agreement with matrix elements. So either they made a mistake or we did. But yeah, that's definitely in there soon. And in terms of the disagreement, I think the general consensus is in a lot of these sort of phenomenological models at the high end, there's always this question of the physics of the single particle space versus the physics of correlations. And these methods that are at the high end typically will work in a somewhat larger space, but not, but only include correlations in a very schematic way, I would say. And so there've been studies that show as you kind of increase the correlations more, that typically that tends to bring down the matrix elements. So in this sense, I would expect these results to be much more comparable with the sort of shell model type results, which they typically are. They still might be a little bit on the low end, but yeah, that's, I think, a very hand-waving way why they're on the low end.
Can I comment on that?
Please. Yeah.
I think probably some of the physics of GA quenching, which was never clear how much it would affect double beta decay, is in there too. Correlations which are responsible for quenching beta decay have some effect there also.
Yeah, I guess I'm never even sure if if these things like the EDF or the IBM put in some quenching for their double beta decay. Or if they don't already.
For the neutrinoless, they generally don't put it in.
Okay. Yeah. Okay. Yeah. So then that would also be an extra 30% or so.
There's two more questions. So please go ahead.
So, hi, Jason. Very nice talk. I don't understand your strategy for your input. So quantified interactions. You are talking a lot about many-body methods and how can you crank, calculations for heavy nuclei. But what makes you believe that the interaction which you use for very light systems, Nn plus 3n force, will work for radium?
Yeah, that's of course a good question. And ideally, what we would like to do is pursue chiral effective field theory in the way it's meant to be pursued, which means kind of order by order, and at each order, regardless of your fitting strategies, you should have some uncertainty from that, however it's fit and determined. And so of course, as you go to higher orders, they should all, these uncertainties should shrink, and these error bars from different strategies should ideally sort of overlap with each other. But of course, we don't have that yet. The best that we have is really what's out there. And so that's sort of what we've tried to do, is take really the workhorse interactions that are out there on the market for something like neutrinoless double beta decay to get some spread. But also, I guess, I would say kind of the proof's in the pudding sort of answer. I mean, if we're getting a converged calculation of lead that's within a couple % of the actual ground state energy. And we see that it really works across the chart up to lead. That's, again, it's not, these should all have some uncertainties on them, but you know, if it works, it also works. But we also know this interaction that does well for ground state energies doesn't work well for radii, and so this is really something that we kind of have to.
So I'm just afraid, Jason, that you might end up with having series of interactions, which will be in a way mass dependent, because as you go to heavier nuclei, the impact of many body forces, which go beyond 3 body forces, will increase. So you have to mock up, you know, those missing forces by changing low energy constants, right?
Yeah, well, I guess that kind of would remain to be seen somewhat. Yeah, because we can sort of test whether, yeah, we can sort of test, because of course we do this normal ordering procedure for including the 3 body forces, and we can at some level really test the importance of what's being thrown out. We kind of this residual 3 body forces. In principle, we could do the same for 4 body forces. It's certainly something that would have to be looked at before we can really claim some really final results for sure. But I think as far as I have seen, at least for ground state energies, that could be totally different for other observables. Typically what's neglected is not terribly important. Again, this could be totally different for lead. Yeah. So again, it would be something we'd have to look at for sure. So.
Thank you. Thanks, Jason. So I think we're out of time, so I'd like to close this part of the session. Thank you, Jason, again.
Thank you.
So we're supposed to be on a break, 10-minute break. We reconvene at 3:25. However, I'd like to ask the organizers to open up the 2 breakout rooms, 1 and 2. So Wick can go to room number 1, Jason to room number 2, and I know there's more questions for both of them. So please, if you have questions, let's go to the appropriate room. Thank you. So I don't have the ability to open.
So yeah, Nick will open the breakout rooms in a couple of minutes.
I think they're already open, right?
I'm not seeing that on my screen.
Let's see, yeah.
So do you have the ability? So Nick, are you online? Let me ask. So I think what we recovered.
I have a dangerous button. Yeah, exactly. Okay, wonderful.
Okay, super. Yeah.
Thanks.
Okay, the breakout rooms are open.
All right, so welcome back, everybody. So we start the second part of the session, and the next speaker is Peter Navratil. He'll tell us about no-coercion model calculation of PNT odd, PNT violation nuclear properties. So Peter, go ahead.
Hello, good afternoon, everybody. Can you see my slides?
Yes, in full screen now. Thank you.
Okay, so let me thank the organizers for giving me the opportunity to present here these calculations. So in particular, I'll be talking about ab initio calculations of electric dipole moments and anapole moments in light nuclei. And in particular, in the EDM calculations were done in collaboration with Paul Froese, my student from UBC. Okay, so I have a little bit redundant introduction for this workshop. So why investigate the electric dipole moments? So there are unsolved problems in physics like the matter and antimatter asymmetry of the universe. The standard model predicts some CP violation, but it's not enough. And so the EDM is a promising probe for the CP violation beyond the standard model, as well as the CP violating QCD theta bar parameter. As we know that a non-zero EDM of any finite system requires both the parity and time reversal violation, and this implies CP violation through the CPT theorem. It's going to be illustrated, for example, in the case of the neutron. So now with the neutron EDM, it's small, so one can look alternatively at nuclear EDM because the EDM can be enhanced by nuclear structure. And also nuclear EDMs can be measured in storage rings, so there are some envisaged experiments to do that. Obviously, to understand the nuclear EDM, we need to understand nuclear structure effects, and so that's where the ab initio nuclear theory comes in. Also, I'll be talking, as I said, about the calculations of parity violation. And so these are important tests of the standard model because they inform us about the parity violating nuclear forces, and also about the physics beyond the standard model because the atomic parity non-conservation is sensitive to different kinds of new physics. For example, it measures the model-independent electron-quark electron-weak coupling, and also it puts limits on some beyond the standard model particles like the Z prime boson. So the parity violation in atomic and molecular systems comes in as spin-independent effects and spin-dependent effects. So I will focus really on the spin-dependent effects only, and in particular this diagram B and C. So the B is the Z boson exchange between the nucleon axial vector and the electron vector currents. And the B diagram is the electromagnetic interaction of the electron with the nuclear anapole moment. So there are actual experiments proposed to measure nuclear spin-dependent parity violating effects in polyatomic molecules, and in particular is light or the three atomic molecules, so that include light elements like beryllium, nitrogen, carbon, and magnesium. And so one interesting thing about these light atoms is that the exchanges of the standard model Z boson, that is basically on this diagram B, can be comparable to the anapole moment contribution to the parity violation, unlike in the heavy atoms where the anapole moment dominates. And this particular diagram is poorly characterized, so is then very valuable to these kinds of experiments. And in general, to extract the underlying physics that we are interested in, one needs to do atomic, molecular, and nuclear structure calculations so that to understand these effects. And so again, this is where the ab initio calculations come in. So I will focus on the nuclear part. So this was the nuclear ab initio theory was covered in the a bit in the talk by John Engel, but then in more detail by in the previous talk by Jason. So ultimately, what we would like to do is to go from the quantum chromodynamics to the structure of complex nuclei, but that's not feasible. So when we talk about ab initio nuclear theory, we really mean like a two-step process where we work with the nucleons as the degrees of freedom, and the interactions between the nucleons are then obtained from the QCD by means of the chiral effective field theory. With the parameters like the low energy constants really fitted to experimental data. And then these interactions are then serve as an input into the many nucleon Schrödinger equation that we solve to predict the properties of atomic nuclei. Again, the chiral effective field theory is the tool that allows us to derive the nucleon and higher nucleon interactions from QCD. So this was again shown here a couple of times. So the main idea is that this chiral EFT works with the degrees of freedom that are nucleons and pions, and the symmetry is based on the symmetries of QCD, and in particular the chiral symmetry is a very important one. So the nice thing about this theory is that it gives us a hierarchy and consistency of the forces. So hierarchy means that, for example, the 3-nucleon force comes at higher order than the 2-nucleon force, and then the consistency means that the low energy constants or parameters that enter the 2-nucleon force also enter 3-nucleon force, and so on. So again, at the moment, these low energy constants are fitted to the nucleon or few nucleon data. In principle, they can be calculated by lattice QCD. So I will be working with the method which is called no-core shell model. So it was mentioned briefly by Jason. So this is like a conceptually simplest ab initio method. So it's a basis expansion method, and the basis that we use is the harmonic oscillator basis, which is truncated in some particular way with this parameter Nmax, which characterizes the total number of excitations above the lowest allowed Pauli configuration. So one can ask obviously why harmonic oscillator basis. So one reason is that it's a kind of reasonable basis for light nuclei, because as we know, the lowest field harmonic oscillator shells match magic numbers of light nuclei like helium-4, oxygen-16, or calcium-40. But also there is a good mathematical reason, because it gives, it allows us to perform these calculations with this Nmax truncation and still preserve the translation invariance, even if we use Slater determinant basis, that means single particle coordinates. So there is a total equivalence between the calculations in Jacobi coordinates and Slater determinant single particle coordinates, which is quite useful. So for these calculations that I'm discussing here, I will be using one particular chiral nucleon plus nucleon interaction, which, I mean, I'm talking about the parity conserving and time reversal conserving interaction. So this is the interaction that was discussed in this paper from last year in PRC. And so it consists of a 2-nucleon interaction constructed by Anton Machleit in 2003 at the N3LO order, and the 3-nucleon interaction, which is at N2LO and has a combination of local and local regulators. So the Hamiltonian is fully determined in few nucleon systems. That means it's fitted to the nucleon scattering data, to deuteron properties, to the triton helium-4 binding energies, and the triton half-life. But then this interaction is then applied across the nuclear chart. And so I'm showing the calculations. So this is was published in this paper. So these are the ground state energies of selected light nuclei. And on the right is the ground state energies per nucleon of medium mass nuclei from oxygen to nickel. And so the light nuclei were done in no-core shell model. The medium mass was done in the self-consistent Green's function method by the Sackler group. And you can see that actually it works quite decently for all the studied nuclei. And actually now we have also results for tin 132 that the calculations were done by Takayuki Miyagi with this Hamiltonian. And again, it's basically spot on compared to the experimental ground state energy. So that's, I kind of consider it quite remarkable that, you can start with an interaction which is determined just in these few nucleon systems, and then it actually works without any overbinding or underbinding, across the chart. So now I'll be showing these results for the parity and EDM and parity evaluation and nuclear EDM. So in particular, I will be calculating the properties of these nuclei that play a role in this 3 atomic molecules. So it's beryllium, carbon, nitrogen, magnesium, and the nuclear EDM. So then I calculate for just the stable nuclei, starting with helium-3 and then going including the nitrogen, the fluorine 19. And so here in this figure, I highlight some of the ground state energies of some of the nuclei that are then used for the EDM calculations and the parity evaluation calculations. And on the right, you can see the quality of the excitation energies for the beryllium-9 and carbon-13 as an example. So overall, this Hamiltonian provides a quite decent description of this light and also medium mass nuclei. So in general, these are kind of large-scale calculations. So this was done mostly in Oak Ridge on the Summit supercomputer. In particular, now we have the code which has the GPU acceleration. So that's very handy in these types of calculations. So now if you just focus on the first thing is to calculate the one-body contributions to the nuclear EDMs and also let's say this boson exchange and nucleon axial vector electron vector current. And so this can be done in a straightforward way by just calculating a matrix element of the operator that I show here. So for the nuclear EDM, it's just basically like a sum of the contributions from single nucleons, and so the dp and dn will be intrinsic nucleon EDMs, and the C is the ground state wave function of a given nucleus, and actually is the one which has the maximal projection of the spin. And so we just calculate this matrix element to get the EDM contribution, and similarly for this the boson exchange. So it's a very much this similar operator. So we use the spin operator matrix element to get this constant that characterizes this contribution. So it's just given as a sum of the proton and the neutron spin matrix element with some constants which are determined from the standard model. But now the more interesting contributions are due to the parity violating nucleon interaction, or parity violating and time reversal violating nucleon interaction that can then induce induce a polarization that then leads to these parity violating moments. So there are two possibilities or two options at the market how to describe the nucleon interaction, which is parity violating. And so one is the traditional meson exchange approach. So this is the so-called DDH interaction from the seminal paper from 1980 that I show here. And then the more modern approach is the chiral EFT And so there is a review paper that was published just summer 2020. So it's quite new. So obviously these interactions involve unknown parameters, again, like the low energy constants. And so in this DDH potential, they were estimated on the quark model. Obviously, one would like to do some experiments to constrain these parameters. And actually now we have two high precision experiments that were just published last year, where they can constrain these these parameters. So one of them was the N helium-3 capture, and the other one was the NPD gamma. So similarly, now if we want to look at the EDMs, then we need an interaction which is also time reversal violating. Technically, it's very similar to this DDH interaction, as long as we stick to this meson exchange picture. So it looks very, very similar. And so I'll be using this particular form of the interaction. Again, it has Yukawa terms, and it's based on the exchanges of the pions, omega and rho mesons. And it has the isoscalar, isovector, and isotensor contribution. And then there are these G bars, are the coupling constants, which are obviously unknown because EDM has not been measured. But these are the quantities that we would like to determine from experiments. Okay, so now this parity violating, time reversal violating interaction will induce parity admixtures to the ground state. And if we use just the second order perturbation theory, so then this can be done in a straightforward way. So you can see you start with a ground state, which is the parity conserving with from the parity conserving Hamiltonian, which has the natural parity, and then the parity violating interaction will then mix the states of the opposite parity, and this is then the contribution from second order perturbation theory. So basically you have to expand over many excited states, and to calculate, for example, the EDM, then we just sandwich the electric dipole operator with this wave function, which has the admixture. Right, so it's straightforward, and now because of this denominator, then one can have an enhancement that was obviously discussed at this workshop several times, that can get an enhancement from nuclear structure if these unnatural parity states are close to the ground state. So now the same, obviously, so before it was for this parity violating, time reversal violating, so I have the same for this parity non-conserving only interaction. So it's exactly the same story. And so now if I want to calculate the anapole moment, so now the operator is different than for the EDM. So I will actually be using only the spin part of the anapole operator, which is the dominant part. So it has the structure of the R cross sigma, and the mu I are the magnetic moments of the proton and the neutron. And so the anapole moment is the matrix element of this operator in the ground state, but now the ground state contains obviously these admixtures from the unnatural parity states, which are then obtained again using the second order perturbation theory. And ultimately what we want to calculate is this kind of dimensionless constant Ka or parameter Ka, which we can then compare with other calculations. So this is kind of my master equation that I want that I use for the calculations. So now, obviously, you can see that now I have like a very large number of excited states which have unnatural parity. So it looks like a very complicated calculation to include all these excited states, and also they will be like in the continuum and so on. So it's very non-trivial. However, we do not actually have to sum all these intermediate states as it is written here. What we can do is actually to solve the Schrödinger equation with an inhomogeneous term, where the inhomogeneous term is given by the ground state with the good parity on which this parity non-conserving interaction acts. And now we invert this equation, and we do that by application of the Lanczos algorithm. So the Lanczos algorithm is something which brings a matrix to a three-diagonal form. So one starts from a vector, let's say V1, which is called the pivot. You apply Hamiltonian on it, and then the result is then split into the original vector and the vector which is orthogonal to it. And then you repeat the process, and if you apply it on the vector V2, then again, we will get a vector V3. But then when you apply it on the vector V3, then you don't get any contribution from V1 because the Hamiltonian is Hermitian. So then, from the first line, one can see that there cannot be a contribution from the V3. And so in the end of the day, this brings the matrix to a three-diagonal form. And why is this interesting is that we can just repeat this process a few times to converge to the extreme eigenvalues by diagonalizing these three diagonal matrix. So basically, even if the dimension that we work with is, for example, 1 billion, we can still get away with about 200 iterations to get 10 lowest eigenvalues. So this method can be also applied for this inversion that we are interested in here. And so in this case, we use the pivot. The pivot is now this ground state with a good parity, on which we apply the parity violating nucleon-nucleon interaction. And so now then we apply the Hamiltonian on this V1, and then so build this all the set of these vectors, the Lanczos vectors, and then there is basically like a recipe how to get this ground state which has this parity admixture, and all the details are given in this few body paper. Okay, so now let me come to some results. So first, I will discuss the benchmark for helium-3 for the EDMs, for the EDM of the helium-3. So this has been obviously calculated before for different nucleon-nucleon interactions, and in particular, there was a calculation also done based on the no-core-shell model. It was published in PLB in 2008. And so there were several interactions used, and in particular also this N3LO by Entem and Machleit from 2003. So I'm showing results for that interaction. But interestingly, there were several other calculations of the same system, some of them using the same interaction as in this PLB 2008, and then they found or claimed that that they found results which were like a factor of half different than in this paper. And actually, in this PRC from 2013 by Lazauskas and collaborators, so they found factor of 1/2 for the isoscalar isovector, but for the isotensor they found 1/5. But then there was a paper by Yamanaka and Hiyama, and they found a factor of 1/2 across the board from all these contributions. And so now, when we did our calculations, we then used the same interaction as as in this PLB 2008, and indeed we confirmed that the factor of 1/2 discrepancy with this paper. So now our results are consistent with these by Yamanaka and Hiyama. So it obviously that kind of gives us confidence that what we do is okay, and now we can proceed to heavier nuclei. So here I'm showing just the convergence for these pion exchange terms as on the size of the harmonic oscillator basis, and it actually works pretty well. So the same, okay, not the same, but now the convergence for the anapole moment calculation now for the p-shell nuclei. So this is for beryllium 9, carbon 13, nitrogen 14, nitrogen 15. So you can see again dependence on Nmax. So now I'm showing this quantity on this parameter Ka that I defined before. So these results were published in this PRA last year. And the dotted lines or the lines are the results are these single particle estimates. So overall, we can see that this NCSM calculations give quite reasonable convergence, and also that an absolute value over the Ka is somewhat larger than the single particle estimates in many cases. So here in this table, I'm basically, okay, so this is basically the table reproduced from this paper. So that shows the results for the Ka for these nuclei of interest. Also, it shows this Kax, which characterizes the Z boson exchange contribution, which I discussed before. It's calculated from the matrix elements of the spin operator of the proton and spin of the neutron. And in addition, I'm also showing the magnetic moments. So that you can see, basically magnetic moments have been measured in all these nuclei. So we can kind of gauge the accuracy or the quality of the NCSM calculations by comparing the magnetic moments to experiment. Basically, again, the magnetic moments are known to be affected by two-body currents. Those were not included, so this is just with the one-body operator, but that's kind of also consistent with what is done for the anapole moments.
Peter, you've reached the 25 minutes.
Okay, so I'm finishing. So now this is the summary of results for the EDMs for the nuclei, for the stable nuclei from P-shell and also for the fluorine-19. And so now what is interesting about this, okay, so these are contributions for the isoscalar, isovector, isotensor for the pion, rho, and omega. And what is kind of interesting is that you can see that different nuclei will give different types of contributions for different terms. So for example, the boron 10 gives a very large contribution for the G, this isovector pion. It's actually twice as large as the deuteron contribution, while, for example, carbon 13 gives a good contribution for the isotensor. The fluorine 19 also gives a very large contributions. Again, the reason is that there is this doublet of the near the ground state of the 1/2 plus 1/2 minus. So overall, this kind of looks like that. If one would be able to measure several of these nuclei, one can kind of map out the parameter space of these parity violating, time reversal violating interactions. Okay, so since my time is up, so I will finish just by showing my conclusions, and be happy to answer any questions that you might have. So thank you.
Okay, thank you. Thanks, Peter. Do you have questions? Please type the exclamation mark in the chat. So there's Dave, please go ahead.
Hi, Peter. Thanks for a very interesting talk. So I was curious, I think you and Jason both mentioned that two-body currents are known to give significant contributions to magnetic moments, and they haven't been included in either of these calculations. I'm curious, how hard would it be to include those, and will those have similarly large contributions to things like anapole moments or EDM calculations?
Yeah, so I think that, so in general, it's obviously technically challenging, but it's possible, definitely. I mean, Jason showed these results for the, for the Gamow teller, where we included the two-body current, so it's definitely doable. So for example, for the E1, at least for the electromagnetic part, it's included, the two-body current is included through the Ziegler theorem. Overall, I think, it's kind of has been observed in the few nucleon systems that these two-body currents are less important, or let's say are sub-leading. But yeah, in principle, they should be included, and it is, I think it is feasible. But even, for these M1s, it's known that they play a role, but still, it's again a subleading effect in some nuclei. In some of the nuclei, it's really negligible. Like, for example, in lithium-6, it's known that it has like very little effect.
Okay, thank you. Is there any other questions for Peter? Jordi, please go ahead.
Yeah, I was wondering, I've been out of this for a while, but the storage ring experiments, can they actually do something like fluoride 19, or is that too heavy and this is more like for theoretical interest?
Yeah, okay, so I think I'm not the right person to ask. So, yeah, so I know that they plan to use helium-3, right? Deuterium helium-3. So I don't know if it's feasible to go beyond that. I'm hoping it might be. So perhaps if there is a good motivation, then something can be done. But again, I'm a theorist.
So maybe my other question would be, can you use these intermediate nuclei, even if they're not direct of experimental interest, as some sort of, if you can do this from ab initio, and then maybe other many-body methods can use then these fluoride 19 results as a benchmark to see if they agree with these methods, and then they can go up the chart to heavier systems.
No, exactly. Yeah. So this is, again, so Jason kind of showed what was done for the double beta decays, right? So we used the Korshell model to benchmark the, for example, the coupled cluster, also the calculations for the double beta decay. So I think that exactly. So this is kind of a good contribution where, these calculations for light nuclei, where we have more control, can be used to help with the heavy, the calculations in more complicated systems.
So in that light, would it be interesting to also study the shift moments of these systems, because that is maybe more appropriate than for this matching to the heavier systems?
Yeah, of course. It's just plug in a different operator. So yeah, technically, I think the most challenging part is this this kind of Lanczos algorithm, where you sum up all these excited states, and then we can use obviously a different operator, to sandwich. Yeah, so there's no problem. Yeah, but okay, I have not done it, but it can be done for sure without any much trouble.
Okay, are there any other questions or comments? All right, I don't see any. Let's thank Peter again, and we go to the next talk. The next speaker is Takayuki Miyagi, and we'll hear about parity evaluation in atomic nuclei. Takayuki.
Thank you. Do you see my screen?
Yes.
Okay, great. Okay, so first I'd like to thank organizers for giving me opportunities to talk about my recent works. So today I'm going to talk about the recent my calculation about the parity vibrating moments of finite nuclei using the Barron space IMSRG, which is already Jason introduced. And yeah, I'm showing some results, benchmark results against Peter's no-Gaussian model calculation results. Okay, so let me start this slide. So again, these precise measurements can provide us the precious opportunity to explore the new physics, and it's also complementary with the collider direct production of the unknown particles. So precise measurement basically can, in the precise measurement, we detect the signals of the unknown process, and hopefully the many-body correlation could enhance the signal. Okay, one example I want to look at is the anapole moment, which is defined like this. And the topic here is that in this plot, so in this plot, the horizontal and vertical axis is the some combination of the coupling constant of parity violating meson exchange potential. And here, as you see, all the experiments for Fluorine 1819 and Proton alpha scaling overlap each other here, but the anapole moment of cesium-133 is doesn't overlap. So I think there is some room of the more looking into it using the ab initio calculations. So particularly this cesium-133 is only one experimental value, one experimentally known finite anapole moment. The other example is the electric dipole moment. The operator is given here. As already discussed many times, this operator breaks a parity and CP symmetry. And for any finite systems, only upper limits are currently known. But since this could explain the origin of matter-antimatter symmetry in the universe, so we are definitely interested in this EDM. And the possible source of this additional CP violation is this, might be a safe term in the QCD or beyond the standard model. So as I already mentioned, the many-body correlation might enhance this parity violating observable. So taking this EDM as an example, let me briefly show you how this could be enhanced. So this nuclear EDM can be written like this. So just individual contribution coming from proton and neutron and nuclear polarizations. So these two terms cannot be enhanced because the proton neutron are usually preferred to pair up with spin 0. So the possible enhancement can be appear for this nuclear polarization. So since we have already known that this parity violating component is tiny, we can do the perturbation theory, and at the leading order, I could find this expression. And as already have seen in this workshop many times, we hopefully find enhancement of this factor. Okay, so in the atomic nuclear, how it can be enhanced. So naively, the most naive case is just going heavier because just simply if the size of the system gets wider, then the single particle levels get denser, then naturally we could have the smaller excitation energies. And actually, because of the saturation property of finite nuclei, it's guaranteed that size of nucleus grow proportional to the A to 1/3. And the other example might be more specific nuclear structure, like here I am showing the alpha cluster. So here I am showing the energy spectra of the fluorine 19. The ground state is just 1/2 plus, and we see some nearly degenerated 1/2 minus states. But in the naive Schermuller picture, this is pretty weird, because in the naive Schermuller picture, the ground state is something like this. So the up to P3 half is completely occupied, and in the SD shell we have 1 proton and 2 neutrons in the ground state. To get excited state, we have to have some excitation from P3 to the probably D5, but the energy gap between this P3 and this D5 should be experimentally 6 MeV or something. So it is pretty unnatural to have this kind of small excitation energy. But once we have realized that alpha cluster is tightly bound, and just consider the excitation state as the alpha plus nitrogen 15 system, it could be explained. So the because of this alpha-like correlation, sometimes the excitation energy could be lowered. And of course, the deformation can be deformation can enhance this factor. So my goal is to calculate the these EDM monopole moments starting from underlying nuclear interactions. So the Hamiltonians are sort of established since there is a chiral EFT, which can provide a systematic way to build up the nuclear interactions. And also we have several options to solve the nuclear Mandelbrot-Schrödinger equations. Like as already introduced by Peter, there is a no-question model and BS balance space IMSRG, which is also introduced by Jason. So this is the our typical workflow. So our task, ideal task, is to solve the nuclear Mandelbrot problem starting from this Coulomb degrees of freedom. But at the moment, it's pretty difficult because of the computational costs in the city. So the alternative path at the moment we can take is bridging these two gaps using the chiral EFT and solving the Mandelbrot problem associated with the nuclear degrees of freedom. So in this process, I'm going to use the IMSRG. So just quickly remind you the chiral EFT. So the chiral EFT is the low energy effective field theory of the QCD, and in this framework, the nuclear interaction can be expanded order by order, and of course the unknown low energy constants can show up, which should be fitted to the existing experimental data, such as the nucleon scattering or light nuclei binding energy or something. And this chiral EFT framework naturally explain the many-body hierarchy, and also hopefully we could estimate the truncation error of the EFT expansion. So this is all derived in the parity conserved, time reversal conserved sector, but we could do the parity variety sector in the same way as given in this paper. And these are typical diagram in the parity birated but time reversal conserved sector and the PT birated sector. As I mentioned, there should be unknown additional low energy constant should arise. And in case of the parity validated sector, we should have like this, and for the PVTB, we have like this. So these all unknown. So for example, the nuclear EDM should be written in terms of these unknown low energy constants. And our task is actually to compute the coefficient of each low energy constant. So our task is to calculate these A coefficients. So just give you the imagination of the connection between the chiral EFT potential and meson exchange potential. Obviously the at the low momentum transfer limit, the heavy meson effect can be mimicked by the contact term. This is just making sure that I am coded correctly. So here I am showing the EDM of deuterium, tritium, and helium-3 using this usual sector potential, and here's a deuterium results. So this NC, here I am using the NCSM because I can do. So the reference are taken, the literature value are taken from this reference. And it looks like totally consistent except for this C3, C4, helium, tritium 3 and helium 3. I believe this is just a labeling issue, I think. And I also benchmarked the parity validated DDH potential for using the anapole of this spin current term, which is also was discussed by Peter. And this my calculated value is also somewhat reasonably agree with the literature value. Okay, so now I have the chiral EFT for parity validated sector, usual sector and the parity validated sector. So the next thing I have to worry about is how to go in heavier system using this Barnes INSRG framework. So as already Jason introduced, we try to decouple the valence space and outside of the valence space using the approximate unitary transformation driven by this Floer equation. Of course, we during the unitary transformation, the many body term can be induced, but we at the moment we are only keep up to 2-body level. So discard the 3 and 4 body for terms. So just give you the imagination of the how we solve the Floer equation. This is an example of Neon 20. So this is a diagram of the just nuclear shell model, and here I take these orbitals are core, and these red orbitals are valence space, and the above are just outside of the valence space. And in this box, I am showing the zero body energy as a function of this flow parameter. And if I increase this flow parameter, then the off-diagonal term given here, shown here, could be should be expressed. So if I increase this S, then this off-diagonal component can be suppressed by the unitary transformation, and problem could be exactly approximately mapped into the smaller Barren space problem. Okay, so the so usually, again, I am showing the nuclear shell model diagram here. So in the usual typical shell model calculation diagonalization, we are taking the single major shell, which is this just N0, 1, 2, 3, or 4. We are taking only this N equal 1 or 2 as the Barren space, but the parity of these single particle states are just comes like negative, positive, and negative, positive. So to calculate the unnatural positive state, which is obviously needed for the calculation of the parity violating moments, we have to extend our Barren space. So here I'm showing the Barren space variation. So P shell is just taking this N equal 1 case. In this case, sorry, I forgot to mention, but here I'm showing the oxygen 16 excitation energies. And in that case, I can only have the ground state, but by adding the D5 and S1/2 to my Barren space, I can calculate the unnatural parity state as well. Okay, next thing probably I have to worry about is the contamination by the because of the center mass motion coupling. So there is a prescription to separate this sort of sphere center mass motion. The prescription is that prescription is to add the center mass Hamiltonian defined like this with some coefficient of beta. So if we keep increase beta, then eventually the center of mass wave function can be factorized as Gaussian. But there is an issue in IMSRG that if we add the center of mass Hamiltonian with too large beta, then the IMSRG, the many body hierarchy in the after the IMSRG evolution breaks down sometimes. I am showing the typical example of breakdown the IMSRG hierarchy. So here P shell, here I'm showing the oxygen 16 ground state energy as a function of this beta coefficient of the center mass Hamiltonian. If I start with the P shell, this is just a single measure shell calculation, that's fine. And adding the D5 S1/2, this also looks fine. But if I take the free PSD Barren space as my Barren space, then the energy goes crazily negative if I increase beta. If I look at the expectation value of center mass Hamiltonian, which is positive, which should be a positive limit to quantity, this center mass Hamiltonian expected value goes negative, which means that the strong three or four body terms are strongly induced during the IMSRG evolution. So to avoid this problem, I have to tune or optimize Barren space. Okay, so this already mentioned by Jason, but recently we developed a new storage scheme for the three-body matrix elements. And here I am showing the, so this is actually the plot Jason showed, same one. And that our basic scheme allowed to store like up to 18 in this particular truncation scheme. And this just gives us the ground state energy of wedge 08 like this. So we can do up to here. And looking at this, we don't know, we have no idea where it's going to converge. But just introducing a new storage scheme of the 3-body matrix elements, then we can do up to 28. And eventually we can get the convergence even in the lead-208 ground state energy. So now the applicable region of the Darwin issue hopefully can be extended up to like here. Okay, so now we are sort of ready to apply the VSMSRG calculation for the parity variating moments. But before doing that, I have to benchmark using the VSMSRG calculation. So let me start with the simplest case, deuteron. Here I am calculating the EDM of 1 pion isobector term using these potentials. And so the point is that I am So in this plot, I am showing the this plot. The horizontal axis is the excitation energy of the deuteron, and this bar indicates the contribution at the energy, and these curves are just a running sum of the components. So in the above plot, I am showing the XCI results, and in the bottom, the VSMSRG2, VSMSRG. And so since the Barren space cannot fully capture the cannot reproduce the full spectra of the FCI space, so we have to push up the center mass contaminated states. So by keep increasing this beta mentioned earlier, I can push up the this center mass contaminated state, and eventually I can get the results fully consistent with the this FCI result. So so the message is that I need to increase the beta until we get the convergence. Then I can move to the something a bit heavier, like nitrogen 15. And again, I am using these potentials, and here in the Barren space, I am not calculating all the unnatural partner states because of the computational limitation. So I have only calculated the 200 intermediate states. And from the top, I am calculating the isoscalar 1 pion, isobector 1 pion, the isotensor 1 pion. And in the bottom, this is the anapole spin current term.
So Takayuki, you reached 25 minutes.
Okay, yes, I'm almost finishing. So a good thing is that we can find almost the beta independent results. You know, if I increase the beta, then all the panels, I can find the sort of beta independent, almost beta independent results. This is good, but still we have some discrepancy between the these Peters no question results. So I'm now pursuing the reason of this discrepancy, probably the high energy states, or I have to re-optimize the balance space or something like that. Okay, so this is a sort of the current status, and just summarize my talk. So the combination of the ChiralFT and the nuclear ab initio calculation can access parity variating moments. And I showed that the unnatural parity states are accessible in the VSMSRG framework. And now the applicability of this VSMSRG can reach to the mass number 200 or so. And I am planning further investigation in the VSMSRG step to compare with the for the better agreement with the no-question model results, like adding the keep adding the high energy state contribution, or employing the Lanczos continued fluxion method, which is already introduced by Peter talk, and or maybe need to optimize the variance space or some other test I am thinking of. And once it could be done, they are done, then I can go heavier system. So yeah, that's all. Thank you very much.
Thank you. So, do we have questions for Takayuki? Please put them in the chat. Okay, so John, please go ahead.
Yeah, if you wanted to apply this to shift moments, the shift operator, most of its strength is at 3h bar omega, so 3 shells above the valence shell. Is that possible for you to in a shell model to have a space that big?
Okay, in that case, probably the direct diagonalization be impossible. So we need to combine with some sophisticated method like Monte Carlo shell model or something.
Can you construct effective operators for a 3h bar omega space?
That I haven't tried, so I don't know well. But yeah, I don't know actually. I haven't tried. But in the past, I have tried just like a PSD PF space decoupling, but that works. So might be possible, but I don't know if it works in a heavier system. I don't know.
So, any other questions or comments?
I have a question.
Please.
Yeah, so, Takayuki, when you discussed the deuteron calculation with the IMSRG, so it seems like you had to use a very high beta compared to what you do and in these other calculations.
Mm-hmm.
So do you understand why is that? Or?
Oh, I think simply the center of mass Hamiltonian is proportional to 1 over A, right? So the deuteron case is just A equal 2, and the other case is like a 15 or 10. So it's usually the center of mass contamination effect gets negligible in the heavier system, I believe. That's probably why we need to large beta for this deuteron case.
But then you show that in these heavier cases, then you could get a spurious contribution, negative energy, right? If you had very large beta.
In a heavier case?
Yeah, you showed this 2 valence space calculations where you had to stop at like 3.
This one?
No, before, but okay.
Before. Oh, this one, I think. Yeah, in that case, you have to optimize the valence space. Like we have to avoid such the IMSRG spoiling valence space. You have to avoid that.
Okay, thank you. So Robert, please go ahead.
I just have a technical question because I'm not a nuclear structure theorist, but can you explain quickly what your E3 max parameter is in your or little e 16, 12, 14, which you were using in order to converge your results?
Okay, so the E3 max is the boundary number for the 3-body matrix element we can use, and ideally, we do not want to have such a truncation. In that case, the cut should be the 3 times of this number Emax. The Emax is the number of major shells taken into account in the calculations. So the idea you want to have like E3 max equal 40 or something, but it's definitely impossible. So we have to introduce this E3 max truncation, and which is given by the sum of 3 particle measure shell quanta.
So the difference between those quanta in which they are, so to speak, and then you cut at this value. So whatever is higher in the combination, this you drop.
Yeah, like if the three particles are in the, you know, the highest shell, then it could be removed.
Okay. Okay.
Okay, thank you. So I don't see other questions. So I'd like to thank Takayuki and all the speakers of this session for wonderful talks and very exciting new results. So now I hand it over to the organizers for the.
Thank you, Vicente. So yeah, now the idea will be to have some discussions. So Dima was going to present the last part, but unfortunately he was not able to present. I know he was coming back in at 4:30, so he might be appearing soon. So I suggest we continue the discussions with the speakers of the afternoon. So we just go to breakout rooms, and I ask to the different speakers to join the rooms. And then we come back if Dima comes back.
Do we each have a room, or
just select
the
select the room and we'll follow. So the idea is normally we will be chatting and asking the naive questions that we like to ask to you guys. Yeah, so then we will try to do that with the breakout rooms. Yeah, feel free to go to one and then we'll be jumping.
Yeah, because it makes sense if Takayuki and Peter and I are on the same, at least, probably.
Yeah, that sounds good. Yeah, we can have the ab initio room. So break the ice.
Yeah.
For those that would like to have independent discussions, yeah, we encourage that. So the idea is to have some open discussions. So please join the rooms and let's try to recreate what we'll have if that were an in-person meeting. Yeah.
So everybody went to room 2. All the speakers,
Almost like we should just keep it public, since everybody seems to be going into room 2.
all 4 speakers, yeah.
Good thing we have 10 rooms, huh?
Just let me know if you want me to make any adjustments for the rooms. I mean, everyone's already in room 2 now, but yeah, so I'd have to close the room and then open them, but
No, it's fine. Just I think leave it open, and then if everybody assembles in room 2, it's fine, right? So that means the discussion goes on.
okay, sounds good.
Sorry, I was speaking myself. It was mute. So, can you hear me now, Robert?
Yes, I can. Yes.
Good. So yeah, I was saying Dima was going to join,
Yeah.
present a few slides about the gamma ray factoring.
Yeah, that would be lovely. Yes.
But I'm not seeing him. Would you be in this main room, Robert, or you are joining a room as well?
I will stay in the main room just in case Dima pops up. But,
okay.
Yeah.
Then I will join a room.
Yeah. Okay. Excellent.
Yeah.
So since you, Andrew, have your camera on, I can say great talk yesterday. So I liked it very much.
Great. Thanks, Robert. Yeah,
it
went faster than it went fast.
Your talk?
No, I feel like I left out points and stuff afterwards always. I don't know. It's a constant.
Yeah, but that's a normal situation, no?
Yeah. No problem.
I think your point came very well across, and also, yeah, it looks very promising. Very good.
Yeah, it should be fun.
Yes.
I think, yeah. I at one point I didn't feel like I made that well is that, what we're doing, we're very focused on an EDM measurement. But what we're working on generally, I think could be fun and helpful at a facility, at some kind of facility or in other labs for, a bunch of other purposes. I haven't delved deep into this, but it seems like actinide chemistry is kind of interesting. And so studying these kind of molecules could be generally beneficial or interesting.
Yes, definitely. I mean, there's a lot of mass spec studies, of course, right? So I think Richard O'Hare and others did a lot of mass spec on the actinides. But of course, then you have mostly the mass, right? And but no spectroscopy. And I think that's really the add-on, so to speak, to. And I mean, your method allows this, right? So that you.
It should. It really should. I mean, the NIST group really has pioneered the heck out of this, and our kind of I think honestly, like one of the first things I can imagine doing at a facility like FRIB is if you can just get a trapped protactinium-229 ion, you could figure out what the spin of the ground state is. Like we don't, I think the spin of the ground state of that atom's unknown. So we could just do spectroscopy on, do quantum logic spectroscopy on just rare atoms that live a short time. This all really hinges on, I think, Ronald's the person I know working the most on this, but taking those hot products and then, cooling them, slowing them, and then getting them into an ion, into like the type of ion trap that I use.
Yes, that you really have it trapped, right? Yes.
Yeah. Trapped in it, whatever, laser cooled temperatures, not, I think Ronald's first stage trap is at like 40,000 Kelvin, so they have them trapped. They're just super hot. And then they cool them as they leak them out of there. Yeah, I don't know. Holding on to charged particles is pretty easy. Well,
yes, compared to the neutrals, I mean, that's a deep potential, right? So it's like if you're driving with a car and then you have a tiny hump, that would be the neutral situation, or you have a deep hole which sucks your entire car, right?
Right.
So that's kind of the difference. Right?
Yeah, right, exactly.
No, the ions have this particular advantage, of course, but I mean, with all the drawbacks which one also has.
Yeah, no,
it comes to
definitely.
Precision, right? Yeah.
No, definitely. I guess all the ion optical clocks have this thing where they can, have really high precision. Like the systematic uncertainty can be incredibly small, but their averaging time to get to that, to realize that kind of precision is tremendously long, weeks and weeks.
Yes.
So this, small.
Yeah, that's
right?
a clock where you don't look too often at it, right? So you let it tick for I don't know, a couple of weeks, and you look at it and say, okay, let's adjust the other clock.
Right, exactly. Yeah, exactly. Hey, Ronald. I can't hear you yet, Ronald.
Again, when I jump the rooms. So yeah, Dima didn't arrive. So I think it's
no.
So most of the people is in the room.
Yes.
So yeah, I think we just have 3 discussions. Yeah.
Well, that's fine.
Yeah. Ronald, how's your Robert and I were just discussing facilities and molecules and ions at facilities. I was wondering how you're kind of slowing and this kind of efforts are going work towards getting these hot ions into traps eventually. Like really low temperature kind of traps.
Yeah. So it's going well. So we are designing that. So now we're assembling the beam line. So hopefully
at MIT, right?
At MIT, and we'll move that to EFRIB eventually. Yeah. So I think there is hope that we can have in 1 or 2 years. EV beams, yeah.
Okay, that's awesome. That's awesome.
Yeah, that would be great. At the point that we can already trap them.
Yeah, you said EV beams. Is that what you said?
Yeah.
Okay, perfect.
Yeah, because now we have EV beams. So, I mean, we're trapping them, but we have to keep the traps at high potential. So then it's not so good for precision experiments. Because the beam comes at high energy, then we just put the trap at the energy of the beam. So if the beam comes at 40 keV, the trap is kept at 40 keV.
Yeah, don't touch it.
Yeah. And it's a very large trap.
Yeah. When it's at 40 keV, Ronald, what happens? Sorry, you guys do put a buffer gas in there or no?
Yeah, that's one. It's with the buffer gas, the one that we use for radium fluoride.
So if you leave it in, I mean, if it stays in that trap for a while, it doesn't, like the buffer gas temperature is much lower. It doesn't, that temperature, that 40 keV energy doesn't just slowly drift down to
because the trap is at high potential, then respect to the trap is EV energies, right? Or less than EV. So it's really trap. So we can trap them. So we can keep them in the trap. But respect to our lab, the trap is a very high energy. So if you want to, let's say, do a rotating field of everything, would be quite complicated.
Yeah,
or
because
your
you put it on
electronics.
this high potential, right? So that's a challenge to maintain it stable at, I don't know, your 40 keV. And
I see.
yeah,
Oh, I see.
so it's in principle as if you are riding in a high mountain, right? And then you have also maybe a tiny trap also where you can keep the things,
right?
Yeah? And so that's all fine. But of course, to really maintain everything at precisely this voltage for the precision measurements, that's much tougher than if you are close to ground potential, right? So that is how I understood it from Ronald, right?
Yeah. Then what we are doing is kind of, we use this first trap, send the bunch, and when the bunch passes by a tube, let's say, we apply a high voltage while it's inside a tube. So, and then when the ion tries to go outside the tube, it's kind of pulled back. So this is a kind of standard technique people use, trapping these fast beams. Just that we are trying to do that very efficiently, as efficient as we can. Yeah. And connected that with the trap. So once you have the EV beam, then you have radio frequency guides. So the beam kind of, when you try to deaccelerate or remove that energy, right? Then the beam just blow up. So it just go everywhere. So then we have funnels that just bring back the ion beam. So it's mainly a kind of transport challenge.
This goes to like efficiency issues, etc. This is probably just too high of energy, but I'm just wondering if you're at 40 keV, can you like evaporatively cool in that trap and slowly lower the potential and, you know, have fewer ions or whatever, but end up at a keV, like with some reasonable efficiency, something analogous to
you can do laser
cooling?
cooling and everything there. So in this trap, sorry, Makoto was okay. So yeah, the problem is that how to communicate with the trap that is at high potential is just challenging, right? So, but yeah, I think we are just deaccelerating. It's just a technical. And in principle, the simulations say that it should be done. And as I said, people do this kind of work.
Yeah,
so
yeah.
And we face our challenges because if we want to study neutron molecules, then we don't know what's happening when we neutralize. And at what moment should we do the neutralization? But for the ions, I think we have a good chance to do that efficiently. To start with the fast beam, deaccelerate, and trap.
Yeah, no, definitely. I know.
Yeah, let me see if I have a. So you see this?
Yeah.
That's kind of a scheme. They're just going everywhere. You have like funnels sending to a trap.
Yeah.
The trap is at high potential, so 30 keV or 40 keV. Then,
okay, wait. Let me ask you this question, Ronald. The trap potentials at whatever it is, 40 keV.
Yeah.
What is the energy distribution of the particles in that trap?
Okay, so when it enters, can be tens of EV, depending how they are produced. That's because we use this buffer gas. And in principle, they can be EV once you have the buffer cooling.
Right.
So
Okay.
it depends how cold is the gas and the pressure of the gas. But we think that outside it can be less than 1 electron volt. So here, with respect to the trap, is just like a normal trap, right? Sub EV and it's trapped there, and we can keep for well, seconds, or more, right? But that's the problem. They said high potential, so we release them, and then they just enter into a region. So what we are doing now is they are neutralizing flight, okay? So then they are neutralized, and the region of interaction we will ionize in this region. So they enter as a neutral atoms, then they don't feel the potential. Then you ionize, but because the region is at high potential, then it's pulled back. So then you have like some lenses, and at the end you have this sub-EV beam. But yeah, because it's low energy, then it wants to go in all directions. So we have some like radio frequency funnels, that you use, and then you inject into the trap. So at that point, we were thinking in a 22-pole traps for some, because people from chemistry use that very efficiently to study molecules.
Mm-hmm.
But now we are doing a 10-pole trap.
That seems reasonable.
Yeah.
And I mean, correct me if I'm wrong here, but if you just want to trap the ions, you would get rid of the neutralization stage, unless I missed something about the.
The trapping part is just because we would like somehow have a potential that pulls them out, okay? So then, for practical reasons, and also for many things, because it's not a pure ion beam. So it's let me just share again. So let me share the screen. So when the beam comes here, we have ions of many kinds, right? You can have radium, you can have a cocktail of many ions, okay? So then if you try to decelerate everything, then you will be injecting large contaminants into the trap. So you might have cesium, you might have, well, not in this mass, but whatever, thorium or whatever is in this mass, okay? So the reason of neutralizing and reionizing in flight has two advantages for us. One is the ionization process is very selective, right? So we are sure that whatever is ionized is what we want to study. So then here we have a pure beam of even the molecule that we like to study. That will be a plasma, right? Or the ion. Now there are advantages because they are neutral. They enter inside this region without feeling the potential. The full region is at the same energy of the beam. Let's say it's 30 keV, right? Then when they try to go out from the region, because they were converted into ions inside, then they will feel a potential pulling back. So then they will be decelerated. So they go out with low energy. So they feel they have to climb this potential. They don't have to climb the potential, but they enter because they enter as a neutron. But they have to climb when they go out because they are converted into ions inside. Does it make sense? Yeah.
Mm-hmm,
So then it's this double advantage. Because otherwise, if you want to decelerate, you always have the problem, right? You apply the potential and then the last region is kept at high potential. So if you want to go back to ground, then you reaccelerate, basically.
Yeah. No, definitely.
Or you can apply pulses. So people do that, apply pulses, but because the neutralization reionization is very selective.
Yeah,
it's a very selective ion. So.
Yeah, but
No,
sometimes, I mean, the things, it's not always like in radium fluoride, yeah, where the neutralization does break up the molecule. You often have the situation that you have dissociative neutralization, right?
Yeah, that's in general for ions, okay?
Yeah.
So that's, we initially designed that for ions. So yeah, for molecules, we don't know.
You mean
good?
atomic
So we have
ions.
Dima came. So good.
Okay.
Yeah.
Great.
Dima, can you hear us? Or so he's having problems with the network. Yeah.
So what's going on in mines?
So yeah, for molecules, it might be that the chances, the good thing is we'll have low ions. We can inject into a trap, and maybe we can do kind of Andrew has been doing, okay, do the reaction inside the trap and create a molecule inside. Yeah.
Yeah, no, that's definitely something I'm interested in. Like, just get the isotope you want, get it in the trap, and then take your time to leak in a reagent to make whatever.
Yeah.
At least everything that we're doing now is just going to be with single molecules. Like later we could extend to, quantum logic on multiple, but that would be state of the art at NIST right now. But it's possible.
Yeah, no, that's cool. So I think our challenge now is we slow down and trap. Once we do that, we can apply all your methods. So as you said, you can bring your setup and just connect there. So that would be ideal.
Yeah.
So
we have
a facility that, and part of the idea of this workshop is that, right? We have a facility in which we share lasers. These are the most expensive part normally, right? And the beamline does this deceleration. So you can do many kind of experiments. Yeah.
The beamline is the most expensive part.
Dima, can you hear us now? Dima? Because camera is not on, but
yeah, he wrote that he has some some problems with it.
Okay. Yeah.
So for us it's more expensive than lasers, but because we have this lasers that we can tune, and we have multi-step reionization. We have more than 20 laser systems. Is that right, Shane? Shane is our
wow.
Yeah. The coordinator of the experiment at CERN. Yeah.
Yeah, I'd say 20, but then not just the lasers, the frequency conversion. So, doubling, tripling, quadrupling, things like this. So a huge amount of consumables which just go into, And also transporting the light is very expensive if you do it properly. So it's a huge amount of investment needed.
Transporting the light?
Yeah, exactly.
Yeah, because our laser lab is like 20 meters away, right? So the accelerator
20 meters away, it's downstairs, and we have to overlap the beams as well. So just getting the optics to overlap different wavelengths is very expensive to do it efficiently. And yeah, so it is a real challenge to get it all into the interaction region without losing too much.
Yeah, many of these slides that we are interested was deep UV light. So we need this frequency mixing and quadrupling. And we wanted deep UV light with lots of photons and narrow band. So we need these amplifiers, and each amplifier needs a pump laser. And so actually the beamline is, well, it's expensive as well, but not as, the beamline can be $1 million, but, or $500,000. Yeah.
Really?
Yeah.
Okay.
That's cheap, or?
Seems like it. I don't know. I really don't understand these scales very well.
Yeah, I think because at the end are pipes, and the expensive one are the vacuum stuff.
Okay.
Well, our beamline, right? It's just very small. The beamline of the facility is extremely expensive. But our portion that is 3 meters length,
Okay.
It's yeah, I think about 1 million is a good number. But the lasers can be more.
Yeah. Is the facility, I mean, when CERN is on, is it running, are people doing spectroscopy almost 24/7?
Different kinds, yeah. So yeah, not just laser spectroscopy, but yeah. So the facility that we just ran an experiment last week, actually, which is why I still look terrible and feel terrible, because it was very, very hard work. But yeah, so essentially when the protons are on target, you operate 24 hours per day, a couple of days between different groups and different experiments, and then you run for generally 8 months a year. This year's a bit different because it was the long shutdown in the previous 2 and a bit years, but then of course COVID delayed the start of this year. So this year started last week and will end in November. Something like that. And then of course it's not just Zolder, there's the AED, it's an anti-proton decelerator. They're doing antimatter spectroscopy. So people using lasers all over the site actually.
I see. They're using the Isolta laser system?
No, so they have their own entire facility. They require slightly higher energy protons than us, so about 20 GeV. And then they have, I think, even 2 or 3 laser groups there, which do, they did the 2-photon 1s to 2s transition. They're even doing, I think now we're trying to do Rydberg spectroscopy. They did laser cooling now of anti-hydrogen. So all continuous wave generally. Although I think one of them is a pulsed laser for the Lyman alpha cooling of the anti-hydrogen. So it's something like 123 nanometers. So pretty tricky to make.
Yeah, for sure.
So yeah, no, I'm maintaining the lasers. I think one of the most expensive things of these facilities is also the workforce. So the team that has to be there operating and maintaining that. So once you have the laser systems, when you have everything. Hi, Alex, how's it going?
Good. How are you? Just made it to the office to escape the 41 degrees outside. It's like, feels like Saudi Arabia here in Vancouver.
Yeah, I hear that you guys are experiencing record temperatures. Yeah.
So the one comment that I wanted to make is the really expensive part of that is the RIP facility. And I think that it needs to also inform the decision where to put it and how to put it. Because operating the RIP facility is $20,000 an hour, right? Just to put this into perspective. And making a beam delivery to an experiment is quickly in the hundreds of thousands of dollars. And having a facility that provides beam, that has the right niche, that has, I think Shane mentioned it, the problem that we have in all these facilities is we have all these very expensive and smart experimental end stations, but in the end of the day, we deliver one radioisotope beam at a time. And that means that most of these stations are idle for like 90% of the year, right? That allows for upgrades, that allows for maintenance and so on, of course, but the uptime could be much higher. So yeah, there's several projects investing into simultaneous beam delivery, and that might be something that is especially for these high precision experiment valuable, because it would enable longer beam times. Right now, beam times are limited to a few days at a time in all facilities, right? There's a few facilities that promise to change that in the future, but as a matter of fact, at the moment, it's in all facilities a few days at a time.
I mean, just from my perspective, just from the types of experiments I think about, in some ideal world, we would, get the beam for like an hour, trap an ion, and then use that for the whole day, and not use the beam outside of outside of that, and then, you know, repeat again at whatever 5 in the morning the next day when the ion has decayed.
Yeah, that's a challenging wish, because the type of beams that we are talking about here in this workshop require very dedicated target and ion source combinations, which means that it's difficult to anticipate to have basically another user that takes it 23 hours a day to make the beam available to you for 1 hour a day.
Right.
But again, a facility that operates several beams simultaneously will be more open for a discussion like that than a facility that has one beam, and then that's even worse, right? Because now the experiment doesn't take 24 hours for 5 days, but only 1 hour a day.
Yeah, that's a difference to synchrotron facilities, right? Where you typically have several beam times, and then it's only the question if you have bunched modes or not, right?
Exactly.
So those are the
That's very different. Yeah. And this is a major investment, right? In order to get such a facility, EPIC is trying to do that at Isolde. We have been trying to do, or we are trying to do that with Ariel, which is coming online now. But this is in the hundreds of millions, including the manpower to build such a facility. The EPIC's proposal is 300 million Swiss francs or so to get simultaneous beams. So having a facility that actually makes the beam available is probably the biggest investment, and also, in my opinion, an important pivot point in the science proposal that then enables funding for the end station and the PhD students, etc. And if you can go to a funding agency saying that you have 30 days of beam time a year, or 50 days, or 2 days, it's a big difference.
Yeah, definitely. So, by the way, we have Dima here. So, Dima, how is it going?
I hope I'm really sorry. This is terrible. It was working all the time before, and 1 minute before it started, now it's working again, it seems.
So I will go to the meeting room. So, and I will.
But we are in total 13 participants, if I'm not entirely wrong, right?
Yeah. So most of the people are in the meeting room, so we can call them.
Okay. Yeah.
It's not adding the breakout room numbers to this 13.
Yeah, exactly.
They have like.
There are more than 20, I think, in the breakout room.
Yes, excellent. Yeah.
So let me see what they are doing, and I will come back.
Okay, cool.
I just pray it doesn't break again.
Yeah. Are you in Mainz at the moment, Dima?
Yes.
Yes.
Yes. I've been teaching for 1.5 years and having like Zoom meetings all day, every day, and it usually doesn't happen. Sometimes it, drops out.
Yeah, for a second or so, right? But not that long. Yes. Yeah. Yeah. So that's really unfortunate.
So Robert, just for information, we're going to be trying the in-source on the, I think it's a weekend, but let me just look at the dates.
Okay, cool.
You have your dosimeter things, don't you, for Isolde?
Once again, please.
You have your dosimeter for the hall. You're allowed into the facility, right?
To be honest, no, I don't think so.
Okay.
But so I think I cannot go to the hall, but I can go upstairs into this.
Okay, great. Yeah.
So that would be fantastic. So it would be on this weekend, you mean?
Yeah, no, so it'll be the 10th, 11th, and 12th of July, I think, is
okay.
scheduled.
Yeah. Okay.
Yeah. So it's coming up.
Cool.
And we'll set up for it as soon as Rillis is done with the magnesium online run.
Mm-hmm. Yeah. Okay. Ah, wonderful. That's excellent news. Great, Shane.
Yeah.
Okay, I think we are almost all back. So Nick, can you please bring the all to the main room. So I still see a few names outside.
Sure thing.
So yeah, Dima would like to continue his last minute of the presentation. So he will present how to measure protactinium highly charged with a laser beam.
Protactinium, maybe. I just really apologize that this is happening with my network, and I pray it doesn't break again, but we'll see. Actually, maybe before I continue, I just realized from Week's question that there was potentially one confusing thing that I need to. For the thallium fluoride, this J1 has nothing to do with angular momentum. This is this spin-spin coupling tensor, historically called J coupling. So this vector, in fact, is proportional to the molecular axis. So it's a normal vector. So this kind of Hamiltonian is time reversal conserving and parity violating, as it should be. All right. So I think my network disappeared when I was presenting my coworkers. I don't know if you heard or not. So this is the Minds group, and these are collaborators elsewhere. Can you hear me?
Hearing, yes, but you don't share yet, at least on my screen.
Oh,
are you?
Okay. This is a problem. I was trying to do this. Let me see. What now?
Yes, we are seeing.
I'm sorry about this.
It's not yet the presentation mode, though.
So maybe I go here and that's what I want to show. Yes. So the sorry, I have to repeat this. This spin-spin coupling, and this is confusing notation having to do with history. That this is the vector corresponding to this spin-spin coupling tensor, and it's not. It has nothing to do with angular momentum. So this Hamiltonian is in fact time reversal conserving and parity violating. Yes, thanks, Week, for asking this question. All right, then these were the collaborators, and this is the Minds team, and these are people elsewhere in US, in Germany, in the Max Planck Institute, and so on, and even in Novosibirsk. All right, so what I'd like to tell you now is maybe the closest of my 3 short stories that comes to something radioactive. And this is a Gamma Factory at CERN. And this is a proposal, I would like to say, sort of in this, semi-jokingly, that this is a way to convert LHC into a tabletop experiment. But seriously, this is a proposal to make a rather unique source of photons, and at the same time a precision ion trap for all kinds of experiments. And the idea is shown here. The central point is that in the LHC that is designed for circulation of either protons or bare nuclei, you can also actually have atoms, well, ions, with most of the electrons stripped, but maybe 1 or 2 or 3 remaining. So the typical system we are talking about is, for instance, hydrogen like lead or something like this. And these partially stripped ions can be accelerated to ultra relativistic energies with a relativistic gamma factor of 3000 or so. And then you take a laser photon and you Compton scatter it from this atom. And this leads to, I'll show you in the next slide in more detail, this leads to photons of very high energies going in a narrow angle in the direction of propagation of the ions. And this was formulated as a proposal to CERN in 2015 by Witold Krasny. This promises to be a source of unprecedented intensity of 10 to the 17 or so photons per second with energies up to 400 MeVs. And then you can actually play tricks and even have higher energies if you like. It is a very interesting and unusual laboratory where you can do experiments already with your primary beams interacting with your ions here, the secondary beams that you are producing. And then you can also send your photon beam into targets, and you can produce tertiary beams of leptons, neutrons, neutrinos, and so on. And you can do a lot of interesting things with them as well. So the physics here is not very sophisticated, but very beautiful. And there are two frames you can look at this in. One is laboratory reference frame. And so you have this ultra-relativistic ion and the normal optical photon coming in. And if you go to the rest frame of the relativistic ion, there is a relativistic shift of energy of this incoming photon by a factor of 2 gamma Lorentz. So 6,000 or so for LHC at the highest energies. The next thing that's happening is best seen in this frame. So this is an atomic system, say 2-level system for simplicity. So you absorb the photon, and then when the atom de-excites, it emits the photon in an arbitrary direction in its frame. And it's in the simplest case, it is basically a nearly elastic scattering, but could be also some kind of a Raman process. But let's say 2-level system and nearly elastic scattering. Then if we look at this back in the laboratory frame, there are two parts of relativistic magic that happen. One is that most of the photons that were going, in the arbitrary direction in the ion frame are now going, in fact, in the forward direction. And if you look in the forward direction, then there is an additional boost in energy by another factor of 2 gamma. So as a result, you have 4 gamma squared, and then you can calculate what kind of energies you get, and with an optical photon, you get up to 400 MeV or so. And sorry, I have something that appeared here. So it appears promising, but you might ask, is it really realistic to have an atom in the LHC? Will not the electromagnetic field in the ring rip the electron of the atom and strip it? Is it possible or not? So the answer to this is yes, it is possible. And a few years back, there was a demonstration where I believe that was hydrogen-like lead and helium-like lead was first accelerated in the SPS. This is a injector, formerly a collider, now an injector for LHC, and then circulated in the LHC for a couple of hours, from which the lifetime of such ions in the ring were determined to be in excess of 40 hours. So basically, this works. I hope you still can hear me.
Yeah.
Good. Okay. So from this initial proposal by Witold Krasny, this has grown into a study group that now operates as part of the, in my opinion, amazing program, amazing and visionary program at CERN called Physics Beyond Colliders. CERN really wants to remain a laboratory that's highly relevant for the future, and so they are looking into many different options of what to do in the future, and those include interesting things like, for instance, EDMs and storage rings, various dark matter searches, etc., etc. And Gamma Factory is one of these study projects. So it's now a pretty large group of volunteers at this point who are studying different aspects of what can be done. And it turns out that if you take a sort of white sheet of paper and start writing down all the interesting things you can do, it gets, first of all, very exciting, and there's a lot of things you can do in different sort of areas of physics. For instance, last year we published this catalog of what you can do in terms of atomic physics, mostly physics of highly charged ions. Here, the way I like to think about this is that how do we do precision physics? We of course use lasers or some kind of nice light sources, and then some of the best, most precise measurements, they come from ion traps, and then you can think of these ions that can be very well controlled. You know, the beam of the ions can be focused down to maybe 20 microns or so, and that there are very precise position monitors and timing and everything. So and the lifetime is very long, and you can trap very exotic things in it. So you can think of it as really a tabletop style experiment, if you like. So I'm not going to bore you with very many things, but you know, these are atoms, and you know, this is very nice because you start with basically a normal optical laser, and then you boost the energy by a factor of 6,000 to gamma when you go to the ions frame, and so you are now from electron volts, you are you know, several tens of kilovolt, if you like, and so you can drive these transitions. The idea, by the way, is that the difference of this source from Compton scattering sources that use electrons, for example, is that here you're not scattering from a free electron, you are still scattering from an atom where the resonant cross section is on the order of lambda squared. So it's a nice a big cross section, and so you can do a lot of things you do with atoms. For instance, you can do optical pumping, which results in electronic and nuclear polarization. And then there is a question if this polarization actually is going to survive a round trip in such a machine. So there are, of course, accelerators where polarization surviving many turns has been realized, but not this kind of machine. So it's a little bit of an open question. If it is possible, then perhaps one can think about measuring EDMs, but this is an open question whether it's possible or not. But regardless, even single path allows you to have optical pumping, and so you can study, for instance, parity violation. So from atomic physics survey, we then moved on with a group of extremely nice co-workers whom I am very happy to recommend as some of the best physicists and co-authors that you can find. We put a pretty large survey of what you can do in the area of nuclear physics, and it's a very, very big, it turned out actually as a review of, a little bit of a review of different parts of nuclear physics. as well. It's a 60-page paper, and I'm very excited about it. It can be found on the archive. And here, by the way, one of the connection to radioactive molecules is that these large photon fluxes, secondary photon fluxes, allow you to produce a lot of exotic isomers and isotopes, and perhaps this could be a source for radioactive molecules. That's one of the connections to this meeting. Anyway, so my traveled talk today was about 3 short stories. Each one can be made a long story, but these are short stories for today. The first one was about the idea of measuring parity violation in liquid state NMR using this effect of Dyer stereomerism that splits the frequency of NMR transitions for different enantiomers in chiral solvent. And I told you about our experimental progress in this direction. The second short story is a proposal to search for nuclear spin parity violating time conserving effects in spin-spin coupling, which started as also actually zero field NMR liquid state, zero field liquid state NMR idea, but actually evolved into a suggestion that we hope will be adopted by the Centrix experiment, and would be sort of a side experiment for them. And I'm hopeful that one of these 2 techniques would succeed finally in detecting parity violation in molecules, which maybe it's a bit of a shame for our community that with 50 years of trying, we still haven't even detected parity violation in any molecular system. And maybe motivation, let's put it positively, motivation for our community to measure parity violation finally. And then the last thing is the Gamma Factory at CERN. It's a novel tool which can be thought of a unique light source and at the same time a precision ion trap. And as to protactinium, so the idea would be it has to be, I haven't thought about protactinium in this context before Week's talk, so it has to be thought through carefully, but maybe you can have a partially stripped ion of protactinium that would be free from the decay due to electron capture. So it will have a long lifetime, and then the normal optical laser, or perhaps even a static undulator or something like that, can be tuned into the ion frame due to relativistic Doppler shift, which can allow spectroscopy to detect and confirm this 220 electron volt transition. So that's I think is a very I'm grateful to this workshop for. I think this is an idea we'll be thinking about in the future. And so with this, I'd like to once again thank you for your attention, and deeply apologize for my internet quality.
Yeah, thank you very much, Dima, and thank you for coming back and staying till late to finish the talk. So I think we can take a few questions and then we will finish today. It was a great day. So from Andrew, would you like to start?
Yeah, sure. Just in regards to the Gamma Factory, I don't understand the geometry that well, but I'm just curious how things work out in the laboratory frame when you're, shining light on some transition. What is the, what happens to the transition width, and then what are, how do things like time of flight, broadening, et cetera, affect, or, how many photons can we scatter, I guess?
So you can scatter several photons in sort of one. Typically, it depends on the transition and so on. But you can typically scatter a few photons. Here you can start with a relatively low power laser and then have a cavity to enhance it if you like. Yeah, so all are good things that we need to think about, but there is nothing, no showstoppers that we found so far.
Good. More questions? So I will ask, so what's the plan so far? So what's the idea technically? You will start doing another proof of principle, or from the CERN perspective, is there funding?
Yes.
To
So
support
that
this?
is exactly. LHC, you know, it's generally hard to book time on LHC, and so the idea is to start with a full-blown proof of principle experiment at the SPS, the gammas are on the order of 100 there or so, and in fact, the first atomic transition that we plan to drive is a transition in lithium-like lead, which happens to be at around 220 electron volts, if I remember the number correctly. Is very close to protactinium transition. So that's the plan, and in principle, all the physics of the gamma factory should be well demonstrated with this proof of principle experiment, and there are even applications for instance in the precision heavy ion spectroscopy, which is actually a very interesting atomic physics, as some of the people in the audience know very well, because they are the experts in heavy ion physics.
Yeah, great. I think we can take the last two questions from John and Robert. Well, first, John.
This gamma factory, I'm blanking on an excellent Japanese theorist's name. I'm sorry. He has a center for physics at the center of the universe or something. He spent writing papers for a long time, harnessing electroweak unification to make from effects like this neutrino antineutrino pairs. And he wants to make a lot of antineutrino pairs and do a lot of physics with them. And some of this was tabletops. It's grown into things where he's irradiating a heavy ion, accelerated heavy ion beam at quite high energies, like the CERN as energies. So have you thought about this at all, Dima? Because what he can do, he can even do things where his production depends. He tries to measure the electron neutrino mass this way directly. By looking above some threshold on the atom, you start to make the path that makes the neutrino pairs. That energy of about how you stimulate in the atom, it's well matched to what the mass of the neutrino might be. But then he also wants the cross section depends, near threshold depends on whether it's neutrino Dirac or Majorana. I mean, there's some amazing things you can do with this theoretically, and as I understand it, it's all well founded in electroweak physics. So, is that on your list of things to do with this gamma factory?
Yes. So in this paper, one of the discussions there is about neutrino sources. You know, like the tertiary beam, and then there's of course a lot of physics you can do with those.
Might not be the same thing. I wish I could remember the man's name. He's well known. I'm just it's a great set of theory papers that have been written on this. They've done some work on nonlinear optics to do some of this stuff. Very preliminary work.
Is it Yoshimura, John?
That sounds right. What was it again?
Yoshimura.
Yeah, exactly. Yoshimura. Thank you.
Okay. Yes. Good. Thanks.
Okay, good. And the last question from Robert.
I have a quick question related to the possible direct excitation of the nucleus, right? Because if I recall this correctly, if you are completely stripped of electrons or have too few, then the cross sections are extremely small, right? For a direct laser excitation.
Yes, of course, yes.
So what are the prospects to see something?
Yeah, actually, yes, good. The beauty of resonance is that the resonant cross section, if you have a closed transition, is pi lambda squared, right? So no matter what kind of resonance it is. And so if you go to, for instance, low excitations where it's only one single channel, the cross sections are actually pretty large. So we have a table of low energy nuclear transitions, and there are interesting proposals, even including laser cooling of ions using nuclear transition that Professor Tkalia, Eugene Tkalia in Moscow has written some papers about this. And even though the the rates are low, but the ions live so long in the storage ring that you can actually laser cool.
Okay.
Yeah.
Thanks.
Yes, but if you are interested, have a look at this preprint. There is actually a pretty large part of it is about direct spectroscopy of nuclear transitions.
Mm-hmm. Okay.
Sorry, I was mute. Yeah. So once again, thanks to all the speakers and participants. So we'll see you tomorrow at 9 a.m. to continue the discussions.
Thanks so much. Bye-bye.
Bye-bye.
Thanks a lot.
Good. Yeah. So yeah, Nick and Robert, and we have Stefan as well. Yeah, just to coordinate tomorrow,